Distinguished guests, inquisitive scholars, and my dear colleagues in the aerospace industry, it is with great honor and sincere enthusiasm that I welcome you all to the MRAE 2025, the third international conference on modern research in aerospace engineering. This esteemed event, organized by the Amity Institute of Aerospace Engineering at Amity University, Uttar Pradesh, represents a significant occasion where we gather to explore the latest developments in aerospace innovation. The theme for this year is Promoting Innovation and Research in Aerospace Engineering for Vikasit Bharat, embodies our collective commitment to leveraging knowledge, research, and innovation to support India's development as a self-reliant and technologically advanced nation. Through collaborative efforts, we strive to foster a sustainable future and achieve significant milestones in the field of aerospace engineering, aligning with national progress and technological excellence.
It is with great pleasure and heartfelt warmth that we welcome our esteemed guests today. Your presence truly elevates this occasion, and we are honored to have you with us. As we gather to celebrate and recognize excellence, we extend our deepest gratitude for your time and support. Let us now begin this special moment by handing over the Tulasi sapling to our distinguished guests who have inspired us with their achievements and contributions. As the Tulasi sapling symbolizes purity, prosperity, and good health in the Indian tradition.
Firstly, we would like to request our Honorable Dr. W. Selvamurthy sir to kindly present the Tulsi sapling to our chief guest, Honorable Group Captain GVG Yugandhar sir. Guys, can we please have a round of applause?
We now request Dr. Sanjay Singh sir to kindly present the sapling to our guest of honor, Group Captain Sanjay Kumar Singh. Please give a round of applause.
I would like to request Dr. V. R. Sanal Kumar sir to kindly present the sapling to Honorable Dr. Selvamurthy sir.
I would like to request Dr. Rajesh Kumar Saluja sir to kindly present the sapling to our Honorable Conference Chair, Dr. Sanjay Singh sir. And finally, I would like to request Dr. Neeraj Kumar sir to kindly present the sapling to our Honorable Technical Chair Professor, V. R. Sanal sir.
We would like to thank all the dignitaries. Moving on, knowledge is the light that dispels darkness. To symbolize the illumination of wisdom, we now invite our chief guest, our guest of honor, along with all the distinguished dignitaries present on the dais to kindly come forward and perform the ceremonial lighting of the lamp. To seek blessings for knowledge and learning, we now invite the students of Amity Institute of Aerospace Engineering to present Saraswati Vandana. May this invocation inspire us to dedicate ourselves to the pursuit of wisdom and excellence. This sacred ritual not only pays homage to the source of wisdom but also embodies the spirit of learning, an enlightenment that resonates deeply within us for our academic community. As our students come together to offer their heartfelt tribute, may the blessings of Saraswati inspire us all to reach the greater heights in the pursuit of knowledge and innovation. We are from third year. Yes, sir. So I just want to do the CPA, commercial pilot license. So I just started preparing for the DBT exam. Now I'll start with my medical number. There are many science schools in India. No, sir. I mean, sure. हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। तू स्वर्ग की देवी है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे। तू स्वर की देन है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे। हम हैं अकेले, हम हैं अधूरे, तेरी शरण में हमें प्यार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। मुनियों ने समझी है, मुनियों ने जानी, वेदों की भाषा, पुराणों की वाणी। मुनियों ने समझी है, मुनियों ने जानी, वेदों की भाषा, पुराणों की वाणी। हम भी तो समझे, हम भी तो जाने, विद्या का हमको अधिकार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ। हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ।
We would like to sincerely thank the dignitaries and singers for bringing a spiritual start to the program. No work can attain the status of a masterpiece without proper guidance. We at the Amity Institute of Aerospace Engineering are privileged to have Dr. Sanjay Singh Sir as our head of institution and the conference chair for MRAE 2025. Sir is an alumnus of IIT Kanpur, and his leadership as the head of the Amity Institute of Aerospace Engineering has been instrumental in guiding our institution towards excellence in education and research. His visionary guidance, years of experience, and unwavering dedication have propelled AIAE to the forefront of aerospace engineering.
I would request all of you to give a round of applause and please stand up as we welcome our Vice Chancellor, Professor Dr. Balwinder Shukla ma'am. Students, we kindly request you to please be seated.
Sir's visionary guidance, years of experience, and unwavering dedication have propelled AIAE to the forefront of aerospace engineering.
We would like to request Dr. Sanjay Singh sir to please present the Tulsi sapling to our Vice Chancellor, Professor Dr. Balwinder Shukla ma'am. Students, we request you to kindly clap as we present the Tulsi sapling.
Sir's expertise in the field and his commitment to fostering a culture of research and innovation are truly commendable. We believe that his words of wisdom and encouragement would greatly inspire our conference attendees, motivating them to strive for excellence in their respective endeavors. I now invite Dr. Sanjay Singh sir to address and introduce today's program to this esteemed gathering.
A very good morning to all of you. On behalf of our Honorable Founder President Sir, Dr. Ashok K. Chauhan, Honorable Chancellor Sir, Dr. Atul Chauhan, Honorable Vice Chancellor Madam, Dr. Balwinder Shukla, President ST, Honorable Dr. Silvamurthy Sir, I feel extremely honored and privileged to extend a warm welcome to our chief guest, Shri GVG Yugandhar ji, Group Captain and Director General, Aircraft Accident Investigation Bureau, Ministry of Civil Aviation, Government of India. Our guest of honor, Shri Sanjay Kumar Singh ji, Director, Aircraft Accident Investigation Bureau, Ministry of Civil Aviation, and all the keynote speakers, scientists, delegates, faculty members, and students to this third international conference on modern research in aerospace engineering 2025, which is being organized on the theme promoting research and innovation in aerospace engineering for Viksit Bharat. So it is a matter of great pride and honor for Amity Institute of Aerospace Engineering to organize International Conference MRAE 2025, bringing a common platform for scientists, academicians, and students. The main objective of this conference is to instill the research and innovation spirit in the students and community in general, to promote research and innovation in our nation and create researchers for tomorrow. This conference is going to bring together scientists, researchers, academicians around the globe for deliberation and experience sharing. This conference is being organized under the able leadership of our Honorable Founder President Sir, Dr. Ashok K. Chauhan, Honorable Chancellor Sir, Dr. Atul Chauhan, Honorable VC Madam, Dr. Balwinder Shukla, and President SC Sir, Dr. W. Sirvamurthy Sir. So our Founder President has taken the education at global map Today, Amity Education Group, comprising 12 universities, over 150 institutions, 28 schools in India, and 13 international campuses, nurtures more than 250,000 students under the able guidance of 8,000 plus faculty members. Under the dynamic leadership of our Honorable Chancellor, Dr. Atul Chauhan, Amity has able to file more than 2,564 patents with more than 445 granted recently, and has produced over 45,000 journal papers and reputed journal papers indexed by Scopus SCI papers. And apart from this, our Amity faculty has filed, there's developed more than 4,700 case studies widely referred by leading institutions such as Harvard, MIT, Oxford, and Stanford, with 50 plus advanced research center and over 500 funded projects. In collaboration with government bodies, industry, and global institutions, Amity has established a strong innovation and research ecosystem in the field of AI, cybersecurity, space science, and renewable energy, biotechnology, etc. Our dynamic Honorable Vice Chancellor Madam, Dr. Balvinder Shukla Madam, has taken the Amity to the top position with the recent NIRF ranking of 22, NEG A plus grade, and VASC QA international accreditation. Please join your hand together for our Vice Chancellor Madam. First MRAE conference was held in 2016, and 55 papers were received. Out of 55 papers, 35 accepted papers were presented and published by Springer. In our second conference, which was held in 2023, we received 84 research paper, and out of 84, 52 papers were accepted, presented in the conference, and 48 paper later on 48 paper were published by the Springer. But in this conference, MRAE 2023, we received 201 research paper and we accepted 114 papers. And these papers and the 140 papers will be presented in 13 different technical tracks, and out of this 114 papers, 12 paper, best paper will be selected, because we have tie up with one journal of aerospace, aeronautics, astronautics, and aviation. So best 12 paper we will send for the publication in this journal, and remaining presented paper we will send to the Springer for the publication. Later on all the paper will be indexed by Scopus. So in this 2-day conference MRAE 2025, 12 keynote invited talk will be delivered by national, international scientists, academicians, and these are, we have Dr. Rakesh Kumar sitting here. So he is professor and HOD Department of Aerospace Engineering, Punjab University College, Chandigarh. Dr. R.S. Pant, Professor, Department of Aerospace Engineering, IIT Bombay. Dr. Sanjay M.R., Principal Scientist from Thailand. Sachin Singh Gautam, Professor from IIT Guwahati. Om Prakash, Professor from UPS Dehradun. And we have international speakers. We have international speaker from Abu Dhabi, Kazakhstan, and one more speaker is and Vasat. So Amity University, as you know, Amity University is a research and innovation driven university. So at Amity Institute of Aerospace Engineering, we always promote research and innovation among the students. We involve our students in the research activity. So as a result, our UG aerospace student, first year, second year, third year, and final year students, our PG, MTech students, they present paper in the reputed international conferences. Recently, our second year aerospace student visited USA to present 9 research papers of our aerospace propulsion group in the top conference of the world, that is AIAAA conference. And last month, our second year aerospace student published a research article in NPJ journal. This is the Q1 SCI journal. Please join your hand together for our students. In the last 1 year, our B.Tech Aerospace and M.Tech Aerospace students have presented more than 40 papers in international conferences, and they have also published more than 15 papers in a reputed journal. So based on these publication, what is the outcome of these publication? Based on these publication, our students are getting admissions in the top university, international university with scholarship. Last year, based on publication, our B.Tech aerospace student, Miss Deria Pinto, she secured admission, direct admission in PhD program at John Hopkins University with a scholarship of 48,000 US dollar for 3 years, subject to increment of 18% every year. And apart from this, without any that is tuition fee of 68,000 US dollar is paid by the university, and the same amount will be paid for the next 2 years. She also secured first position in Yukti Innovation Challenge and got funding from AICT of 7 lakhs for her innovative idea to develop underwater vehicle to collect microplastic particles. I am confident that the third international conference on modern research in aerospace engineering MRAE 2025 will serve as a crucial platform for fostering intellectual exchange and developing innovation solutions to meet the dynamic challenge of aerospace sector. Through collaboration, discussion and presentation, MRAE 2025 aspires to contribute significantly to the evaluation of aerospace technology and applications. So we look forward for valuable synergy through collaboration and meaningful participation in MRAE 2025. So with this, I once again I welcome all you to the Amity University to this international conference MRAE 2025. Thank you.
Thank you, sir, for welcoming the gathering with grace and giving us an overview about the conference. Next, I would like to welcome our Vice Chancellor, Professor Dr. Balvinder Shukla ma'am, to inspire us with her words. Over to you, ma'am.
Very good morning to all of you. Good morning. That's better. Very respected, Honorable Founder President, sir, Honorable Chancellor, very esteemed Chief Guest, Group Captain GVG Uganda, Director General, Aircraft Accident Investigation Bureau, Ministry of Civil Aviation, Dr. Sanjay Kumar Singh ji, Director AAIG, Dr. Silamurthy ji, Dr. Sanjay Singh, my esteemed colleagues, and very dear participants and the students. And I was really very happy and delighted to listen to the address of Dr. Sanjay Singh when he was sharing the achievements of his students, the achievements of his alumni. And I think that is always a moment of pride, elevation for any teacher when the students do so well. I, on behalf of Honorable Founder President, Honorable Chancellor, all the additional Vice Chancellors, Deans, Head of Institutions, I extend very warm welcome to our esteemed Chief Guest, the guests of honor, distinguished speakers, all the participants for this very important conference being organized by Amity Institute of Aerospace Engineering. The conference on the theme Modern Research in Aerospace Engineering. And I think the discipline of aerospace engineering is extremely important. And when we have the Viksit Bharat, the space mission, and how the space missions will play important role in all spheres of the nation building, whether it is defense, whether it is agriculture, whether it is other disciplines. And therefore, I want to congratulate all the students who have chosen aerospace as their the graduation and post graduation education. And I think that when Honorable Founder President started this program, and he was very clear in his mind that the aerospace engineering and the space science and technologies are two so important disciplines. So therefore, as per his vision, we develop the talent who will be contributing to research, innovation, as well as through the other means to the economic development of nation, as well as they will contribute to the industry growth. And I'm very happy that the way in the last couple of years, how the MIT students especially have worked very hard, and the credit goes to all the faculty members of aerospace engineering under the leadership of Dr. Sanjay Singh, who is very passionate. And whenever we have any review meeting, he does not commit just like that. And he will say that it will take time, but my student will produce the result. So that's the confidence your director has in all of you. And the dream of our chancellor that every MITian be a success story. And each student will be innovative, creative, and will not only think for looking for the job, but looking for maybe starting their own venture, maybe creating the products which are important for the society, for the industry. And today I'm really deeply honored to have among us the Group Captain GVG Uganda, Director General of Aircraft Accident Investigation Bureau from the Ministry of Civil Aviation. The moment I met, the first thing came in mind. I think that everybody has that, the fatal accident which happened in Ahmedabad. What happened? So he shared that still the investigation is going on, and I can understand it's such a complex. Finding the truth and finding the, what exactly has happened. And it is really, really very challenging task. But I think every challenge gives the new learning and the new directions. And I'm sure while he will be addressing all of you, he is going to bring what is the excitement, for the aerospace engineers, what is the future, what are the career options, and how all of you are going to contribute to the nation building. And I'm extremely thankful to our Honorable Founder President, Dr. Ashok Chauhan, who has given such a great platform, the MIT Education Group, to all of us. And where his vision is that to provide the best of the education globally benchmark with the values, sanskars of India, so that every Amitian becomes a global citizen, does not just think for themselves, but the things for the society, things for the, because we always believe Vasudev Kutumbakam, whole world is one family. And therefore the dream of Honorable Chancellor that all Amitian will contribute to the make this world a better place. to live. And I'm very, this year the MRAE has drawn the, as Dr. Sanjay was sharing, that the large, very big response has come this year, the in the form of research papers from the various leading research organizations, academic institutions, and the students, which will be presented across 13 tracks, and those contributions span, in the various disciplines, whether it's fundamental theory or applied engineering or emerging interdisciplinary areas. And I think these papers is the hard work of the researchers, the faculty, the students, and I'm sure these the development, the findings, the research will be presented. It will give great learning to all the participants who are here, and that will also help all the students, especially the pre-final and final year, what kind of the career opportunities are going to be for them, and how they need to prepare themselves, what kind of skills and competencies they need to develop so that they are ready for the employability. And employability does not mean the placement. Employability means even starting your own venture. Or even if you're going for your higher education or going back to your family business, in case anyone, and having the right kind of skills and competencies in every profession are very important. And in the last few years, we have seen that first astronaut who went to the space, Rakesh Sharma ji, in 1984, something like that. And there are then the recent one who has been recently met the Honorable Prime Minister, also the Subhan Shukla, and whose story have been, I'm sure motivating all of you, everyone, every Indian. And I think that that's the kind of the career opportunities are there. And it's only that what kind of a dedication, what kind of commitment, what kind of the hard work, what kind of passion you have. So there's so much is there in this space, and I'm sure the learned speakers who are sitting on the stage and subsequently, so you are going to have a great deal of learning today. And the kind of the achievement we have seen, and these recent triumphs built on the proud legacy. In 2014, the Mars orbital mission, Mangalyaan made India the first Asian nation to reach the Mars and the first in the world to succeed on its maiden attempt. More recently, Chandrayaan 3 made history by landing successfully near the moon South Pole, while Aditya L1, India's first solar observatory, now studies our stars from space. Together, these missions showcase how India is rapidly becoming a leader in global space exploration. I'm sure Dr. Ramotiji is going to share more in this, because he, after every, whether it's Chandrayaan, Aditya L1, and we have always seen Sulamurthy on one TV channel or other TV channel, and giving his analysis, and how the Indian scientists and researchers are working in this field. And I'm really happy, and I want that to congratulate that how our aerospace engineering students are contributing in this momentum through their publication. Dr. Sanjay has already shared, and very high quality publications with the students publish. And I think the National Education Policy 2020, which is focusing a lot on research, though it is for the BA, BSc, that kind of program. But I think Dr. Sanjay has really, really taken that National Education Policy 2020 to his heart, and very passionate that how every student from aerospace engineering, um, publishes the paper, because it has a lot of benefit. If you are going for higher education, admissions will be greatly helped. And if you are really having the good research mindset, good track of publications, what the Dr. Sanjay has shared, that getting the admission in the prestigious institutions with scholarship, with fellowship, that becomes much easier, because they will always look at that what kind of the students are there. So therefore, I would like to once again congratulate all the participants from various institutions who have come here to present their research papers. And I'm sure this conference is not going to be just for discussion, but it's going to give a lot of opportunity for the interaction, networking, and collaborations. And I'm sure that all the participants, the researchers who have come from the other institution, they will find the collaborators here. And then the next conference, when we meet again, I'm sure there will be a lot of collaborative research. With this, once again, I extend very warm welcome and congratulate Dr. Sanjay Singh and his entire team of Aerospace Engineering Institution for putting up such a wonderful conference. So wish you all the best. Thank you.
Thank you, ma'am, for your inspiring words. Audience, as you all know, our Vice Chancellor, Professor Dr. Balwinder Shukla, ma'am, is a visionary academician known for her expertise in academia, research, and administration. With over 3 decades of experience in industry, academia, research, and administration, she holds an MTech from IIT Kharagpur and a PhD from Queen's University, UK. Thank you, ma'am, for gracing this occasion.
Ma'am, we kindly request you to grace the occasion as it is time to release the souvenir for this conference. We humbly request our dignitaries to do the honors. I also request Dr. R.K. Saluja sir and Dr. Neeraj Kumar sir, along with Mrs. Bhavya Saxena and Lisa Francis, to accompany the release of the conference souvenir. I would like to request the audience to join their hands as we release the conference souvenir.
Thank you, dignitaries. It is with great pleasure that we would like to welcome Dr. W. Selvamurthy sir, who is an eminent personality in biomedical research with over 4 decades of expertise. He holds a master's in human physiology from Christian Medical College, Vellore, a PhD from Delhi University, and a DSc from Bangalore. His 40-year tenure at the Defense Research and Development Organization saw significant contributions in nanotechnology, yoga, military, psychology, and polar physiology research, benefiting the armed forces in challenging environments. Currently, Dr. Selvamurthy sir occupies key positions at Amity University, serving as President of Amity Science, Technology and Innovation Foundation, Director General of Amity Directorate of Science and Innovation, and Chancellor of Amity University, Chhattisgarh. He has also chaired influential committees, including the National Advisory Committee for Scientific Social Responsibility.
With an H index of 39, he has authored more than 250 research papers and 18 books. His outstanding contributions have earned him prestigious awards, including the Dr. APJ Abdul Kalam Award and Distinguished Science Leadership Excellence Award. Dr. Salvamurthy's dedication to advancing biomedical sciences is evident through his global representation at forums like the World Health Assembly and the Organization for Prohibition of Chemical Weapons. His legacy is one of remarkable leadership and groundbreaking contributions. Ladies and gentlemen, let us warmly welcome the distinguished Dr. W. Salvamurthy, sir. Sir, please.
So, good morning, friends. So, my dear students, it's always a pleasure to be with my students, particularly from aerospace. They keep coming to my cabin more often. Sanjay keeps sending them. They bring all research, innovation. I see some of the faces, very familiar spaces. And also, I visit their club, research club, and they have a research magazine they are bringing on. It's a small research magazine which next issue I'm going to contribute. I said, why don't you do it in challenges and opportunities and defense aerospace? So I have given them a task also. So let's give a big clap to our own students. You are doing a great job. And even in this organizing this event, they have played a pivotal role. And Sanjay Singh have been guiding, motivating, leading, along with their very brilliant faculties. So I'm so thrilled, excited to be with you all, particularly the students. Honorable Founder President, Dr. Ashok Chauhan ji, now for him, research and innovation is his life, breath. So he has created, I want to tell our guests, now today we have created a Amity Universe, Dr. Ashok Chauhan, the Founder President, with 13 universities in India, 18 campuses abroad, 28 schools, 250,000 students, including them, and also 10,000 faculties, 5,000 PhD scholars. So it's a very vibrant research and innovation driven campus, led and also founded by Dr. Ashok Chauhan. Let's give a big clap to our founder president, who also finds time to watch all this program. As I have been to his office, there are 6 monitors, 3 this side, 3 this side. And then he keeps watching every program, what is happening, and he addresses some of these programs as well. So you have such a great leader who has envisioned in 90s, late 90s, India will become a developed nation, will become a superpower. That when he came back from Germany after 28 years, that he envisioned, and he thought we can do it through your students, our students, faculties, research scholars, and with the blessing, support, guidance from all the institutions and experts from outside Amity. So this is how Amity has filed 2,600 patents. We have published 45,000 research papers. Our H index of Amity University is 189. So this is growing. This is a very vibrant campus. So after 40 years in DRDO, it's an exciting place where I have been able to make a small contribution in research and innovation, which I see an exponential growth in terms of projects, patents, publications, PhDs, and also the consultancies, extension activities, number of activities which have happened, which is happening. So I'm so happy to be here. Also at the inaugural session of your 3rd edition of the aviation conference, which you are organizing, aerospace conference. And I welcome each and every one of you. And your chancellor, Dr. Atul Chauhan, he has sent his greetings. He is actually abroad now. He is in United Arab Emirates. And so he keeps traveling, hopping from one country to the other and one meeting to the other. And he has sent his greetings. He is also, he holds both engineering and as well as the management degrees from University College of London as well as the London School of Economics. So this is led by such great people, the Amity Group. That is how it is growing so fast. Now coming to this, we have a very distinguished guest, Group Captain GBG Ugandar. I was just having a chat with him because, I closely work with Air Force. when I was in DRDO, we have many programs where I have closely worked with the people in the uniform, particularly the Air Force, Army, Navy, and also paramilitary, as well as all security personnel for technologies and related issues. So he hails from that organization in Op Sindhu. It was the aerospace, the airspace defense. That was demolished in Pakistan. And our Air Force played a pivotal role in this operation. Let's give a big clap to all the Air Force officers who are here, who are in Amity University. We have also Air Vice Marshals and also we have Air Commodores and Group Captains. So we also have people in uniform from Air Force. So we are very proud about it, and we are privileged to have today Group Captain GBG Yugandhar, who is the Director General of a very important responsibility, Aircraft Accidents Investigation Bureau, AAIB. So he is the Director General, which is a very important. The recent incidents, the recent accident which had in Ahmedabad, the Air India flight. So this is a big. Now they are doing the investigation. Like this, they do a lot of investigation. So when I was chatting with Group Captain Yugandhar, I was telling Amity University should participate in their mission in accident analysis. There are a lot of database available today, hundreds, thousands of the data sets available to see the patterns. Some of them could be related to human factors. Some of them could be a technical failure. Some of them could be due to bird hits. So like that, there are many, many factors which are responsible for air accidents. So I said, Amity should also contribute. We have a big data analytics center. We have a very strong the artificial intelligence center with 10 petaflop computing capability. We have brilliant faculties and scientists in Amity Institute of Aerospace Engineering, Amity Institute of Defense Technology, where there is a aerospace vertical, and we also have Amity Institute of Space Science and Technology. So all of us, we would like to contribute to your mission. So welcome to Group Captain GBG Yugandhar, the Director General of the Aircraft Accidents Investigation Agency. Now we also have the guest of honor, the Group Captain Sanjay Kumar Singh. He is the director. Working with him, he is also Group Captain. So the Group Captain is very strong position in the Air Force. So we are privileged to have two Group Captains sitting on the dais, and he is ably guiding, supporting as director, executing all the vision of our the Director General here, who is sitting here. So welcome to Group Captain Sanjay Kumar Singh. Let's give a big clap to Group Captain Sanjay Kumar Singh as well as our Professor Sanjay Singh, the leader in the Amity Institute of Aerospace Engineering as director. You know, he is very dynamic. He is very cool-hearted, and also he handles problems very, very sensitively, delicately, and leads this group of faculties of Amity Institute of Aerospace Engineering, which was one of the topmost institutions which was established. Today we have more than 200 to 300 students in this Amity Institute of Aerospace Engineering, and he is spearheading as a good leader. Let's clap for Sanjay Singh for this wonderful. The theme which we have chosen for this third edition of this aerospace conference is very, very important. Now we are looking at what should be the new trajectories promoting innovation and research in aerospace engineering. That's the theme in which we are going to deliberate and look at what are the trajectory in which our students, faculties, country should focus in the aerospace engineering domain. My association started with the aerospace engineering in DRDO, way ahead 40 years before. And we developed a light combat aircraft. You are all aware, light combat aircraft, Tejas, which is the 4th plus generation fighter aircraft today, which has a digital cockpit, fly-by-wire, and modern avionics, the radars, weaponized. So you have the best 4th plus generation fighter aircraft today in India. We have developed indigenously, except the engine, which is still a problem. We are importing from G414. We are importing, but in that My contribution, our contribution from the psychology, physiology side was ergonomics. How do you design the cockpit to Indian pilots? Because they vary in anthropometric dimensions, physiology, psychology. So how do you build a system, calculating the mental workload? Where do you place the displays, which it will register? The pilot will be able to register. So the whole ergonomic design of the cockpit was done by our institute, the Defense Institute of Physiology and Allied Sciences, and also Defense Institute of Psychological Research. So when I was in DRU, my journey with aerospace engineering started with that. But then we did many more things. Like when you select a pilot, how do you select a pilot? Everybody cannot fly a fighter aircraft, which flies at supersonic speed. So how do you, because you have very less reaction time. So how do you assess the aptitude of a person for flying a fighter aircraft? So we have the computerized pilot selection system, which is being used by the Air Force today at their Air Force Selection Board at Dehradun, Varanasi, Mysore. In this, our selection system is being utilized there. So there again, my signature is there. Then the other important thing which we did for Air Force in aerospace engineering was onboard oxygen generation system. See, when the fighter aircraft flies, you can do mid-air fueling. Suppose you want to do an intercontinental flight of the fighter aircraft, you can do the mid-air fueling can be done. So in that, you have increased the endurance of the aircraft. But how do you increase the endurance of the pilot who is flying at that altitude, maybe 35,000 feet or 40,000 feet or above? So you have to give oxygen. You cannot carry so many cylinders of oxygen for that duration. So we have to generate oxygen while it is flying. Because the air has oxygen and nitrogen. So we developed a system where sieve out the nitrogen, concentrate the oxygen, and keep giving it to the pilot. So this is on-board oxygen generation system, which is being used now in the Air Force. So this is yet another important contribution. Then we did many things: anti-G suit, airborne early warning and control system, ABACS. Then we developed an engine which has now matured enough. Kaveri engine today is able to develop more than 75 kilonewton thrust, which is very important because for aerospace you need the heart of the engine. Heart of the aircraft is engine. So that is where we have to, all of you, this is a challenge for students, faculties. Please start thinking, how do we make a aero engine, which is a complex problem. And today only 3-4 countries have monopolized the development of the turbo and the aerospace, the aircraft engineering, particularly the fighter aircraft, which has to fly at supersonic, or now we are looking at hypersonic propulsion. So you are going to deliberate on the hypersonic propulsion as well. So let us also look at development of aero engineering is a challenge for you. Now we are also looking at 5th generation fighter aircraft, from 4th generation, 5th generation. We are looking at advanced medium combat aircraft, which has stealth capability. So that all this you can work. How do you design a stealth aircraft? Even in terms of structures, aerodynamics, all this is a very big challenges for all of you, the students. So there is an exciting area. That's what you are going to deliberate. I'm sure you will arrive at converge into certain domains in which Amity should launch programs in this aerospace engineering. Then I was also associated when Dr. Kalam was the chairman of the COFA committee. When we had accidents, there is an accident committee, COFA committee, where a lot of accidents were happening. Bird hit and machine failure, technical failure, human failure. So all this, the COPA committee was looking at in a very concerted way. We made recommendations. I was a part of that committee with Dr. Kalam. So where accident investigations were done, so we categorize how do we predict, how do we prevent these accidents. So that is where now I was suggesting to DG that Amity will be able to contribute for this, looking at the modeling of the patterns of accidents which have happened over a period of time through retrospective analysis of the data which they have. So now coming to Amity Institute of Aerospace Engineering, not only we are producing human resource, more than every year about 200, 300 students, only in the aerospace. Then we have defense technology, aerospace. We have also in Amity Institute of Space Science and Technology, they have the space system. So all this is, we are producing almost 600 students every year. That's a big effort from Amity University, Amity Institute of aerospace engineering in particular. And they're also doing research, particularly students. The Sanal Kumar, who is sitting there, now he has developed his own Sanal Kumar effect of the flow, the air flow, and also the dynamics of the hemodynamic flow as well. He correlates with that. And so he is doing a great research with his students. And let's also clap for Sanal Kumar, who is a brilliant scientist who came from ISRO. And he is also spearheading along with Dr. Sanjay Singh's leadership. He is able to propel. Now, coming to we are working on propulsion, aerodynamics, drones. We have a drone center. Drones are becoming very important in aerospace. So we are also not only aircraft, helicopters, the fixed wing as well as rotary wing, but we are also looking at drones. So Amity has got a drone center, and which is closely working with the AI center. AI-based accident analysis, I have mentioned. Amity Space Mission, Dr. Ashok Chauhan, the founder president, has promulgated a big mission, Amity Space Mission, where we are looking at the health of the spacecraft as it flies through the AI, artificial intelligence. We are looking at the health monitoring of the spacecraft in flight. We are looking at the debris management, 40,000 debris floating around in low Earth orbit. So Amity Institute of Space Science and Technology is doing research on debris management. So like this, a lot of exciting things happening in Amity University in this area. Now the final carry-home message, that the frontiers of aerospace research is very open with artificial intelligence, quantum technologies, quantum communication, quantum computing, cyber security going to play a very important role. So you don't have only barriers that only aerospace engineers. You have to work with computer engineering for cyber security, because it's all net-centric operations, both in civil as well as in the military. So that's why cyber security plays a very important role. In propulsion, we are talking about hypersonic propulsion. So start working on hypersonic propulsion. Stealth materials. You need different kind of materials to develop the turbo engine or the aerospace engineering. In the aerospace engines, you need a very high temperature tolerant systems. So materials is another challenging area which you can look at. So there is tremendous opportunity. So for the Viksit Bharat, he has added aerospace engineering for Viksit Bharat. Our Honorable Prime Minister has already given the vision for the nation, which is India should become a developed Viksit Bharat by about 2047, when we celebrate 100 years of independence. So if it has to happen, then all of us have to contribute. So this type of conference, we again reinforce our thought, we propel ourselves through our intrinsic motivation to contribute to this Viksit Bharat and connect with people. Don't work in silos. So it is now transdisciplinary, multidisciplinary approach is very vital. So let us all break our barriers and silos, work together as one team, not only within Amity Group, but also outside Amity. So we have a lot of MOUs with DRDO, we have MOU with Navy, we have with Army, the RTRAC, and we also we are going to look at Air Force as another major partner. So let us build connectivity, because Founder President Dr. Chauhan has created 3 important missions which I like. One is Mission Connect, Mission Synergy, and Mission Outcome. So everything what we do should have outcome. So I want to tell Sanjay Singh, that we must look at the outcome from this deliberation. You have organized 3 editions of this conference. What has been the outcome, and what will be the outcome from this conference, which we can carry forward in the form of specific recommendations, which will go into trajectories and the areas in which we have to invest in terms of effort, energy, money, and resources into this area. So please come out with specific recommendation. My best wishes to all of you who are connected with this. I welcome once again our distinguished guest, chief guest, as well as guest of honor, and our brilliant students. Great, you are just great. You are the best.
Thank you, sir, for your enlightening words. It is with great respect and honor that we invite Group Captain GVG Yugandhar sir, who is a serving officer of the Indian Air Force and currently on deputation as Director General Aircraft Accident Investigation Bureau under the Ministry of Civil Aviation. An aircraft maintenance specialist by profession, he has spent his his career finding practical solutions to some of the toughest technical challenges. He has designed innovative repair schemes that has brought back to service aircrafts damaged by natural calamities, corroded during the island operations, or stressed in heavy landings, work that was later published as a training manual. He has also represented India in Russia and the United States during the induction of new aircraft fleets. Over the years, his expertise has guided the evaluation of indigenous aircraft, retrofitment of Western avionics on legacy platforms, and system modifications that improved safety and reliability. His research on life revision studies enabled older fleets to safely serve beyond their assigned operational lives.
Beyond engineering, he has flown over 1,000 hours as a flight engineer on MI series helicopters. His flying experience spans disaster relief missions, communication duties for state heads, and even peace enforcement operations in Sudan. A passionate advocate of safety, he continues to work on human factors in aircraft maintenance, applying research directly to the field. He holds a MSc in Defense and Strategic Studies from Madras University, an MTech from Punjab University, he's a gold medalist, and a Master of Management Studies from Osmania University. Trained in aircraft accident investigation both in India and abroad, he has led and participated in several high level investigations. Having served as Chief Engineering Officer at a frontline airbase and Director at Air Headquarters twice, he now leads India's civil aviation safety efforts as DG AAIB since 2023.
In 2025, he assumed a pivotal role in leading the investigation into the Air India AI-171 crash, the first fatal accident involving a Boeing 787. As Director General of AAIB, he coordinated a multidisciplinary team with participation from ICAO, NTSB, Boeing, and GE, ensuring international best practices were applied. His emphasis on technical accuracy and transparency, along with the unprecedented security cover extended to him, underscored the sensitivity of the case. The preliminary report issued under his direction identified a sudden loss of engine thrust shortly after takeoff.
We kindly request Sir to give a few words.
Good morning, friends, respected faculty members. First is, I would like to commend MIT University, Dr. Sanjay sir, for organizing an international conference on the most relevant topic on the modern research in aerospace engineering. Before progressing into the interaction, I would like to know how many of you have chosen aerospace engineering as your passion. It's good, very good, because in my few minutes of interaction with you, I would like to talk about the passion, innovation, and hands-on experience. Okay, so most of the studies in India, we have been focusing only on the theoretical part of it, and when the scales are increasing, applying those theory into practice and getting hands-on experience is becoming very difficult. So these are the advantages which the foreign universities get, and I am happy to know that under the guidance of Dr. Selvamurthy sir and Dr. Sanjay Singh sir, you are getting all these three kind of exposures. Okay, so working with the industry, working with some practicing professionals will always give you a lot of advantage. So during my course of these three portions, what I would like to talk about is the passion. Actually, one of our professors, like when we were students like you, he used to talk about the choice of your career. Okay, so everyone, nobody would like to study. Have anybody liked studying in your school? Have anybody liked hardworking? Okay, so I'm just taking it another way. Okay, it's like that X and Y axis. Your professional requirement and personal requirements will be like X and Y axis at 90 degrees apart. Okay, so he used to tell that whatever choice of subject you have taken, you have to start liking it. Now you have taken it. If it is a passion, it is very good. If not, you start liking it. Okay, then the both axes will join together, and you will actually enjoy it as a profession. Otherwise, you find a lot of people stressed out, okay, burnt out. They will 90 degrees to 180 degrees apart. His personal requirements are different and professional requirements are different. Because today's profession requires a continuous learning. You have to learn continuously. You ask your professors who started their career and their engineering with a different kind of engineering branch, and today they have learned the modern technologies and they are teaching you, and they keep studying it regularly. So this lifelong learning becomes easier when you take the subject as your passion. If you have not yet started that, you start doing that. Okay, so here it is always good to study their successful people who have started with their passion. So 2 or 3 small examples I would like to quote, like Ratan Tata. He started his career in different conglomerates of Tata Group, but he had to take sabbatical to look after his mother, and he was in a hospital. But he had a lot of passion towards the automobile engineering. Okay, so present Tata Motors used to be called as Telco. Okay, he never know that he will be coming back and joining with Tata's again. So during that time, he designed Tata Sierra. Okay, so while he was in the hospital, and then later with a bigger aim, that Telco has been renamed as Tata Motors. Okay, and when Tata small cars were not doing well, instead of feeling envious about the Mahindras, he told all his designers to learn from the new entrant as a younger sibling, and now Tata Motors is doing extremely well. Okay, so this is how the passion works. Like JRD Tata, everybody knows him as a businessman, but he holds a civil pilot license. Okay, so many people like that. There are so many engineers who migrate into macroeconomics. Okay, so you can read many of these people and you can actually apply it to your personal life so that the passion can be generated. Once a passion is there about your subject, then you are not burnt out. So today we like the subject, we continuously study them, and we never feel, at least on an average we read at least 500 pages a day. Okay, and we apply. It's not that 500 pages is not an academic education, they are all applications. Okay, so this is how we enjoy reading and studying once you develop your passion. Upgradation of skills. Today you will become irrelevant if you think that whatever you have learned today in the college and you want to apply in your career, you will be left over somewhere. You have to continuously upgrade your skills. Like what sir is talking about, artificial intelligence lab which we have. So now it is interdisciplinary. You have to collaborate with everybody. Unless you collaborate, your own single knowledge is not sufficient to grow higher and to contribute to the system or to the nation. Okay. Next is change management. It is a self-explanatory thing. Like I would like to quote the example of the internal combustion engines to electrical vehicles. So many of us have studied the internal combustion engines, and the same generation engineers with engineers like you, they are working in the R&D of the new automobiles. So now they are migrating to electrical vehicles. So these are all possible if those people have got the passion and also about the upgrading of the skills to the newer technologies. Next, I would like to again ask some questions so that you are all flowing with me. Okay, so how many of you have qualified in GATE? Okay, okay, few of you. And how many of you are aiming to qualify in GATE? That's really good. Okay, this is one opportunity where you can prove your capability as an engineer, whether you study your MTech or not study MTech. So from the beginning itself, you have to concentrate on the core subjects. The basic problem what is happening is, many of the people know that the IT is one area where there are a lot of opportunities. They started leaving their core subjects. And today there is a great opportunity for the core subjects, whether it is chip design, okay, or when it comes to the innovative methods of mobilities, all these things require core engineering branches. And similarly, we have the carbon neutral energy development. all these areas require your engineering, core engineering background. Now, when it comes to the avionics and aviation ecosystem, the aviation industry is very highly matured industry. Whatever the Western countries have developed, they have developed over a period of last 4 or 5 decades. They have learned from their errors, which they have learned during their First World War and Second World War. Today, leapfrogging into the technology straight away is not possible. Okay, I am not pessimistic about it, but we have to see what are all our strengths, especially when it comes to the researchers of India. We are very hardworking and we have got the core maths and science knowledge with us. Okay, so where we have to pitch in so that we can contribute to the global good. Okay, so today many of our professionals, they are working towards the global good, whether it goes to the Microsoft or Google or any other bigger industries. So now the design, development and series production of aircraft is a very long gestation period, requires long gestation period. Dr. Salamurthy sir was for it. When we joined in Air Force in 94-95, we were told that by 2000 the LCA is going to fly. Okay, so today we are still doing the baby steps in our LCA. So that is why only the governments can fund such type of projects. Why I am telling these points is I will bring to those areas where you have got the opportunities for research and growth. And similarly, the product, after putting so many years of research and development, when the outcome comes, there may not be market for it. There may not be market. And today the government is buying. So now if you don't have any world market, bigger conglomerates can't sustain. So that's where we have to see those areas. With my experience in the aviation ecosystem, looking at the global market and the Indian market and capability strengths of our Indian students and the research institutes, I found out few of the areas. The first area I would like to talk about is the materials. Sir has already talked about it. Materials, when it comes to engine, we may not be able to crack immediately. But when it comes to the materials for structures, we will be able to develop. So materials, now entire world is developing these materials. So we can actually jump into the league. So now the materials which are used for the structures, earlier we used to have metallic structures. So now we have 80% of this is composite only. It is not only for manufacturing, these materials are required for repairs. Any aircraft which is down, whether it is bird hit or anything, small repairs, on the composites repairs is a very tough task. They can't do it instantly. For metals, the repairs must be much easier. We used to do a lot of riveting, lot of supersonic kind of welding, all those things we used to do. So today we can't do that kind of thing. Now there is a great scope for Indian students and Indian Research Institute for development of materials. If we can start with the materials required for the structures, we can further progress into the engines. Okay, so materials not only for manufacture but also for your repairs of the structures. This is one area which I can straight away tell you where there is no entry barrier. Okay, if you want to manufacture an aircraft or manufacture an engine, there is a big entry barrier because of the reliability requirements and also your reputation, which we have done over a period of last 40-50 years, which we don't have. Next, come to the avionics and integration. Avionics and integration, with your kind of knowledge and the kind of faculty which we have available within India, we will be able to integrate these avionics which are available outside. Okay, which we have done in many of our legacy fleets. When we had to continue with the legacy fleet, because the Indian government doesn't have any kind of unlimited budgets. If you are given some 2 or 3% of our GDP for the entire defense, we have to maintain those fleets over a period of a longer time. But still we have to fight the new generation aircraft. Okay, so that is how what we have done was we have integrated the modern avionics. Aircraft doesn't change much. Aircraft has to fly at a particular speed. Aircraft has to have the countermeasures, electronic countermeasures. Okay, so all these things comes under the avionic group only. Okay, so these countermeasures, and then you have to have countermeasures. So these equipment we can procure, we can develop, and we can integrate into our existing systems. So this is one area where the Indian scientists and the students have got great capability. Okay, so I will also guide you how and where you will get this kind of detailed information from the government of India, where you can straight away go and contribute. Next, come to the fuel cells. So today the aircraft are flying with fossil fuels, and over a period of another 3 or 4 decades, we have to go carbon neutral. And these fuel cells we can leapfrog straight away. We are at the same platform, whether it is the US or India, all of us can develop these fuel cells. I am not only limiting itself to the electrical based fuel cells. You have multiple varieties of fuel cells. Okay, so the fuel cells is not any chemical engineers domain today. If it is to be employed in your aircraft, lot of your research is required. It is going to be multidisciplinary. Electrical engineers, chemical engineers, structural engineers, aeronautical engineers, everybody have to work together. So fuel cells is one area where India can contribute a lot. Next is the avionics calibration. Today, India is doing only 2 to 3% of the entire MRO business. It is estimated to be more than 3 billion, and we have an opportunity like what we had in 1990s for the information technology. In this next decade, this MRO industry is going to have a great opportunity. So today we are doing a business of only 2% in the entire globe. So we have opportunity of another 98%. Even if you can't go up to that 98%, we can go up to at least 40-50% of the market, because our engineers are good, they are disciplined, knowledgeable, and we are rule bound, because we don't do any stealing of technology. Okay, so we learn from all other countries. Okay, so sir would have gone to many other countries, and we have seen many other technologies, but we collaborate with them, but we never steal the technology which the entire globe realizes, and they cooperate with us. So in MRO, we are encouraged by the foreign players, the OEM, original equipment manufacturers. So you have to aim towards this MRO industry also. Next is maintainability of the equipment. So many of the Western countries, they have a concept of use and throw. But how many of us are using our cars for more than 15 years? Just because the government is asking us to throw the vehicle, but otherwise we are using beyond that. And we are flying the aircraft for more than 40 years. The life revision studies with DRDO, what we have done with Air Force, we have flown for more than 50 years. Tomorrow, sir is going to the closing ceremony of MiG-21. MiG-21, which the Russians have developed, and today they are not flying. They are surprised to see the aircraft is being flown by Indian Air Force. Okay, so we are good at maintaining the equipment. So the maintainability studies. So the equipment which is available in the global market, we can take up the maintainability studies. We can go to the OEMs and we can take up the maintainability studies and give solutions for them. So this is how the cost of maintenance of the aircraft can be reduced. And today the entire aviation industry, especially the commercial aviation industry, is totally competitive is one, and every penny counts. Okay, so how many of the airlines can buy an aircraft and operate it commercially? It is totally not possible. If we have to buy one aircraft, say for example 200-300 crore, and you have to buy a fleet of about 10 to 15 aircraft and operate it, no airliner can maintain it. So most of the airlines, okay, they go with leasing model. Leasing model is where we have got great opportunity to contribute. There are certain areas, some 2 or 3 of them I will quote them. When it comes to leasing of the aircraft and engines, okay, so how the productivity can be improved, that is reducing the downtime for maintenance. All these areas you have the scope to innovate. Then coming to training, training of pilots, training of engineers, training of technicians, it is a very huge market. Indians are very good at this. We have very good faculty, and all of you can grow as a good trainers, because training cost and training, that is the faculty cost in foreign countries, is much higher. At the cost of fraction of the cost, we have the faculty working here with us. fraction of the cost the engineers are working here. Okay, so now the training is a great opportunity where you all can get into. There are certain non-revenue flyings. When it comes to defect, once the aircraft has got certain defect and it is rectified, it has to go for certain test flying. So these test flyings also can be reduced by doing a lot of research. So many of the things have been reduced, but you can further work on those areas. We have something called as follow-on support. As I said, you understand what is outsourcing, no? Outsourcing. Okay. So the original equipment manufacturers, whether it is Boeing or Airbus, they don't go and give that kind of servicing. Like if you have Maruti servicing center at every corner of the town. Okay, the same way they can't have. Okay, so they have got some field service representatives, logistic service representatives. Okay, this is one area where they don't feel that you are a threat to them. Okay, so these are the areas where your generation can participate and work with those OEMs. So now as a researcher, you must be proficient with the dynamics of the costing. As I said, if it is not economical to implement your technology, whatever you have developed, it will not find place in the market. So now you will have to understand what is the dynamic of the costing. So I also suggest the university to conduct the viable, practical and globally compatible research. And today aviation is not any region bound technology. It has to be compatible globally. Whatever you develop, it has to be compatible with the global technologies. And finally, I would like to ask one more question. How many of you have seen, if you have not read, Flying Without Formula? Have you? Yeah. So who is the author? Okay, A.C. Kermode is the author. Sir, I suggest this book be bought and kept in your library in multiple copies. Okay, we are also, when we join our Air Force, we are also not exposed to flying, you know. So these Kermode copies are there everywhere. Okay, so it gives you the bird's eye view without studying any mathematical formulas into it. Okay, how a pilot can read and learn, because a pilot need not be a technician or engineer, but he will understand the dynamics, how the background engines work, how the controls and services work, how the entire controls work. All these things are there in the book. Okay, I suggest most of you, in addition to your academic studies, you also read these kind of books. So now I finally come to a selfish motive of motivating all of you to join Air Force. Air Force is the only organization in entire India which can give you hands-on experience to work on the aircraft. Nobody else will allow you to touch the aircraft and experiment with the aircraft. Okay, so Air Force is the best option to start your career as an engineer, as an aeronautical engineer, because you will be exposed to multiple type of systems over 5-6 generations. So today, even if you have 5th generation aircraft with us, we still fly the 1st generation aircraft where we are upgrading to the 5th generation aircraft. Nobody else has got the bandwidth to spend so much of time and money for that kind of thing. Okay, so Air Force, where we get hands-on experience, where the engineers do the rectifications by themselves, they get exposed to all the DRDO scientists. We are free to go to any of the DRDO labs, collaborate with them and work with them. The confidence which we get when we talk to the OEMs, when we question the OEMs, when we question the design, we get it from our DRDO labs. Okay, so all our DRDO labs, we collaborate, we work with them and we learn a lot from them. Okay, so that is how Air Force will give you the opportunity to grow. Okay, so hands-on experience if people want to have, and we have a beautiful system of short service commission. You work for 10 years, you learn the things and go. Okay, that is one. And now instead of only wearing the uniform, not everybody will get an opportunity because they need monkeys sometimes. Okay, you have to be a good team leader, you have to have certain psychological aspects and all of them. So everybody is good at something. You may not be good to be sometimes Air Force officer. But now Air Force and armed forces, we have something called as IDEX. Okay, you just Google what is IDEX. We have given 41 challenging projects. All of you can partner with us. The industry, institutes, and the students, everybody can participate in the IDEX competition. We have 41 projects in that. You download them and you participate in any of the project. We give you money. We will not question if the project is not successful. That is what the government is doing. Okay, we are jointly collaborating today. Why these tanks and everything has been developed in India? It is because government has said that we will give you the seed money, we will handshake with you, the collaborator, whoever is the technology partner, and we will also give you a market for the next 10 years. That is how Mahindras and Tatas have come to us. And now you can be an industrialist. Okay, like we have so many entrepreneurs who have come and given us drones, armed drones. All these technologies have come from people like you only. Okay, so now you go through the IDEX competitions. Okay, you go through various the armed forces websites. You can take up these projects and you can collaborate with us and you can contribute with us. And today, in fact, because of our lack of time and further programs, I am not able to continue with you for the further proceedings. But I am available anytime, sir. And whatever, sir, is there. Okay, so we will join you, and it is for the good cause of the nation, and we must become Vikasit Bharat by 2047, and you are all the pillars. Okay, so whatever small guidance we can give, we feel it as a privilege to us. Okay, and I wish you all the best. Thank you.
Thank you, sir, for inspiring all of us with your thoughts.
We request Dr. Selvamurthy sir and all the dignitaries to kindly grace the felicitation program. And we request Dr. Selvamurthy sir to kindly felicitate the chief guest, Group Captain GVG Yugandhar sir. Sir, please.
Everyone, please join your hands for the felicitation. Now we request Dr. Sanjay Singh sir to kindly felicitate our guest of honor, Group Captain Sanjay Kumar Singh sir. Now we request Dr. Sanjay Singh sir to kindly felicitate our guest of honor, Group Captain Sanjay Kumar Singh sir. Now we request Dr. Sanjay Singh sir to kindly felicitate Dr. Selvamurthy sir. Audience, please join your hands for the felicitation. Thank you, dignitaries. We request Dr. Rajesh Kumar Saluja sir, the organizing chair of this conference, as he merits significant acknowledgement for his dedicated efforts. Sir, please.
Good morning to one and all. As I am very happy and in this momentous occasion, I would like to read the vote of thanks with immense pleasure and gratitude. Right. So we have a full exciting journey of 2 days waiting us in the heart of aerospace engineering. I extend our sincere gratitude to all those who have given us full support and have made this moment possible. Our honorable founder, President Sir, a visionary in the truest sense, Sir, our deepest thanks for setting us on this path of excellence. Your dreams have paved the way for realization of this conference and made this moment possible. Your guidance continues to inspire us. We are deeply honored to have with us our esteemed chief guest, Group Captain GVG Ugandhar, Director General of AIB, and guest of honor, Group Captain Sanjay Kumar Singh. We add you have added unparalleled prestige to this event, sir. On behalf of this organizing committee, I would also like to extend my thanks to our Honorable Chancellor, Sir Dr. Atul Chauhan, Honorable Vice Chancellor, ma'am, for their constant encouragement and support. I would also like to thank our most honorable Dr. W. Selvamurthy, sir, who is Foundation of Research. And I would like to thank all the contributors, Dr. Sanjay Singh, sir, Dr. Neeraj, all faculty and students, all the IT team and support staff. Thanks to all of you. Without this support, it would have not been possible. Thank you.
Thank you, sir. As we launch this journey into the skies, let our minds be the wings and our dreams be the fuel. In the vast expanse of possibility, may this endeavor rise like a rocket, bold, brilliant, and boundless. With this, we have come to the end of the inauguration ceremony. Now we'll be transitioning into the keynote sessions. Thank you.
पहले मैं यहाँ से स्टार्ट करूंगी, मैं ये करूंगी, तुम ये बोलना, फिर
जो लिखा है वही करना है सिंपल।
हाँ, उसके बाद मैं बनाना है, क्योंकि वो सब कल
ऐसे लीजिए
क्या
मैं बुला बट जो सेंटर हो गया
बस सेकंड
ओके वो नहीं बता दो
फिर सेकंड कीनोट है वो नहीं
ठीक है टेक्निकल सेशन में
टेक्निकल सेशन पे कहाँ पे आने हैं हमें A very good morning to everyone present here in the F-3 seminar hall and joining us online. We welcome to the third International Conference on Modern Research in Aerospace Engineering, organized by the Amity Institute of Aerospace Engineering, Amity University, Noida, Uttar Pradesh. We will begin with two keynote sessions followed by the paper presentation of technical session 1, which is aerodynamics, fluid dynamics, wind tunnel, and computational fluid dynamics.
It is a privilege to have with esteemed dignitaries, learned speakers, and enthusiastic participants, and experts from across the globe. We look forward to an engaging morning of insightful research presentations and technical exchange.
Distinguished guests, esteemed delegates, it is now time to begin with the keynote talk session. We are honored to have two eminent experts who will enlighten us on their visionary perspective.
I please request everyone to kindly maintain the decorum and listen to the talk attentively. Please note that we will be having a quiz session based on every keynote session. The top three winners of the quiz will be awarded with the prizes. The link to the quiz will be shared after the session is over. So,
Our first keynote speaker is Professor Dr. Rajkumar S. Pant from the Department of Aerospace Engineering at the IIT Bombay. Professor Rajkumar S. Pant has bachelor's, master's, and PhD degrees in aerospace engineering. His areas of specialization include aircraft conceptual design, air transportation, and optimization. He has been a member of Faculty of Aerospace Engineering Department at the IIT Bombay since December 1989. He is currently a professor in higher academic grade. Professor Pant is an alumnus of College of Aeronautics, Cranfield University, UK, where he earned his PhD under Commonwealth Scholarship Scheme, and in IIT Madras, where he did his masters in aeronautical engineering. He has also worked for 5 years in Hindustan Aeronautics Limited in the design and engineering department at Kanpur and Nasik divisions. Today, he will speak on hybrid electric multi-lobe airships for cargo transportations. So, ladies and gentlemen, please join me in welcoming Professor Dr. Rajkumar S. Pant to deliver his keynote address.
Very good morning to everyone. Greetings from Nuremberg in Germany. I would like the hosts to confirm to me that my voice is audible and my video is also visible.
Yes, sir, you're
Great.
audible.
Thank you so much. Thank you so much. So I am actually in Germany to present a paper, a keynote speech also related to the same topic, but there is a conference happening on electrical airships, and I'm going to present some studies on the rigid cargo airships that we have done. But today, I want to take the next few minutes to talk to you about hybrid electric multi-lobed airships for cargo transportation. Is it possible for me to share my screen? Because the one that you have is actually a PDF file, whereas I would like to have a PPT. So if you allow me, then I would like to share my screen. Yeah, thank you so much. Okay. Again, just a confirmation that that my screen is visible, and then I can go ahead.
Yes, sir.
Okay. So today we will quickly look at the following important aspects. I'll give you some background about the topic, and then I will talk mainly about single and multi-lobed airships and hybrid airships and hybrid propulsion system. Okay. And in the end, I'll briefly present to you some results that we obtained between conventional. If you look at the lighter than air systems, they are a subfamily of aircraft. Most of us study about heavier than air systems or HTS systems, but today we talk about lighter than air systems. And under that, there is a small category called as the lifting body dynastat, and that is the aim of today's presentation. Okay. Now, you know that the market demand for sustainable aviation is growing because of severe environmental constraints and because of the depletion of fossil resources that we have. So over the years, many companies all over the world are looking at hybrid airships for cargo transportation. By hybrid, I mean that 70% of the lift comes from the lighter than air gas, which gives buoyancy, and the remaining 30% or so comes from the aerodynamic lift based on the forces acting on the body as it moves. So this is the hybrid airship, but we are looking at double hybrid here. We are looking at hybrid airship and also a hybrid propulsion system. In the propulsion system, apart from the conventional IC engines, we are looking at electric motors which derive their power from the solar photovoltaic cells or fuel cells. So this is actually a hybrid. So as you can see, on the left hand side, we have the hybrid airship, which is a multi-lobed envelope, as against a single conventional envelope on the top. On the right hand side, we have the hybrid propulsion system, where you can see that in the conventional propulsion system, you have fuel which is supplied to an internal combustion engine, and then there is a mechanical bus which is connected to the propeller. In hybrid, you have two independent streams, and these streams together are giving the power. One stream is the same as conventional, but the other one could be using photovoltaic cells or fuel cells, and then electric motor which can be driven. There are also many other ways of hybrid, okay, but we'll not go into that detail right now. So these are two examples of multi-lobed airships which have already been developed by companies across the world. On the left hand side, we have the Airlander, the double hull envelope under development in UK, and the right hand side shows the tri-lobed P791 made by Lockheed Martin. But these are essentially called as unconventional airships. Now, what are the merits? Why do we go for multiple lobes? The multiple lobes have advantage of both the worlds. They have aerodynamic lift when they move because of the shape, but they also have buoyant lift because of the volume in which you put the LTA gas. The good part is that their lift can be moderated or modulated by controlling the angle of attack of the flight. Now, since they have a large surface area and a flat surface, that area is good for mounting the solar cells. And also, since the cross-sectional area is less compared to a single envelope of the same volume, you are able to get less resistance to the side wind condition. This is one of the big problems with airships, that their sideward movement because of the large shape is very detrimental to their operation. Also, if you have a flattish bottom, you can have a air cushion landing system like a hovercraft attached on the bottom. So these are some of the merits of multi-lobed airships, because of which they are being developed all over the world, and they are very popular. Now, one of the standard envelope shapes which was developed in Germany in the University of Stuttgart was the Lotte airship envelope. Lotte was the world's first solar powered airship developed by young students in University of Stuttgart in the year 2002. Now, we have looked at a tri-lobed version of the same envelope, and we have first carried out some studies to validate our tools. So on the left hand side, you see the validation of the lift coefficient with angle of attack, which all students know is supposed to be linear. So the red triangles on the left hand side indicate the experiment by Funk et al. In 2003 on the Lotte airship envelope, and the black dots that you see are the results obtained by us. Okay. On the right hand side, we have the drag coefficient versus the angle of attack. And here we see that, as expected, the CFD code that we have used matches the trend, but it generally over predicts the drag coefficient. This is something which is very well established. Okay. Now, if you look at the multi-lobed envelope, okay, and the single-lobed envelope, we notice very interesting thing. If you look at the conventional envelope on the left hand side, if you look at the red line, that is for the conventional single-lobed airship. But see how much there is a change in the lift coefficient versus alpha for the tri-lobed envelope. So we see that the slope of the curve is also increasing. Okay, we see that the slope is increasing. So this is the advantage of a multi-lobed envelope. But along with the advantage, we also have some disadvantages, and that you can see on the right hand side. The drag coefficient of a multi-lobed envelope is higher. So we see that whereas the drag coefficient for the single-lobed envelope or the conventional envelope in the red line on the right hand side is very slightly increasing from -2 to +10 degrees, but the increase is much sharp, and also the values are much higher, about 50% higher for the tri-lobed envelope. So what you gain in terms of lift in some ways gets cancelled in terms of the increase in the drag. But as aerospace engineers know, the most important aspect is the L by D, or the aerodynamic efficiency. Now we noticed here that in the range of 4 degrees to 10 degrees angle of attack, which is probably the angle in which the aircraft will normally fly, we noticed that there is a huge improvement in the L by D. Okay, the L by D values are greatly improved. In the conventional airship, the L by D goes up to about 1, whereas it is nearly 2 for the tri-load envelope. So the CD changes by 50%, the slope improves, but L by D becomes almost doubled. So one of my PhD students has developed a sizing methodology for multi-lobe airships, which has these 5 important elements: the energy calculation, the mass breakdown, the geometry, the environment, and the aerodynamics. And when we look at hybrid airship, there are methodologies available either in the textbook like Nicolai and Carrickner or in other sources. So this is what we have adopted in our calculations. Now we come to the second aspect of hybrid, which is propulsion system. In the propulsion system also we have gone for a hybrid configuration. As I mentioned to you last time, we have a hydrocarbon fueled IC engine and electric motor both, and we have solar arrays mounted on top of the envelope because of its flat surface with the fuel cells. Now these are better than battery because they give you higher specific energy, and also it allows you to charge it more often. The operating altitude that is chosen is to suit the IC engine, because for the battery and electric motors, altitude does not make any great difference, except the solar arrays will get better radiation when you go to slightly higher altitude, especially above the clouds. So now I want to just quickly show you a glimpse of the results. I have skipped because of the because we started late and because I wanted to avoid too much detail. I have deleted some slides, and I'll talk to you only about the conventional and tri-load airship. So hybrid airships, they have a lower payload value. Okay, we see that the operating empty weight is higher because they have more systems. In this case, we have fixed a buoyancy ratio of 0.75. That means the buoyant lift is 75% of the total lift. Now, if you notice, the mission fuel consumption is about 14% lower in the case of the hybrid airships, but there is also a 15% reduction in the payload, primarily because the operating empty weight is higher. Now, we have kept the same maximum takeoff weight for ensuring a correct comparison. Okay, so therefore there is no percentage difference. So what we save in the mission fuel, we consume in the payload. Okay, so if we look at the 20 tons of payload, then the takeoff weight goes up by about 3 tons, but the cruising speed increases, and the envelope volume also increases. So now the next study that we are going to do is to vary the values of the buoyancy ratio and the structural mass ratio to see if we can optimize it. So in short, what I want to conclude is that a hybrid airship is going to give you much better aerodynamic lift characteristics, which can be used by you to overcome the problems faced by conventional airships in buoyancy control. You could trade off the lift to control the buoyancy. You may lose little bit of mission, but you also consume less amount of fuel, so they are environmental friendly in nature. So with that, I would like to end my presentation, and I would like to open the floor for a few queries if you may have. Thank you so much.
Thank you, sir. Are there any questions from the audience? Please introduce yourself first and then answer.
I am Shankar Subradas from BTech Aerospace, third year in Amity Institute of Aerospace Engineering. My question for you is, looking towards the future, what advancements in battery technology or lightweight composite materials would you have that would be most crucial for making fully electric large-scale cargo airships into a commercial market?
Okay, that's a fantastic question, because what we have found in our study is that the improvements or the benefits of cargo airships primarily depend on the improvement in the solar efficiency, the electrical power, either through batteries or through solar cells, or reduction in the empty weight using composites. So these two technologies are going to greatly affect the future, and a lot of people are working in these areas to try and take advantage of the airships by reducing the structural weight and increasing the battery efficiency. But battery efficiency is increasing, but we are going to hit a plateau very soon unless there is a complete transformation in the technology. So we are waiting.
Are there any
Thank you
questions?
so much for such a wonderful question.
Any other questions? May we have a huge round of applause for Dr. Thank you, Dr. Pant, for such a visionary and thoughtful.
Thank you, Dr. Sanjay Singh, for inviting me. Despite being in Germany, I am very happy to be able to join in and take part, although virtually. I would have loved to be there in person, but I had already committed to this visit and hence I could not. Thank you so much for having me.
Thank you so much, sir. We now break for high tea, and I request everyone to be seated back at 12:10. Thank you so much.
Bye.
We now transition into the technical session 1, which is on aerodynamics, fluid dynamics, wind tunnel testing, and computational fluid dynamics. It is my honor to introduce our session chair, Dr. Neeraj Kumar, and our session co-chair, Dr. V.R. Sanil Kumar. Dr. Neeraj Kumar is a renowned academician and researcher in aerospace sciences. He is also the director of Amity Institute of Defense Technology at Amity University, Uttar Pradesh.
Dr. V.R. Sanil Kumar is a distinguished academic researcher, former ISRO scientist, and professor at Amity Institute of Aerospace Engineering, Amity University, Uttar Pradesh. We welcome our esteemed chair and co-chair to guide this session. We now begin with paper presentation of technical session 1. I would also like to share that 2 additional sessions are running in parallel. Technical session 2, AI and ML, applications in aerospace engineering in the F1 MDP hall. And technical session 3, space research, rocketry, avionics and instruments in the F-3 MDP. We request the esteemed delegates and participants to engage with the technical session that best aligns with their interests. The total allotted time for paper presentation is 10 minutes. The first bell will ring at 5 minutes, the last one at 8 minutes. We request you to complete your presentation 2 minutes after the last bell rings, after which we will open the floor for question and answer session for another 2 minutes.
So, our first presenter is S.M. Mahadev Hassan, who is from United College of Aviation and who will be speaking on the topic of experimental investigation of turbulence and mean flow in swirling jets.
Thank you. Am I visible and audible clearly?
Yes, sir, you are.
Okay, thank you. Good afternoon, good noon to all of you. This is S.M. Hediasan, lecturer of Aeronautical Engineering Department at United College of Aviation Science and Management. So, on behalf of my team, I am honored to present the experimental investigations and the mean flow swirling jets at the third International Conference on the Modern Research and Aerospace Application Engineering 2025 at Amity University. So let me take you a few years back. My curiosity started at Holter Shagal International Airport, watching a takeoff that looked austere but delivered elegant and also reliable thrust. Later, a simple tap test adding swirl to the water jet showed me how rotating winters that jet boosted the mixing and that leaks a
Excuse me, sir.
Yes, sir.
Can you please adjust your mic? You're not clearly audible.
Dr. Hassan, you are not perfectly audible. Can you adjust your mic, your sound, anything?
Hello. Hello. Hello.
Better you please speak. We can hear you. We can hear you. Kindly start your presentation.
Sorry for interruptions. Okay, let me share this thing. Okay. Is it okay now?
Perfectly fine. Dr. Hassan, you have a 10 minutes time. Kindly finish within the stipulated time. Thank you.
Okay. Yes, thank you. So from that perspective, our research began. Without further delay, let's move into the main sections. So throughout my presentation, I will cover this topic. So actually,
And Dr. Hassan, sorry, can you put your presentation in your slide in the presentation mode?
Yes, it is in presentation mode.
No, it is not there. Full screen, it is there in the. It's okay. Please.
Okay. Actually,
Yeah, fine.
yes, thank you. Actually, jet are provided when a fluid discharge into a surrounding mediums when which may be stationary or actually are moving that unpin any aerospace industrial processes such as fuel ejector, combustion chamber, engine exhausted, and also ignition stabilizer frame. So that's a vital role in the aviation field. So in the velocity field distributions, the circular jet flow are shapes like a top head shapes and uniformly. So the unstable thin shell layers are created in the jet boundary, and also the unstable shell layer, the strong founded turbulence are founded in the rear sections, and that's the downstream of the directions of the with the going in the layer sections. And there are four types of zones are identified with studying the initial zones and finishing the self similarity zone. So for do that we have after the, lots of papers, so number of paper has been reviewed and following findings are actual velocity and potential code that out earlier with the help of swirling jet, and that maximize the velocity point shifted towards the swirling center line in the help of swirling jet, and also with the increase of the swirling piece that mix enhance the mixing property of the airfoil mixer, and that's really increasing the Reynolds number, and with the increasing of the Reynolds number, static pressure also increases. So we found the some three research scopes. With the research scope that is the low swirl angles and the slow with the help of the lower swirl number and the higher swirl Reynolds number. So what's our objectives? Our objective is to carry the competitive study between the features and the swirling jets and their flow patterns and the mixing capability of the airflow mixing with the help of swirling jets. So what we have, how do we have done these methods? So with the help of the with the help of the nozzles, and that is made by the 3D printing with the help of the FDM materials, and we have considered the three types of swirling jets. Five with the installing the three types of angles, 5 degree, 10 degree, and 15 degree, and we observed we calibrated the manometers with the help of the digital multimeters, and the Weiser shapes and manometers are used in these sections, and also 2.75 length jet nozzles are used in this experiment. That is the figure we have seen here. And this is the SolidWorks view we have used, and this is the transverse, horizontal transverse and vertical transverse mechanism we have made in these sections to observe the our mixing property. So what we have found in our experiments. So we separate in our research into three categories with the help of velocity profile, vector profile, and the center line decay analysis. So actually, velocity profile in the free jets that really shows the Reynolds number for the 4 into 10 to the power 4, and the another Reynolds number 1.27 10 to the power 5. So that is the free node with the center line velocity exists up to x by 3 equal to 5, while the center velocity is remaining constant. After that, the velocity is drastically decreasing. And the potential core are finded, and the top head shifts are existed in the sections. But when we add the swirling inside in the field jets, we found that there is no potential core is existed. There is no potential uniform velocity is existed. So they get the center line velocity is faster than the fridges, and we observe that the flow die out earlier, where the previous fridges we found x by d is equal to 10, but here we found that x by d equal to 5. So flow die out earlier with the help of swirling jets, and we gradually increase the degree. We found that distinctly demonstrate the influences of the centrifugal force that flow the field generated by the swirl, and that displays the velocity maximum from the center line in the jet boundary, and that maximize the potential core displayed further from the center line to the Reynolds number increases, and that decrease the velocity maxima and shifted toward the center line with the increase of boundary Reynolds number. And in the 15-degree swirling case, we found that the velocity profile shifted downward and immediately gradually reducing the velocity profiles. So in the vector profiles, we found there is the speed rate of the swirling jet. So how the flow is spreading, and how the flow deviated in the flow with the increase of the shear layer. So here is the velocity profile for the features where the potential core is existed x by d equal to 3.5, and the flow is die out x by d equal to 10. But in the swirling jets, we found that the strong vortices just exist in the boundary line we found, and dimension velocity vector that jet boundary in the sections indicate that.
Dr. Hassan, kindly conclude.
Okay, here is the segment of the 10-degree and 15-degree. We also found the similar patterns, and thus here is the representing the velocity center line velocity is decreasing with the help of increasing the swirling number, while the features are center line velocity is remaining constant up to potential core existed. So that's all the comparison parts, and we have also for our satisfaction our data evaluation we go for the simulation portion, and we found similar patterns in the ideal conditions. So in the conclusion, so we can say that the potential core exists x by d equal to 5.5, 3.5, where swirling jets we cannot found any potential core, and by adding swirling jets, it enhance the mixing property of the airfoil in the combustion chamber, then really enhance the efficiency of the overall engine performance. So it's from, that's the conclusions of our part. Thank you, sir.
All right, so we now open the floor for the questions.
Now, questions is open for the audience.
Please ask questions. I would request audience to please ask questions.
Hassan, I do have a question. Which is the best turbulence model to simulate your experimental findings?
So we have used a K omega SST model to simulate this situations, and we try to maintain the similar boundary conditions in our simulation models.
How much deviations you experienced?
So it's 2 to 5% deviation we have observed, but the profile we have found in our experiments that are quite similar. Sir.
Okay, thank you.
Dr. Hassan, can you put the conclusion slide?
Yes, sir.
You have mentioned 5 points.
Yes.
My question is very simple. Out of these 5, which one is new, which is not known to the scientific community earlier?
Yes, sir. Thank you, sir. We have reviewed a number of papers, but most of the paper we found that they are concerning regarding the high Reynolds number with the high swirling number. So limited work has been done in the low Reynolds number and low swirl number. So we work at the low Reynolds number. That's help us to identify how the flow is deviated, and the flow is mixing with the and that's enhance the mixing property. So that's a new nobility in these sections, and that's deviated the boundary conditions of that existed with the help of high Reynolds number, sir.
Thank you, Dr. Hassan.
Thanks, sir.
Thank you, Mr. Hassan, for your insightful contribution. We appreciate your efforts and research.
Thanks. It's my pleasure.
Thank you, sir. Our next presenter is Priyansh Mohit, who is from Amity Institute of Aerospace Engineering, Amity University, Noida. And the topic is numerical study of an innovative flame holding method in a strut assisted scramjet combustion chamber.
Our distinguished guest, respected professor. Today, I am going to present. Is it visible?
No, sir. Your screen is not visible.
Kindly reshare your screen.
Okay. Okay.
So please click on the share and share the screen. Yes, thank you. Put into the presentation mode.
So can you put it in the presentation mode?
Now it's visible?
Yeah, please put it in the presentation mode.
It is in the presentation mode.
So just click on the slideshow mode and you can start from there.
Can I start?
So we are now presenting your presentation. Just a second. So could you please stop sharing?
Okay.
So your time starts now. You have 10 minutes total. You can start.
Can I start now?
Yes, sir.
Okay. So, good evening, good morning, everyone. Right now, I'm going to present to the numerical study of an innovative flame holding method in a strut-assisted scramjet combustion. So the content will be introduction, objective, methodology, results, and then conclusion. In the introduction section, the key propulsion system for hypersonic aircraft with high thermal efficiency and reduced vehicle weight, which is air breathing, no onboard oxidizing. So the main purpose of this research is combustion challenge, because there is a very small time, that is residual time, that we get inside the combustion for combustion. So here I'm using this novel design to get a better fuel mixing efficiency inside the combustor of a 1000 mm scramjet combustor. So the objective will be to enhance combustion efficiency while minimizing the total pressure loss, and to validate the numerical model through grid independence and result verification. So the methodology that I use is we developed a schematic of stranded combustor with proposed dual rocket strut design. The governing equation that I used is 3D Reynolds Navier-Stokes RANS and numerical solver with CFD simulation that captures soft interaction. So this is the modified DLR stranded combustor that I used for this study, and this is the geometry, novel geometry that I used for this computational fluid dynamics study inside the 300 DLR combustor. This is a modified DLR stranded combustor with length of 32 base height 6.73 and 1 spacing between the two struts. The inlet height of this combustor is 80 wall divergence at 3 and after 80 axial distance. So simulation approach will be axisymmetrical computational domain using 2D CFD simulation flow combustion characteristics. Here the grid generation. Here I showed the grid generation where unstructured quadrilateral mesh that is created by using ANSYS Fluent. So the mesh refinement is the final grid. I used final grid around the strut so that the accuracy will be maintained inside the combustor and from where the H2 is injecting. In the next slide, these are the boundary condition, that initial condition that I use. The H2 which is injecting at Mach 1, the air from inlet is the air that is getting inside the inlet is at Mach 2. Temperature of H2 at 250 and air of 730 Kelvin. So the validation and grid convergence studies. So the soft structure that captured and simulation reproduced experiment, that is H2 injection B, A, B, C, D. These are the studies that we get. So the density controls of traditional DLR stranded combustor. In the A, H2 fuel injection behind the strut base. B is the expansion fan at the strut base. C is the friction of the leading edge soft wedge, and D is the recompression of the soft wedge. And here is the variation of static pressure along the lower wall and the Mach number profile along the center line of the engine for grade 1, 2, 3, 4. So for final mesh selection, grade 2 is selected, which is 4,89,695 cells. For further simulation, that is ensure that mesh independent accuracy. In the result, we get a better mixing combustion link when we use this single wedge strut and when we use dual rocket strut. In the dual rocket strut, the jet vortices contour shows pair of recirculation region around each H2 injection, which is 0.5 in upper and 0.5 in the lower strut in double rocket. So the outcome is dual rocket strut achieves higher recirculation intensity and better mixing and improved combustion efficiency compared to wedge strut. And this is the conclusion that I get. Just behind the strut of the double rocket, we get a better mixing efficiency in the double rocket strut inside a 300 combustor.
Completed?
Yes.
Could you please tell me what is the percentage of pressure loss, total pressure loss you experienced, and how much residence time you altered, and how did you achieve that?
So the residence in this study, I did not get into the residence time, but the pressure loss, when we match the pressure loss with wedge strut, diamond strut, and the lobe strut, we get the next presentation. I will show it to you because I am presenting two paper. This is the first one and the second one when we compared with all this strut design, in which the wedge strut is the lowest pressure loss that I do.
Okay. Questions from audience? Is one or two questions?
It's a good work, Mr. Mohit. My question is, you increase the number of strut.
Yes, sir.
1 to 2.
Yes, sir. It is splitted by 2, sir. 1 mm gap is there between these two struts.
And we increase to 3, and if we increase the 2, 3, will it beneficial, or you will have many losses? Because you have not
Sir,
talked about the losses.
Yes, sir. It will increase the losses, I think, and because it will create more drag and it will create more pressure loss inside the combustor if we keep increasing the number of struts inside the combustor. Okay, so now this is paper number 8, which I am going to present.
So we have actually questions for you from the audience.
So, what is the objective of selecting incoming Mach number as a 1?
Incoming Mach number is 2.
No, you have written 1.
Fuel is injecting at Mach number 1. Hydrogen is injecting at Mach number 1.
See, all the scramjet combustions is entry Mach number is supersonic Mach number. Okay. Another thing is the combustion process is highly unsteady in nature. You have done only 2D simulations.
Yeah.
And the steady state simulations. How we are going to bridge this 2D to 3D?
And that is the thing. The 3D simulation study is right now going on. So, and in the scramjet combustor, inside the scramjet combustor, the combustion happens in supersonic range. So around 2, because the inlet Mach number is 2, and the fuel is that is injecting is injection happening at Mach 1. So this is.
Okay, you have to concentrate on the three-dimensional releasing effect. This is a much more important than they're doing 2D.
Yes, sir. Yes.
Mr. Divyansh, I have a question.
So, if you could please stand up and ask the question.
Can you please show me the introduction slide? The introduction slide.
Okay. Yes. Is it visible?
No. Okay, I will just ask anyways. Like on the introduction slide, I want to just confirm that you have written 92% efficiency. Is it correct?
Yeah.
Like you have achieved 92% of efficiency. So I want to ask, like, what type of validation you have done, like from experimental validation or like how
No,
you
not experimental validation. I did validation from the Overman paper, which they used the DLR combustor, 300 mm DLR combustor they used. So they use different kind of flamelet model. I use some just basic model. It is non-premixed combustion.
So you have used non-premixed combustion.
Yeah.
Okay. So how you have validated your reaction mechanism? Like what type of reaction mechanism you are using?
There is no single step reaction is happening right now in this study. So no basic, no any other flamelet models.
Okay. Thank
you. Just normal simple.
Are there any more questions? Alright, so we have another paper from actually Divyansh Mohit on the topic of comparison of various flame stabilization devices for supersonic ramjet engine performance.
So this is paper number 8.
Yes, sir, you can start.
Is it visible now? Okay.
Yes, sir.
So in this paper, I compared scramjet different strut design for a scramjet combustor for 1000 mm combustor design. So the research gap was lack of systematic comparison of different strut configuration in 1000 mm. So the present study is evaluating mixing and combustion efficiency and pressure loss of wedge, lobe, and diamond strut designs. So in the previous paper that I presented, so the two strut advantage study shows it improves fuel air mixing and flame stabilization. And the present work that in this paper I'm showing that is a systematic comparison of strut design focusing on mixing and combustion efficiency. These are the objectives to analyze different strut design and to evaluate combustion efficiency and flame stabilization. The methodology that I used is RANS. Turbulence model that I use is SSTK omega for better capture of near the wall to accurate prediction, and the boundary condition mesh independent correlation. This is the combustor basic design. It is a single wedge strut design DLR, and these are the strut designs that we use to simulate in this combustor. Now the computational domain is basic, traditional baseline DLR scramjet, and the strut are 3 different struts we use. And unstructured quadrilateral grid is created, generated. The mesh is defined near the strut, combustor walls, and center line to capture the sharp velocity gradient because of the injection of the hydrogen from the center of this strut. These are the variation of cross stream velocity at different stream wise location. For this is the at this first in first graph, it is x is equal to 78 mm in second, x 125 mm, 157 mm, and in the fourth one is 233 mm. And we compared it with CFD overman and the experimental result, which shows almost equal if we compared it with the CFD result and experimental result. A little bit of difference because of this 2D and 3D simulation that I did. The strut design and performance in scramjet combustors are this diamond strut shows the noticeable vorticity but fails to sustain a strong recirculation zone. And in this figure, we can see this the performance parameter. This is the wedge strut, lobe strut, and diamond strut. So combustion efficiency rises downstream of this strut due to progressive hydrogen air mixing, and wedge strut shows highest combustion efficiency, that is 69%. Lobe strut achieves 67% efficiency, slightly lower than wedge, and diamond strut has weakest mixing efficiency because it is not creating enough vortices inside the combustor. So this is the graph of the three struts, which is wedge, lobe, and diamond, and these are the vortices that we get for this 3 strut. In this figure 10, we can clearly see the combustion
Mr.
efficiency.
Mohit, kindly conclude.
Okay. In this figure 10, we can clearly see this. The combustion efficiency of wedge is the highest, and then lobe, and then diamond. And same with this total pressure loss, which is higher in the lobe, and then in wedge, and then diamond. So in the conclusion, we get diamond strut, which has the lowest pressure loss but weak combustion due to poor recirculation. In the lobe strut, we get a strong mixing but penalty of highest pressure loss, and wedge strut best overall performance with highest combustion efficiency for the 1000 mm combustor. This was my study.
Questions from the audience?
So we have questions for you.
Take mic, sir.
If you could please stand up and ask the question. Thank you.
Different combustion. What is that different turbulence model you have used to validate? Because you are telling 69%, 67%, and also.
Yeah.
What is the different? What is the effect of these numbers with the different turbulence model?
I have used K omega SST only for this simulations. So these are the basic. I have not used any flamelet model or reaction. Single step reaction is happening right now in this simulation. Hello. Yes, sir.
So I have a question for you. I want to ask, what is your inlet Mach number? What the
Inlet Mach number is Mach 2.
So you are doing supersonic combustion in that
Yeah.
station. Yeah. So I saw your mesh. Like, are you sure that unstructured mesh is sufficient to calculate the detonation, combustion, and then 67% and 69%?
Yeah,
Can you?
since I'm using the single step reaction, I'm not using flamelet model. So I think it matches with the experimental result and the overman result also. In this here I can show you.
Also, one more thing, you're why I like pointed out the mesh, because even in the contours I cannot see like clear shocks. So you know,
Okay.
due to the
This
mesh,
is
unstructured mesh.
okay. So this is the variation of cross string velocity at different string wise location. So we match with the experiment, overman paper, and then my CFD result. So it validated. Then we proceed with after validation we proceed.
Okay.
Okay. Divyansh, what is your scientific message while doing this comparison study? How can you optimize the device for better performance of the ramjet?
Sir, I want to say that when we simulate with the 300 mm combustor, we generally scaling efficiency. The trade-off is the scaling efficiency because in 300 mm combustor the scale distortion will be there, and mixing and flame stabilization may be not directly translated to full scale results. That's why I use 1000 mm scramjet combustor for simulations.
Okay. Any other questions from the audience? Okay. Next section. Next paper,
Alright,
please.
sir.
Thank you, Mr. Mohit. Your efforts are appreciated.
Thank you.
So I will repeat the rules again. The total allotted time for paper presentation is 10 minutes. The first bell will ring at 5 minutes. The last one at 8 minutes. We request you to complete your presentation 2 minutes after the last bell ring, after which we will open the floor for question and answer session for another 2 minutes. So our next presenter is Farhan Naimuddin Sheikh from Department of Aerospace Engineering, MIT Art Design and Technology University, Pune, India. And he will speak on investigating the impact of sunroof size variation on aeroacoustic performance of an MRAE body using CF.
Good afternoon, everyone. My name is Farhan Sheikh, and I have completed.
You are not visible.
Oh, just a second. Now am I?
Yes, you are.
Okay. So, good afternoon, everyone. My name is Farhan Sheikh, and I have just completed my BTech in Aerospace Engineering from MIT Arts Design and Technology, Pune. So the title of our research is Investigating the Impact of Sunroof Opening Size Variation on Aeroacoustic Performance of an MF Body.
Sir, your slide is not visible actually. Please share the screen.
Is it now?
Yes, please do it in the presentation mode.
Yes.
Yes, now you can start.
Okay, so the title of our research is Investigating the Impact of Sunroof Opening Size Variation on Aeroacoustic Performance of an MF Body using CFD. So these are the content, introduction, objective, methodology, results, and then finally conclusion. So the Ahmed body is a simplified car model used in automotive aerodynamics research to study airflow and aerodynamic forces. You can see how an Ahmed body looks like in figure 1. So when a moving vehicle reaches a certain speed, buffeting is noticeable if the sunroof or window is open. This buffeting, characterized by low frequency, around 20 Hz, and high intensity, over 100 decibels, is quite disturbing and annoying, compromising both the comfort and safety of the vehicle. And this phenomenon is known as Helmholtz resonance. So the scope of the work is that till now there have been no studies specifically examined the impact of sunroof openings on the aeroacoustic parameters of an Ahmed body. There have been some researchers, but they have focused on the aerodynamic and acoustic characteristics of Ahmed bodies and their various modifications, but not the sunroof opening. The unique influence of sunroof size and position on flow-induced noise remains unexplored. So our study aims to address this gap by investigating how varying sunroof size, specifically sunroof size, affects the aeroacoustics inside the cabin. And our objective is to analyze the influence of varying sunroof opening sizes on sound buffeting and the associated aeroacoustic characteristics of an Ahmed body. So this is our research methodology. So for validation, we have used this geometry, and it is basically a semicircular cavity inside a bullet-shaped domain. This was the mesh which we used, and we have used inflation layers near the wall to accurately capture the physics of the flow. This was the surface mesh used by us, and these are the boundary conditions. So the left wall, the curved wall, is our inlet, and this part is our outlet. And the inlet velocity was kept 9.5 meters per second because it was specifically given in our research paper, which we used for validation, reference paper. The outlet was pressure outlet, and the wall of the semicircular cylinder was no slip, and top, bottom, and side wall was free slip, were free slip. And our research is unsteady. Since we are looking into aeroacoustics, we had to use unsteady flow. This is the temporal discretization. So the number of time steps were chosen as 6060. This because even this was specifically given in our reference paper. Time step size was 0.033 seconds. The time step size is very low so that we could capture the flow physics accurately. And max iterations per time step was kept 20. And then we performed grid independence test. So as you can see, after we used fine mesh, the mean CD was almost same. So after very fine mesh, we stopped doing grid independence test, and then we moved on with very fine mesh. So the number of elements were 1,43,000. Sorry, 10,43,091. And the wall Y plus we achieved was 1.26, and the mean coefficient of drag was 1.0535, which matched with our reference paper also. So the blue line is represents our simulation, and the orange line represents our reference paper. So you can see it is quite similar. So our solver was validated. The research paper mean coefficient drag was 1.107, and our simulation mean coefficient of drag was 1.0535. So the error was quite low, which came 4.28%. So so that we could know that the solver which we are using is correct. And this is the velocity contour in our reference paper, and this is the velocity contour which we achieved in our research. This is also quite similar. So coming into our current research, this is the geometry which we used for our Ahmed body, and the sunroof opening sizes were calculated by using Kia Seltos car as a reference car.
Mr. Farhan, can you conclude, please?
Yes, sir. So this was the computational domain, and this was the mesh. So we kept a probe in the center of the cabin, and using a fast Fourier transform, we converted time domain into frequency domain. And these are the different cases. So these were our sunroof opening sizes, 5 cases, and these were the calculated sound pressure level which we achieved from our research. These are the velocity contours. So concluding, velocity vector field analysis showed sunroof aperture changes significantly affect recirculation zone formation, location and intensity, especially influencing shear layer behavior. The highest sound pressure level, which was around 84.63 decibels, occurred at 1.2, our case number 2, which was 1.2 length of the sunroof opening. So findings support the development of passive aerodynamic strategies and active noise control to improve passenger comfort. So yes, thank you. Any questions?
We now open the floor for questions. Questions from the audience?
One or two questions, please.
For validation, you have used 9.5 meter per second, I agree, which is related to around 35 km per hour. But any conventional SUV vehicle will go around 100 km per hour.
Yes, sir.
So have you attempted any, other than this, your 9.5 meter per second, any studies has been done at higher speeds? What is its effect?
Yes, sir. For our current research, we have used 27.78 meters per second, which is around 100 kilometers per hour.
Okay.
This acoustic power level, which model you use? Decibel estimation. What mathematical model you are used?
So we have used SSTK omega.
No, I'm asking about the model, acoustic power model.
Sorry, I didn't get your question.
Okay. Recirculation bubble was increase the acoustic power level or decrease it?
Sir, in different cases, it was different.
Okay. Okay, thank you. Next question.
Thank you, Mr. Sheikh, for your insightful contribution. We appreciate your efforts and research. Thank you.
Yes, thank you so much.
Thank you. Our next presenter is Pokla Himavan from Hindustan Institute of Technology and Science, Chennai. He will be speaking on numerical investigations on film cooling effectiveness of gas turbine blades using forward diffused hold by varying the compound injection
angles. Good morning, everyone. I am R. Shivaranjani, and I'll be presenting the paper today, not my co-author.
Okay, please go ahead.
Is my screen visible?
Yes, ma'am.
Please put it on presentation mode.
Okay. Good afternoon, everyone. So our research is on experimental investigation on flame-based cooling effectiveness for varying compound and injection angles. So gas turbines are widely used in aeronautical industry as well as power generation industry, and they operate in a high and an extreme thermal conditions, and so they intend to have a very high thermal load which often exceeds their material melting point. So film-based cooling system in order to reduce the surface thermal load. So what they do in film-based cooling system is there are holes, cylindrical or laid-back holes on the surface plate, which inject a coolant which has a comparatively lower temperature compared to the main hot stream, so that it is protected. So the previous research, which were all carried out, did not explore the complete range of compound angles. They only explored till 180 degrees. So our research wanted to close this gap and study a complete 0 to 360 degrees of compound angle and found out what is the effectiveness for both cylindrical as well as the laid back holes. So our injection, we kept a constant injection angle of 35 degrees for compound angle of 0 to 360 with a blowing ratio of 0.6 and 1.25, maintaining a consistent density ratio of 1.6 and Reynolds number of 80,000. The model was, this is a geometry. We designed it using SolidWorks based on the dimensions were taken based on our previous literature's review, and keeping the cylindrical hole dimension as 11.1 mm and laid back hole with an extra downstream slope of 15 degrees. For boundary condition, we went with 300 kelvins for the hot mainstream temperature and coolant of 187.5 Kelvin. We calculated it for both the blowing ratio of 0.6 and 1.25. And the mesh we chose was structured hexahedral mesh, with approximately 0.9 million elements, and the turbulence model was KST omega. We also carried out grid independent study in order to verify that the mesh density doesn't affect the performance of our results, and that the mesh density is sufficient enough to give us consistent result. So in the end, we wanted to find out the adiabatic film-based cooling effectiveness and centerline effectiveness of for both the holes in order to compare them under a single category. So these are our results. These are the results for cylindrical hole, the bottom plate effectiveness for the blowing ratio of 0.6. Here we can observe that at blowing ratio 135 degrees and 225 degrees, it shows the highest cooling effectiveness because of their broad and more uniform coolant coverage. Whereas when compared to the other blowing ratios, like compound angle of 45 degrees or 90 degrees, doesn't give that much good amount of results. The surface is deviating. And if you go with blowing ratio of 1.25, due to the increase in velocity difference, we have a jet liftoff. So when compared to 0.6, 1.25 has reduced its cooling effectiveness. This is the adiabatic cooling film system, the cross-section view for both the blowing ratios. So we also wanted to analyze the central effectiveness in order to find out how is the consistency of the cooling, because when you go initially the performance was better, but over the period of time the performance reduced. So when you compare the center line effectiveness, we got a better results for compound angle of 0 degrees for blowing ratio 0.6. But that reduced eventually. So for the when you take 225-degree compound angle, that is more reliable, though the cooling effectiveness is less, but it is consistent. And when you go for the blowing ratio 1.25, 25 degrees, because it has highest effectiveness. And effectiveness of laid back hole. For laid back hole, we can go with either 90 degrees or 275 degrees because they have better coverage in the surface. And for 125 degrees, we can go for both 90 and 275, but it is preferred to go with the blowing ratio of 0.6 because of the jet liftoff, there is a deviation and separation in the flow, which is not preferred for our system. So this is the adiabatic cooling effectiveness. And when we talk about the center line effectiveness of laid back holes, we can see 0 degrees perform better and much effectively for blowing ratio of 0.6, and compound angle 275 degrees perform better for 1.25 because of their wide range. And so we can conclude that if you're going for a cylindrical hole, if our requirement is to have a cylindrical hole, then we can go for 135 degrees compound angle or 225, because 90 degrees and 270 give a lesser performance because of jet liftoff. And if you're going with a laid back hole, you can go with 90 degrees or 275. And the effective blowing ratio would be 0.6, but it again depends on the working conditions. And the overall takeaway would be that the laid back hole performs slightly better than the cylindrical hole because of its forward inclination. And for better cooling attachment and reduced liftoff, and for more uniform thermal protection, we can go with a laid back hole with a blowing ratio of 0.6 with 90 or 275 degrees as the compound angle. That's fine. Thank you.
Thank you. We now open the floor for questions. Anyone from the audience?
Any question? One or two questions, please.
Ma'am, we have question for you.
So it is a good research you have done. So I want to ask the application part, like where we can. Hello. Are you? Am I
Yeah,
audible?
it's audible. Yeah, it's audible.
Yes, yes. So I want to just know the application part, like how.
Okay.
Yes.
Yeah. Like when you go with the turbines of an aircraft engine, so because the working condition are in higher thermal load and higher temperature, you cannot use your blade. You cannot always use a material which is higher than your, like, which has much more melting point compared to your engine temperature. So what we can do is, what we usually do is, we go with the film-based cooling system. We make a hole in the turbine plates and bleed a coolant through that so that it just protects the blade. So it can be used in all aeronautical engines and all power generation turbines, wherever you feel like your material is working under higher thermal load, to just reduce that.
Okay.
Did
Thank
I
you.
answer your question? Yeah.
Yes. Thank you.
Okay, any other question? So according to you, which is the best model, numerical model for predicting this cooling effectiveness?
Yes, sir. As I said in conclusion, we can go with a laid back hole with a compound angle of 275 degrees or 90 degrees with a blowing ratio of 0.6.
So what type of heat transfer model you will invoke?
Sir, I didn't get you. Can you
Heat
repeat?
transfer model, which is the best model for predicting this effectiveness?
KST omega, sir. K omega SST. We went with K other epsilon also, but we found KST omega is better to understand the heat transfer.
Okay, thank you.
Thank you, ma'am, for your insightful contribution. We appreciate your efforts and research. Thank you.
I will repeat the rules again. The total allotted time for paper presentation is 10 minutes. The first bell will ring at 5 minutes, the next one at 8 minutes, and you are requested to complete your presentation 2 minutes after the last bell rings. And then for another 2 minutes, we'll have the question and answer session. Our next presenter is Saqib Reza from Institute of Aerospace Engineering, Amity University. He's a research scholar, and he will be speaking on performance evaluation and comparison of full length and truncated aerospike nozzle using methods of characteristics and simple approximations.
Hello, good afternoon. Good afternoon, everyone. So, my name is Mohammad Saqib Reza, and I'm here to present my research work. And the topic of my research is performance evaluation and comparison of performance evaluation and comparison of aerospike nozzles. Okay, because I have done work for different by using different method of characteristics. That's why. So this is the outline of my presentation. So I'm just starting with the introduction of nozzles. As we know that there are three types of nozzles: converging, diverging, and CD nodules. And our aerospike nodules comes under this CD nodule. So currently, industries are basically using Bell nodule, which comes under the CD nodule. So we can have this prospects like aerospike nodules. There are two designs can be possible. One is that truncated aerospike nodule and full spike nodule. So this is the basics of the aerospike nodule, how it works. Like combustion, combustible gases comes out from the combustion chamber, and expansion occurs around the spike. Okay, so why aerospike nodules? So aerospike nodule basically altitude compensating nodules. Like as we go up, pressure decreases of the atmosphere, but aerospike nodules compensate this effect. So that's why we can use single aerospike nodule for the multi stages instead of multi stages, CD nodule. So this is better than the conventional nodules. Conventional nodule means normal Bell nodules that we are talking about. But the challenges we can face is that weight, because we have a spike, so weight will increase. Thermal failure occurs because spikes facing very high temperature gases. So that's why we need to truncate it. So we are here comparing for two different configurations in which we are generating contour by using the method of characteristics and simple approximation method. So these are the methodology that I have used. Okay, so we can generate this contour by using various different methods apart from method of characteristic and simple approximation method. We have Rouse method, Angelino method, etc. But I have used here only MOC, means method of characteristic and simple approximation method. So by using like MATLAB, we are able to generate the contour of the spike, by using method of characteristic as well as for the simple approximation method. So here are the domain design and boundary conditions for both of them, and these are the mesh geometry. So what we did, like near the surface of the spike, the mesh are very fine, and then the away, like which are very far away from us, that we have used structured one. So simulation, for the simulation we have used this density based solver Sprat-Elmaras turbulence method for the full spike, and the K-epsilon turbulence model for the truncated one. Similarly, other parameters have been applied. Okay, so after generating the contour and then simulation, we need to calculate the thrust. So there are three types of thrust that we can get from the aerospike. First one is that from the expansion of the gases, where the velocity of the flow increases, momentum changes occurs, and we are getting thrust. Another one is that from the spike, and the third one is that if we contour it, if we just truncate it, then we can get the thrust, third component of the thrust from the truncated surfaces. Okay, so validation have been done, and where we have used exit Mach number and the thrust again for the different nodule pressure ratio, and then we compared this thrust like numerically, analytically, and that my result was agreed with the research papers which was earlier published already. So these are the contour Mach number contour for three different altitudes, like for the over expansion, under expansion, and the optimum expansion. This is the for the over, this is optimum, and this is the under expansion. And now the thrust what we have got. So first I have calculated the thrust and exit Mach number at sea level only for different truncations. You can see here that for the full spike like 0, and then 10%, 20%, 30%. So what we see that if we increase the truncation, thrust basically reduces. But after certain numbers, like you see that from 35% onwards, again it is increasing. And we are getting around same value of the thrust what we have got for the full spike at 46%, and then later on it is again decreasing. Similar pattern we have got for the SAM as well, but the thing is that for the method of characteristic, results are better than as compared to simple approximation method. So we have got better result for 46% as compared to other truncations, and it is almost equal to the full spike nodes. So again, what we did, we have done this calculations for three different altitudes, where our nozzle is basically facing over expansion, optimum expansion, and under expansion. So what we see over here is that exit Mach number is basically increasing as we go up, like from over expansion to optimum expansion. But here what you see that for under expansion our nozzle is performing better. Like as compared to if we see that bell nozzles, its performance basically decreases, after optimum expansion. But here we are getting, better result, like almost as like what we got during the optimum expansion. That's why we say that, this aerospike nozzle is altitude compensating. But here as well, that for the method of characteristic, we are getting better result as compared to SAM. Similar result that we are getting 46 for the 46% truncation. Okay, so we can prefer that 46% truncation because here after truncating the nozzle spike part, we are basically reducing the weight. Again, as well that like that thermal stress can be decreased. Like we don't have spike now; it's truncated. So better to use that 46% truncation. Here are the conclusion. So from our result, we get that method of characteristic is giving better performance as compared to simple approximation method. So that's why next to that's why for the generation of the contour, normally we should use method of characteristics. And next, that 46% truncation nozzle is almost giving like performance of full length nozzle. So that's why we should go for the truncated nozzle. Now next is that effective altitude compensation that we have got. Like if we just go up like from the over expansion to optimum, then optimum to like under expansion, our performance is basically getting better. And that's why this aerospike nozzle is basically called as altitude compensation nozzle. So now again question is that why method of characteristic is giving better as compared to simple approximation method? It's like 4 to 5% only, because the shock waves what we are getting after truncation in method of characteristic is diamond shock waves, which is basically because of the expansion and compression waves interacting over there and then making up flow stable. But while in SM, a simple approximation method, recirculation waves forms, which is basically producing losses. So that's why it is having less performance as compared to method of. So method of characteristic is the preferred method for the aerospike nozzle design. What we have basically finalized over here. Thank you.
So we open the floor for the questions. Are there any questions?
Do you have any experimental evidence to support your numerical?
Sir, not yet, sir. It's fully that simulation based. Not yet.
What is your future plan? It's a good work.
Yes, thank you, sir.
So,
any question from the audience?
So you have used the KF silent turbulence model.
Yes.
So have you used other models also and compared it or not?
Splat MRAS. But for the surface based, like we didn't use that another method. KF silent is basically giving best result for the surface based.
Okay.
For supersonic fields. So that's why we have used this one.
And what about the mesh part? Like
base part, like yes, unstructured mesh near the surface, where the mesh number was more than 1 lakhs only. But the away from that, we have used the structured one.
okay, okay, sir. Thank you.
So we have another question.
I just want to know that in your, I guess third last slide or something, you have mentioned that under expansion you are getting higher thrust as compared to the conventional bell nozzle.
Yes.
Can you explain me the physics behind it?
Yeah. That's I said na, like expansion and compression waves that we are getting from the that truncated part. That is basically adding. Okay. And the expansion of flows occurs here. Between two boundaries. One of the boundary is that aerospike surface, and another one is that open to the atmosphere, which doesn't happen in the bell nozzle. In bell nozzle, what happens? The expansion occurs inside the bell. Here it is, happening outside. Okay, so atmosphere basically it is helping with them. So that outer boundary is basically adjusting with the atmosphere. As the pressure goes down, that boundary will increase as well.
As it is expanding outside, it is also very sensitive.
Yeah, but the outer boundary is like atmospheric boundary, na? That's why.
Okay. Thank you.
So the physics is pressure thrust is reducing, so that you will be getting the advantage on momentum thrust.
Yes,
that is the spike nozzle's basic physics. Okay, thank you.
Okay, thank you so much. Thank you so much.
All right. Thank you, sir, for your insightful contribution. Uh, as we draw this session to a close, we extend our heartfelt gratitude to our session chair, Dr. Neeraj Kumar, and our session co-chair, Dr. V.R. Sanil Kumar, for their time, guidance, and thoughtful engagement.
Now may I request Dr. Agneev Roy and Dr. V.R. Sanal Kumar for the facilitation of our session chair as a token of appreciation. Sir, please.
So please center our glass.
May we have a huge round of applause, please? Now I would request Dr. Agneev Roy for the felicitation of our session co-chair. Now I would request the respected session chair and co-chair to present the certificate to Mr. Sakib. Please. A huge round of applause, please. To all presenters and participants, thank you for your enthusiasm and contributions. We now break for lunch. Kindly proceed to the dining area and we look forward to welcoming you back for the afternoon sessions. Thank you so much.
Thank you. A very heartfelt welcome to each and every one of you joining us both in person and virtually for the third international conference on modern research in aerospace engineering, which is proudly organized and hosted by Amity University of Aerospace Engineering, Amity University, Uttar Pradesh. We will kick things off with three compelling keynote sessions by highly competent experts, followed by paper presentations of technical session 4, which will be on the topic aerodynamics, fluid dynamics, wind tunnel, and computational fluid dynamics. We hope you have a good time and enjoy.
It is our utmost privilege and honor to have our esteemed dignitaries, distinguished speakers, and enthusiastic participants from across the globe. We look forward to an engaging series of high quality keynote addresses along with presentation of novel ideas and innovative research papers. We request all of you to listen attentively and participate actively in order to cultivate a deeper understanding of aerospace engineering.
Ladies and gentlemen, it is now time to begin the keynote talk session, which we all have been awaiting with excitement and anticipation. We are privileged to welcome three distinguished thought leaders whose insights will enlighten this hall and ignite the spark for future breakthroughs in aerospace innovation. Let us prepare to be inspired, challenged, and transformed by the knowledge that they bring.
So, our first keynote speaker is Professor Dr. Rakesh Kumar, Professor and Head of Aerospace Engineering Department, Punjab Engineering College, Chandigarh. Dr. Rakesh Kumar is currently working as Professor and heading Aerospace Engineering Department at Punjab Engineering College, PEC, Chandigarh. and is having a teaching experience of more than 25 years. He graduated from PEC and obtained his MTech and PhD degree in aerospace engineering from IIT Kanpur. His specialization is in flight mechanics. His other research interests are aerodynamics, artificial neural networks, AI, and unmanned aerial systems. He has served in Hindustan Aeronautics Limited for 3 years and has supervised production and overhauling of Dornier 228 aircraft. He has published more than 60 papers in reputed journal and conference proceedings. He has presented numerous research papers in reputed national and international conferences in India and abroad, including paper presentation in USA, AIAA, Italy, Dubai, etc. Dr. Rakesh Kumar has completed various DRDO and other sponsored research projects worth crores. He has delivered more than 50 invited talks at various academic institutions. He has won various awards such as Best Project Award, Best Teacher Award, Best Paper Presentation Award, etc. Today, he will speak on integration of computer vision and AI with drone for revolutionary technologies and applications. Ladies and gentlemen, please join me in welcoming the Professor Dr. Rakesh Kumar to deliver his keynote session.
May we have a mighty round of applause, ladies and gentlemen?
Good afternoon. First of all, I thank organizers, especially Dr. Sanjay Singh, for inviting me for the as a keynote speaker. So today my talk will be related to drones, giving it computer vision with the help of AI, and what are the latest technologies in which you can work. I will extend those areas also to you. The talk will be including introduction, classification, some drone examples will be there, drone components, drone with computer vision and AI, and then how AI I had applied with methodology, and some results will be presented. And afterwards, there will be some applications with the help of uh, PPT as well as with the help of video. So, more or less, drone can be called as unmanned air system, unmanned air vehicle, which is without or no human pilot, crew, or passenger will be on board in this case. So, it can be defined as that, but it can be classified on various factors also, like size. It can be micro UAV, mini UAV, medium UAV, large UAV with the help of range also, medium, short, close, rotors, tricopter, quadcopter, hexacopter, even single rotor also. And depending upon landing also, horizontal takeoff landing and vertical takeoff landing. Aerodynamics consideration also we can be there, fixed wing, flapping wing, ducted fan, multi-rotor, and it can be lighter than air or heavier than air. So you can see there are heavier than air drones which are various fixed wing, quadcopter, etc., and lighter than air like aerostat, airships, balloons, etc. If you classify based on weight, it can be nano less than 250 grams, micro 250 to 2 kg, small 2 to 25 kg, medium 25 to 150 kg, and large greater than 150 kg. So you can have single copter, multi-copter, birotor, tri-rotor, quadcopters, all those things. With fixed wing, you can have variable sweep, forward swept, out swept, everything. And hybrid, it can be including both. For vertical takeoff, you are having rotors, and for forward motion also you are having separate rotors. And during forward, you are acting like an aircraft. So these are some vertiplanes, convertiplanes you can see. VTOL, WASP, tilt wing, tilt rotor, and this rotor with testing for. So these are certain tail sitting UAVs. some configurations you can visualize. I'll go very quickly because of shortage of time. So some drone example, this is the simple drone with the camera. Then this is FPV, this is micro UAV drones which can be used for military purposes. Black Hornet, which is micro or nano also you can say. So this is air taxi you can have, flying wing. This is used for Indian Army also. Rustam 1 is there, male, medium altitude and long endurance. This is Rustam 2 also called, nowadays it is called Tapas. And there are certain more UAVs made by Boeing, stealth with stealth technology. Basic components, if you see, there are airframe, propulsion system, command and control systems. The variation may be from raw to sophisticated stage with advanced technology. So the system is same, but you can have different technology usage from raw to high advanced technology. These are certain sensors you can have installed on that UAVs. Optical, hyperspectral, thermal, LiDAR, multispectral. All these you can have vision with the help of this. So object detection. ये ऊपर आ रही है, ये लाइन नीचे कर सकते हैं. पूरा yes. Side. So object detection using UAV you can have, first you can capture image, detect whatever category you want to detect and track that also, and whatever position coordinates you can have, you can go with the help of object detection using this camera. And so if you see, AI gives the computer vision to UAVs basically, and this is also termed as image understanding, machine vision, robot vision, image analysis, or video understanding. So different names have been given, making references to the inferences about the external world. So if you compare machine learning and deep learning, both are part of AI. Machine learning is subset of AI, and deep learning is subset of machine learning. You can see with the help of machine learning, you can categorize or classify the image. Rather, it can tell you car, not car, or some numerical values it can give. But deep learning is extension of this machine learning, and it can give another classification features also, like car, which will be having yellow color, Ford. It can get that model also, and whether it is car or not a car also you can have. So more features you can have with more hidden layers. It is deep learning is with more hidden layers, and it extracts more features basically than the machine learning. So you can classify in this fashion using machine learning and deep learning. You can classify, label, segment, various mapping, etc. You can see vegetation separately, ground separately. With purely no vegetation you can have, and you can segregate the buildings also from a certain area. So motivation behind using this is AI or deep learning, etc. is automation, versatility, safety, efficiency, and speed. So drone sensor plus onboard processing makes the drone intelligent. So intelligent drone can have object tracking, self-navigation, object detection, and collision avoidance technologies, and more. So this can be first you can get the videos and then get the frames captured from that video, segregation, annotations you can do. Then pre-processing you can have with the help of then deep learning method or machine learning method. You can extract the features and further classify with the help of post processing. You can categorize the thing whether it is present or not, or in which fashion it is present. So in my work, we had done some project, and in that we had applied various deep learning techniques. Basically, object detection methods are mainly traditional image processing method and deep learning method. So based traditional image processing methods can be based on appearance, based on color, based on depth, based on motion. Also you can have you can subtract the background and get the actual image you want. Spatial temporal filtering, optical flow, and deep learning may be region based or single shot detection. SSD is called single shot detection, and YOLO is there. YOLO series is there, and there are region based detection also, where we can use recurrent convolutional neural network, and RFCN also you can use, faster RCNN, and other methods you can use. In our work, we had used all and compared all the methods, and we had arrived at the solution that YOLO V8 gives you the best results. So certain disadvantages or drawbacks or constraints you can have, that is flat and small view of objects. It will not be able to work properly. In case it can have difficulty in labeling data, object overlap may be there, image quality and resolution. If you are not having quite good image, then it will not be able to detect. Weather conditions can affect for the detection, and data volume and storage capacity of the computational system can also be the challenge, because it requires a huge memory. So you can use GPU in case of this deep learning. However, you can use a CPU for machine learning. So data processing you can have. We had done data collection, then annotation. Data annotation we had done, and with the help of RoboFlow, we had got this annotation, augmentation, and data quality checks we had done. Then some of the data was used for training, and then for testing. Model training was done, and then testing and evaluation was done with the help of unseen data, and calculate metric and compare different models. So we had compared different models, and interfaces on results, inferences, whatever we could get. That summary has been presented later on. We can see. So these were the data which were collected at New Chandigarh. Videography was done, and videos were got, and those frames were segregated. Frame rate was 50. So RoboFlow is a tool for data annotation as well as augmentation, etc. I have already shown. This was utilized, and the implementation of YOLO V8 algorithm was done to build the model, and it works best. Basically, it is also given in literature, so we used that after comparing various methods. So two classes were identified to detect or identify or classify. That was one truck and Isuzu D-Max. And then videos were converted into frames which were used to train the model. And then for testing, video feed was given as input for testing. So we had got this data. There is a road going which is having some truck as well as some Isuzu. So we were able to track with the help of this technique YOLO V8 Isuzu as well as truck. So we had a video also, but this is just a picture. You can see we could detect those from a quite high altitude. So these were the results obtained, graphical results also, training etc. was done, and the results were matching quite good. So drone applications, if you can see, so you can have a military and civil application basically, and in military battlefield combat, missile launching, target and decoy, war zone, medical, defensive, spying, and in civil you can have disaster management, environment, mapping, monitoring, crop monitoring, air quality monitoring, mountain inspection, soil monitoring, wildlife monitoring, mining, urban, etc., surveillance, logistics, and combining both these, you can make some laws also for enforcement, law enforcement, border surveillance, and police, etc. We can. So some of the examples you can have in terms of combat, mapping, reconnaissance, research and rescue. So search and rescue, whenever there is some avalanches in the hill areas, snow avalanches, etc. Some debris, some ice can cover this men also who are working over there. So you can identify those also, and search and rescue can be obtained with the help of this AI, etc. So model accuracy, confusion matrix. So you can see out of 1,000 images, 350 images had no human presence, and 650 images had human presence. And out of 350, the model predicted 348, whereas 640, 650, it could identify 624. So using AI and computer vision, you can identify the disaster situation also and manage that situation. In earthquake also you can have by making various techniques you can identify how it collapsed, etc. Then medical delivery, flood situation, and some flood situation, and this is monitoring of some construction on site, and you can monitor that also. Then you can have application of UAV for crop health monitoring with integrated information dissemination. So with the help of multispectral technique, sensor, you can utilize those also for crop monitoring. 3D terrain, you can also generate with the help of LiDAR, etc. And you can plan for some tourist places also by having whatever height variation is there with the help of this AI. Some latest technologies used, and it is swarm of drones which fly 15 meters. These all are drones. Might have seen some of the videos just to show that how drones can be utilized in so for indigenization you can have it. Most of the parts are basically from abroad. You can try to indigenize. The BOM is available in India, but was that dream girl. Then there was suicidal drone also we can have here.
Then pilots directed almost 3,000 precision strikes last year. We're super proud of it. It allows you to separate the bad guys from the good. It's a big deal. But we have something much bigger. Your kids probably have one of these, right? Not quite. Hell of a pilot? No. That skill is all AI. It's flying itself. Its processor can react 100 times faster than a human. The stochastic motion is an anti-sniper feature. Just like any mobile device these days, it has cameras and sensors, and just like your phones and social media apps, it does facial recognition. Inside here is 3 grams of shaped explosive. This is how it works. Did you see that? That little bang is enough to penetrate the skull and destroy the contents. They used to say guns don't kill people. People do. Well, people don't. They get emotional, disobey orders, aim high. Let's watch.
So this you can. So then thought I want to share that today drones, robots and sensors can provide intelligent and accurate information during disasters. This allows rescue workers to make better decisions during search and rescue, and AI can greatly improve the decision making process and shorten the turnaround time, helping emergency and disaster management efforts. So that's all. You can see various applications, and you can work in this is a vast area, and you can work in this field also, in the field of AI. Thank you.
We now open the floor for a few questions from the audience. And we encourage everyone to be as participative as possible. This is for you all as well. I think there are a few questions in the back. I can see hands raised over there.
Good afternoon, sir. My name is Kalin Gaur. My question to you is, you showed examples of computer vision and autonomy in drones. My question to you is regarding situations where signals or inputs by humans are not possible, like in the modern conditions that are going on in Europe and all. In those kind of situations where human signal is unable to reach, and the other inputs is unable to reach, how can a computer vision and AI enhance the autonomy of drones?
So AI does that only actually. It will get the signals from feed from the camera itself, but there is a onboard data processing which will see the target through that video, and then it can act accordingly. Okay. You have to program it before that what is the target you are going to. So accordingly that is trained, and it will identify the target with the help of user. There is no requirement of GPS, etc.
Okay, thank you, sir. So we'll take 2 questions. Can I ask one as well, considering as
Good afternoon, sir. I'm Shima from second year. Sir, I have a question regarding AI-based integrated drones. Can they be used in space research or exploration of any asteroid or any other planet in the future? And what are the challenges that we will be facing along with that?
AI is already being used everywhere. Actually, in space, it is rather more. It is being used, I think, and lidar is also getting the image imagery, etc., with the help of lidar, satellite lidar. You can use this lidar on satellites also. Through satellites, you can get all the pictures also. AI is being used.
So the final question is basically, considering that computer vision and automation is being used in the military industrial complex a lot these days, and they're moving towards a more automated framework so we can win the technology race. So, like, how will that help the civilian development sector, and how can we continue better cooperation and military contracts for higher quality applications of this?
Higher quality, if it is being used in civilian also, whatever technology is developed, that is best developed for the military purposes. And if you can use that technology within the framework of some rules, guidelines will be there. If there are number of drones coming up, then there will be guidelines also are there, and DGCA is already on the work, and they have published some guidelines also regarding this. And as it grows, there will be certain guidelines. It can be used as taxi or other useful purposes. There will be controlling measures also regarding this, so that it cannot be used for detrimental purposes. So rules will be there to guide all these things. It has a big future.
Okay, so we're concluding the Q&A session. Thank you very much, Dr. Rakesh Kumar sir, for such a visionary and thought-provoking session on computer vision and AI in drones. So now I would like to humbly request Dr. Sanjay Singh sir and Dr. Viyak Sanal Kumar sir to present the certificate and give felicitation to Dr. Rakesh Kumar sir for his keynote session. Thank you. And maybe have a mighty round of applause, ladies and gentlemen. Now, our second keynote speaker is Dr. Om Prakash, Professor, Mechanical and Aerospace Engineering, UPES, formerly the University of Petroleum and Engineering Studies from Dehradun. He is serving as professor and founding head of aerospace engineering at UPES since 2008, a long and industrious career indeed. He holds a PhD from IIT Bombay and MTech from IIT Kanpur in aerospace engineering. His research focuses on nonlinear flight dynamics, navigation, guidance, and control of hypersonic vehicles, UAVs, and hybrid airships, contributing significantly to cutting edge aerospace advancements. He has published extensively in AIAA USA, IEEE USA publications, including Scopus indexed conferences and journals. He is Fellow of Institution of Engineers India, Senior Member of AIAA and IEEE USA. He has been actively involved as international member in the Atmospheric Flight Mechanics Technical Committee of AIAA USA. He served on the board of studies of multiple universities and organized national and international aerospace conferences. He has worked in projects funded by DRDO and DST. He will deliver his keynote on ANN, artificial neural networks based rocket performance prediction and application of artificial neural network for predicting trajectory performance of a rocket given atmospheric conditions, which is a highly interesting topic. With that, let us extend a warm welcome to Dr. Om Prakash. We request him to join us on stage and address us.
Yes, sir.
Yeah. So good afternoon. Again, I would like to thank the organizers of this conference and especially Dr. Sanjay Singh and his team for giving me this opportunity. I will be sharing my work when during my IIT Kanpur, and then this is a relevant topic in modern days. Recent days. Artificial neural network, how it can be used to predict artillery rocket trajectory. Okay, and we talk a lot of about neural network. We have seen sir presented so many types of neural network. How much is capable of this neural network? How much difficult tasks neural network can perform. This is one example for you. So simple missile trajectory, if one has to, simulate. Okay. So either, you have to calculate, for a given range. I've seen some videos where from tank bomb shells are fired on another tank, so they have to give an elevation angle to the muzzle. So that the shell goes to another tank in, long distance in enemy area. Okay. So how will you make sure, like, you are sitting in the tank and you are firing artillery shell and it goes to the enemy tank and hits the enemy tank? How will you make sure? Okay. So elevation angle is one, and in fact this drift. Okay. There is aerodynamics. A lot of aerodynamics goes on when the projectile is in motion. Okay, and you have to make corrections for that when you give the angle to your muzzle. Okay, so meteorological department, will be able to give the atmospheric condition of that day. You can incorporate into your model, so that model can predict at what elevation angle you should fire on that day. Okay, so you cannot, very often keep calling meteorological department. You can train neural network, or you can make your simulation model, okay, based on the physics or based on the data in neural net. Okay, so rockets are fired at different elevation. I have given example. Okay, and range and drift is always our, how far it has to go, where is the enemy, how far I have to hit the enemy, and what will be due to aerodynamics, there will be drift. So the correction I have to give. Okay, these are, real life challenges for our army personnel in their war situation. Okay, so how the neural network can do. So this was the schematic diagram. So range and drift, two parameters based on what is the elevation angle. Okay, so conventional mathematical models are there, and then neural model. So how, intelligent will be neural model. Okay, you can see. I have to, how to keep this sound. In setting it has got. Okay. So this will not go as. Okay. So accuracy, will depend. How accurately you are able to hit the target. So atmospheric condition is one problem you have to deal with. Okay, day, night situation change, and season wise also situation change. So that density temperature affects the range, because drag and lift is always acting on the projectile. Okay, then during launch condition, your tip off. So when the rocket goes out of the muzzle, so it is still having low velocity, so there is a tendency to tip off. Okay, because there is a low velocity. So that tip off can affect the range finally. You are launching, your muzzle is at some angle, but the rocket is going initially with some other angle. Then aerodynamic jump due to wind. So the rocket goes rotating. Okay, in the muzzle, the Bofors shell or the tank shells, they go rotating like bullet. So when you have rotating cylinder, if there is a crosswind on the rotating cylinder, you get the lift. Okay, so you may have some angle set, but due to lift, some other induced angle is there. So that will also affect the lift and the range final. Temperature, pressure, headwind, tailwind, those are there. Even the thrust misalignment, the nozzles are also not properly aligned to the central axis. Okay, so you are fired, but the thrust is at some angle. So thrust is taking rocket somewhere else. Okay, so generally to cancel that misalignment of the thrust, you rotate the rocket. Okay, so how much you are able to take care of all these problems? We can see in our mathematical model, either you use point mass, modified point mass, 6-degree freedom is the ultimate model, mathematical model you can use, which can tell you how much drift is there if this weight condition is there, headwind, tailwind, crosswind. Okay, and you can take care of initial launch, tip off effect. I have equations coming. Okay, so point mass only takes care of drag. Okay, there is no spin, no way you can model spin. Okay, and forget about pitching yawing. Okay, so there is modified point mass, it can take care of the spin. Okay, okay, so you have pitching and yawing, so two planes of yawing, so 3 spatial degrees of freedom, it can go in 3 directions, and spinning, so this makes 6 degrees. Okay, so initial condition, aerodynamic lift, if I have to fire this mic set, okay, if I have to fire this in air, I have to do the wind tunnel testing of this mic first, then I can predict how far it will go. Okay, so the CD of the object, CL of the object should be clear to you. How accurately you are able to do the wind tunnel test or CFD, that is up to you. So so many issues are there. Okay, so my heading will hide this if I can move this. Yes. Okay, so this is the equation of a tip-off modeling. If you are able to model in your 6-degree freedom model. Okay, so simple this equation, results are there. No problem, I'll keep shifting here and there. Okay, so next I have result in next slide. With this equation, how much you are able to capture the effect. Okay, yes, so you can see this circle is the exact value, and with simple 6-degree freedom without tip of effect, you have a cross, and with tip of effect you have a star. Okay, and even after tip of effect, still some correction factor you have to do to match the actual value. This is what happens mathematically. Okay, so you can see how much we are successful. Okay, very difficult to match. Go into the circles. Okay, so it's so difficult mathematically, even doing computer simulation. So this is aerodynamic jump. just to show you the title, aerodynamic jump. Okay, so because it is rotating, crosswind is there, rotating cylinder will produce lift. Okay, so again 6-degree freedom model plane with aerodynamic jump using this equation into the model, and then after that even we are not able to get the accurate results, some factor we are using. Okay, so I mean here we are quite successful. Okay, near about all the results matching to the circle. Okay, circle is the exact. So that was crosswind, then range wind, ahead, headwind, tailwind. So that also one has to model. Okay, so here still we see the deviation in drift, because drift is also important. Okay, so now comes artificial neural network. Okay, you have seen how it can be done. I mean, what is the architecture inside? What are the uses of this? So 3 cases we have done. Okay, predict the range for given elevation. If you fix the elevation, what will be the range? Predict the elevation given the range. If you know the range, can you estimate the elevation? Okay, then under standard atmospheric conditions. Okay, so this is nowadays I think everybody knows about internal architecture of neural network. So you have set up input. For us, you can see the range, wind condition, Wx, Wy, velocities, pressure, temperature, I mean charge temperature is also there. Okay, and we are trying to find the elevation angle even sidewise also. And okay, so what knowledge is required is learning process, how to make the neural network, I mean learn, train. The training skill you should all need. Okay, no mathematics. Okay, and there are parameters, hidden layers, learning rate, momentum constant. If somebody has worked in neural network will understand these parameters. So you have to worry about these parameters. Okay, so first model, again elevation, range, wind, crosswind, temperature, pressure, charge, temperature, everything is model. Everything is given to neural network. Atmospheric condition, wind condition, whether it is jump, whether it is tip of effect, okay, or atmospheric effect, how it is able to give us range for the given elevation angle. Okay, so I mean this is the after training, the prediction from the neural network you have seen. I mean you don't have to vary all those effects to the neural network. Only thing, pick the right number of neurons, hidden layers. Okay, the training you should know how to train neural network, like how to train a small child. Okay, to learn something. Okay, I mean parents have that kind of issue always. Okay, so another, now range is known, elevation angle. Okay, you can see how match is there. Random angles are given, random range is predicted by neural network so nicely. Okay, so this is the last case. Okay, and here also you can see the range and drift both. This is standard condition, the standard conditions. Okay, I mean you can see, I mean there is a very nice match. Okay, so I mean even you can predict the complete trajectory. This I have just added just to show. Okay, so I mean you have seen the capability of neural network. Okay, I mean you decide what, go for conventional or neural network after seeing this much. So set of available firing data we had, we predicted for all these values, tailwind, crosswind, charge temperature, atmospheric temperature, pressure, all those values, neural network is able to take care of. I mean so powerful is the technique. I mean, result of model compare. Well, you have seen through the graph. Okay, so I mean, mathematical. I mean, how many people like going through mathematical tools? Okay, it is up to you. So I mean, force, moments. Okay, aerodynamic coefficients. So many things are required in normal case. Whereas in neural network model, do not require any of the mathematical. Okay, and if the neural network is trained in real data, it will automatically account for initial conditions also, initial jump, okay, or tip of effect. So I mean, so many applications you have seen. Inside detail I have shown you of the neural network. Okay, so now is the age of working smart. Okay, I mean hard work also, but smart will at least initially supersede. Hard work wala will come later. Okay, but initially also you have to produce some result quickly. So I mean you can go for mix. Okay, so I mean there is supply data can be error in the supply data. So I mean there are so many. So much of capability of working in neural network in aerospace engineering itself. Okay, so with this, I hope you have understood about the neural network and trajectory modeling. So with this, I would like to conclude my presentation. Thank you.
Now the floor is open for the questions.
Good afternoon, sir.
Good afternoon.
So my question is, looking forward, do you see hybrid approaches combining physics-based models with neural networks as a way to future enhance reliability in trajectory prediction?
Yeah, reliability is important. Okay, whatever you do, reliability is important. So of course, hybrid will always be answer for that. Okay, so definitely you have to partly work in both. That will be, reliable case. You have to really sweat to get the reliable system. Anything reliable. So both hybrid is, the age for. We have seen hybrid drones also. If you want to make most reliable drone, it has to be hybrid, quadcopter, fixed wing, both together. Okay. Yeah. Thank you.
Thank you, sir.
Any more questions?
There are many training functions. Okay, so which training function is used to train the network, and which one is the best training function to train?
We have so many. Those training functions are actually mathematical functions. Actually, there is a mathematics going inside the neural network as well. Okay, but that's not physics based. So sigmoidal, other this thing. Now these functions are suitable for some type of work. Some functions are suitable for some other type of work, like vision based. Identification. So you have to do first literature survey and have some first hand experience. Do some survey, then select the right function. That will be the right approach. Okay. So there is no clear cut answer, but
which training function?
So we have used the sigmoidal. Okay. Thank you.
Excuse me, sir.
Yes.
Sir. So basically, just the previous question, the hybrid approach of using the ANN model with the our data to predict the trajectory of the rockets or aircraft, right? So I want to ask the how much like the prediction, efficiency of ANN based prediction. Like, what will be the level of prediction? Can we actually achieve the proper prediction, or there will be some errors in the mathematical codes or models?
No, in fact, I was searching about this question over this. Weather prediction itself, you have seen so much of uncertainty in weather, so much of flooding situation, so much damage in property in hilly areas. I come from Dehradun. I've been taking classes online. 2 weeks. We have got one bridge damaged on our way to university. So weather prediction, mathematical model, again, I will say hybrid will be the best. Have a physics-based model and again have a neural network approach also, so that most reliable, because public need reliable information. They don't want to wonder like whether you're saying is right or not. Okay, so definitely in weather prediction, this approach, will give most reliable weather prediction approach, neural network as well as physics based, and people are using this. Okay.
Yes. Okay.
In fact, our mobile app, it gives like 2 weeks prediction nowadays in our mobile. Like, you cannot tell tomorrow, on your own. Okay.
Thank you so much, sir, Dr. Om Prakash, sir, for enlightening us with your knowledge, whether it be training neural networks for defense purposes or predictive analytics study for attack angle for accurate projectile of rocket and rocket performance in different atmospheric conditions. Now, I would like to call upon Dr. Rajesh Kumar Saroja, sir, and Dr. Neeraj Gehlot, sir, for the facilitation of Dr. Om Prakash, sir.
A round of applause, ladies and gentlemen, for the felicitation.
So we now transition into technical session 4 on aerodynamics, fluid dynamics, wind tunnel, and computational fluid dynamics. It is an honor to introduce our session chair, Dr. Rakesh Kumar, and our session co-chair, Dr. Basant Singh Sikarwar.
We request our session chair, Dr. Rakesh Kumar from Punjab Engineering College, Chandigarh, to please take their seat at the chair and accept the gifts and the session materials required. Session materials. Can the technical team please assist with that? We also request our session co-chair, Mr. Basant Singh Shikarwar, sir, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, to also take a seat and accept the required session materials from the technical team, so that we can get underway with technical session 4.
So we now begin with the paper presentations of technical session 4. I would like to inform you also that 3 additional sessions are running in parallel. Technical session 5, which is on flight mechanics, air stability, aircraft maintenance, and UAV, which is held in F1 MDP hall. Technical session 6, which is on space, is held in F3 MDP hall. And technical session 7, which is on materials, is held in B block, room number 006. We request our esteemed delegates and participants to engage with the technical session that best aligns with their interests. The total allotted time for paper presentations is 10 minutes. The first bell will ring at 5 minutes, the last one at 8 minutes. We request you to complete your presentation 2 minutes after the last bell rings, after which we will open the floor for the question and answer sessions for 2 minutes.
Our first presenter for the day is G. Sai Satyanarayana from Department of Aerospace Engineering, Uttaranchal Institute of Technology, University. He'll be presenting online, so we humbly request him to share his PPT and his screen. So, can you please put it on slideshow as well for the ease of access of everybody? Slideshow.
Sir, could you please put it in the slideshow?
Yes, so it's right next to animations. Can you please click on that slideshow on top, on your top bar, next to home, then insert, then design, then slideshow, right there, on the left side of review.
Should I start my session?
Yes, sir. Yes, sir.
Yeah. Hi. Good afternoon, everyone. My name is G. Sai Satyanarayana. I'm a research scholar from Department of Aerospace Engineering, Uttaranchal University, Dehradun. So my today's topic is scramjet engines, high altitude air vehicles. So in the slides, the contents are introduction, objective, methodology, and conclusions. So coming to the introduction, hypersonic air breathing propulsion is an essential technique for achieving low Earth orbit vehicle performance. The specific impulse of supersonic ramjet engine is much higher than non-air breathing engines like rocket engine, as rocket engines carry onboard oxidizers, supplies, so they increase the payloads. This makes scramjet engine to be an integrated with low Earth orbit with trans-atmospheric region to achieve the better performance. Here below I have shown the body of scramjet engine. And coming to the introduction part, a scramjet has a simple concept of solitary continuous flow with no moving parts, inward flow which is compressed on the vehicle's forebody using a suction of oblique shock waves. In isolator section, a shock train that interacts with the developing boundary layer gives a time required for the combustion pressure rise, preventing inlet unstart. Once this air reaches the combustion chamber, fuel is added and mixed with airstream. The ignite gas mixture then expands and goes down the nozzle, generate thrust. This is about the survey which was beginning of a scramjet. The survey is early up to 2000. The survey starts from the short description of NASA Research Center project concentrate on developing airframe integrated scramjet technologies commonly known as supersonic combustion ramjets. NASA Research Center and Johns Hopkins University Applied Physics Laboratory follows an analysis of advancement of computational fluid dynamics concerning notable events in American scramjet research. In 1964, the NASA Hypersonic Research Engine (HRE), the project was initiated, design, develop, produce a supersonic or a hypersonic ramjet engine with high efficiency and Mach 6 ramjet test facility within National Aerospace Laboratories NAL Research Center tested a small version of scramjet engine. It is a prototype model. Research is being done on a shock-induced combustion ramjets for hypersonic air breathing propulsion with a new concept, planar and axisymmetric arrangements, as well as exterior and hybrid compression setup are utilized to approximate two-dimensional geometries. This is survey up to 2015. In 2015 till 2015, a few techniques that the scramjet research have employed to improve a fuel oxidizer mixing while maintaining a high efficiency of combustion with shorter combustors are reviewed. Research belonging to the aircraft noise reduction on enhanced supersonic free shear layer mixing is also added to the review to determine how oblique shock wave reacts against the hydrogen air jet like flame. Wedge is installed on combustion sidewall. The relation between the combining layers and waves of shock is characterized by increasing trend in mixing layers growth rate downstream as result impact waves. This is one more, the same continuation. This is survey till 2015. A large eddy simulation model is centered on unstructured infinite element approach of filtered continuity, momentum, enthalpy, and passive reactive scalar equations, which represents combustion process through total decrease of flux reconstruction, the fundamental challenges of supersonic mixing layers, modeling efforts for high speed combustion, and actual calculations of practical scramjet combustions. The review reveals that a very few LEs works. The RANS approaches pre-demonstrate the system's turbulence modeling. This is a survey till up to 2023, the design performance with advanced technology, the impact of boundary layer thickness, hydrogen injection position, cavity, slot bleeding on fundamental combustion performance under constant intake flow parameters are scrutinized during this combustion design. High-speed scramjet engines are used in military missiles and provide inexpensive access to the space. Scientists from all over the world are always attempting to improve them. Heat energy is produced as hydrogen is pumped into the scramjet combustions, causing a combustion to occur inside supersonic flow air. The objectives are focusing on year-wise survey of scramjet engine, like year of a scramjet engine, analytical growth and experimental growth, discussion on governing equation and design, general boundary conditions of scramjet engine. This is a methodology. On screen, we can see the dimensioning of a scramjet engine, how this scramjet engines are dimensioning. And I have named the few parts also, like, boundary layer location and compression ramp, actual cowl section, removable isolator blocks, etc. And coming to the methodology, I have used governing equations. RANS equation is a primary numerical tool for the investigation development of boundary layers within supersonic ramjet. Here I have shown the conservation of mass, conservation of momentum, and conservation of energy equations. And the boundary conditions of numerical analysis are steady state conditions. Two-dimensional scramjet models are considered. The preferred turbulence is K epsilon and compressible ideal gas is preferred. The conclusion, the current review discuss the initial observation regarding the supersonic ramjet engine. Based on the paper, the primary requirements of scramjet engines are layout of diffuser, specific impulse, fuel oxidizer, and combustion chamber. Numerical simulations are being explored for the standardization in the layout of scramjet engines, since they are correlate to outcomes that are almost identical to those achieved experiments. This is permitted to challenge the design and combustion of characteristic to attain in-turn configuration. Thank you.
Thank you so much, Sai Satyamurin. So,
our next presenter is Dr. Rajesh Senthil Kumar T from Department of Aerospace Engineering, ASC CBE. We would like them to share the screen, please.
Hello. Could you able to hear me? Hello.
yes, sir, you are audible.
You're audible, sir. Yeah. Thank you. I think could you people can see my presentation.
Yes, sir, you can proceed.
Yeah, thank you. So, I am Dr. Rajesh Senthil Kumar. Here, I am going to present our work on augmented one-era dynamic stall model, which we took insight from our another reduced model, expanded dose model. So, last time in MRAE 2023, we have come up with a dynamic stall paper where we have found out this problem. In that journal, we have found out the problem. Now we are continuing that work. So this is the content of the study. So first I'll talk about dynamic stall phenomena. Then I talk about the motivation and objective of the study. Then I talk about the methodology. Then I go to results and I conclude accordingly. So as introduction, the dynamic stall is called as a nonlinear unsteady aerodynamic phenomena, which happens very rapidly. Initially, if you see that it delays separation, but it happens at higher angle of attack, and it leads to lift to overshoot, and it gives unsteady loading as a hysteresis loop. So this is more critical for all the rotor curves, and it has to be understood very strongly. It's a complex phenomena. So in last MRME, we came up with a paper where we use CFD and try to capture the phenomena. So you're seeing this side CFD figure, this is result for the CFD. So now CFD is a high computation tool. But if you see one-era model, which evolved very early, 1985, which gives a red color curve, which runs in a very short span of time. But the black dots are full of experimental data. But if you see CM results are coming closer to the experimental data or quantitatively capture the physics. But this red color line losing something. So now the problem is that the motivation for the study itself, improving this one-era model, which we used in the previous MRM study, to match the experimental result. So when we search the literature, there is another dynamic stall model, which is widely used by Leishman-Beddoes model, which could be able to capture the physics of dynamic stall model much better and comparable with the results. So you can see the red color line is from the LB model, which could be able to comparable with the experiments. So the blue color line is now one-era model. But if you see the comparison between one-era model and Leishman-Beddoes model, one-era model is purely a mathematical model. That means you solve ODE and ODE gives a result. But Leishman-Beddoes model has need lot of experimental data, so they'll correct the experimental data to put it into this dynamic stall behavior. So now the advantage of one-era model is you have to model equation. Once a equation is model, play with the parameters, you get the results. So now what is getting lost? That's what we are talking about. If you saw the loads in dynamic model compared to one-era and LV model, the total load could in LV model could be able to capture the peaks. That means they could capture the peaks. This is what unsteady phenomena, which will come at initial point of dynamic stall. So if these peaks are captured, then obviously we are getting the physics properly. So in one-era model it is not captured. So if I split this loads in one-era model and LB model, it's all types are more or less same. So impulsive same, circulatory same, but stall component more or less same. But there is one load which is missing over here, so vortex load, which is not modeled in one-era model, which is taken care in the LB model. So now the role is to model that mathematically. So the classic one-era model, it has this is the equation, which I put it only for lift, which is same similar for drag and moment. So if the lift has to be computed, they will have this added mass terms due to the pitching and plunging. And there is two gammas, gamma 1 and gamma 2. Gamma 1 is going to talk about attached potential flow modeling with second order ODE. And next one is gamma 2 is a stall component, which is also modeled as a second order ODE. So this you can think this problem as a second order ODE problem, a second order control system problem also, because this entire logic comes from there when Pitot modeled this. Now the problem is there is no vortex modeling in that. So how to look into that? So the objective of the study is to enhance a one-era model to account for this loss in lift. That means I want to get some nature of the math which could be able to get me this results and added over that to make this more better. So now the first modification that I had for is I added another ODE which you called as gamma 3, which is going to give me only the vortex lift. It's going to only the vortex lift. And you see this is a way your any general second order ODE looks like. So you have second dot of gamma, first dot of gamma and gamma. And you see right hand side we wrote a efficient function which is a decaying function. It is a decaying function. So once I see the first peak, then I have to immediately decay the second peak. So I should allow that to oscillate like an vibratory problem. So I want to get only two peaks as that experimental thing. So we noted like, so we took inspiration from vibration of the system and we modeled this convenient form of equation and tried to model the two peaks which we missed in the Onera model. So the the click here is this delta CZ, which is real in terms of real aerofoil. For potential flow, we don't have this stall modeling. So obviously, we need idea about stall characteristics of static aerofoil. So for that, we used XFLRI. So if you know the stall characteristics of static model and we know how potential model behaves, delta CZ has to be modeled properly. So we understood delta CZ is not taken care very clearly. So we went and pushed into that. So if you see, there is C1, C2 are constants of the equations. So that is particularly with respect to aerofoil, I have to tune it. So let me say how the aerofoil, what aerofoil used. By the time these numbers are evolved, and but it is given the paper. The C1, C2 exists in the first derivative and second derivative, and A is the one that talks about the peak of the first amplitude. And from if I properly control this, I would get the peak of the second amplitude. So after this, it dies off. But here is this should not start at the start of the starting time of the oscillation. It should start after some time. That means if you see cycle time from starting time to this 0.22, this equation won't respond. After 0.8, this equation won't respond. So I have to work within the band. So if you see the wild used aerofoil is a NACA 0012, for which everybody has justified this mathematical model. So if I see those models, I could be able to interpret the time of oscillation. So I could be able to do this. So we wrote a function for A, amplitude of this one, okay, in terms of maximum of delta Dz, and in terms of Mach number, and this is called reduced frequency of oscillation. So likewise, we modeled beta, and likewise, we modeled the phi. And this is a time constant which heavily affects simulation. From this time constant only, we are getting this when it has to start, when it has to stop. So this equation was modeled, and second modification was incorporating the separation loads.
Could you conclude fast?
Yeah, including separation loads. We used a Kirchhoff's law from LB model and corrected it for our model, and we added. So now we could be able to have the total loads as such. So this is the augmented lift model. So now we attached flow, separator model, and vortex circulation model. So now for a given aerofoil, that 0012 aerofoil, the augmented model goes closer to the experiment, predicts exact like experiment. And similarly, we went with moment. Moment also, we did the same thing. And here also, moment also, augmented model predicts the performance very nicely across theta's and across case. And the problem here is we had only problem in terms of modeling drag, which we are trying it out, where we have found out a slight loss in data or what predicting the nature happens in CD. So in terms of CL and CM, we could be able to get the exact nature that of LV model could be able to produce. So we tested the another aerofoil also. There also we could be able to get the same performance. So as of now, we have come closer to LB model, and within three equations solving simultaneously and without any external data is needed. Only if you have some static airfoil data result that took an XFLRI, it could be able to run and give the data. So future work is we have a little bit improve the drag model and make it more fine. Thank you.
We now open the floor for any questions. We encourage the audience to also participate in Q&A.
Can we have some applications of your work?
Yeah, this is, sir, we are modeling dynamic stall of rotor craft, which will happen at the tip of the rotor blades. This will help us to extend the study in terms of air elasticity, where the load has to be modeled seriously. So now this lower order model could be able to capture the physics properly. So now we can able to do air elastic studies very strongly, so that we can exhibit two-way FSI with one side vibration equation, another side with this load.
Thank you so much, Dr. Rakesh Kumar Senthil Kumar. Now, I would like to call upon Anjali Mistry, Department of Aerospace Engineering, School of Engineering and Sciences, MIT ADT University, Pune.
Can they please share their screen and put it on slideshow as well? Thank you.
Is my screen visible?
Yes, yes. Can you put it on slideshow as well for the ease of viewing, everybody? Thank you. You may begin.
Can I start?
Yeah.
Okay. Good afternoon, respected jury and fellow participants. I'm Anjali Mistry from MIT ADT University, Pune, going to present our research paper titled The Effect of Airfoil Variations on Aerodynamic Parameters in Propeller-Based Configuration on behalf of my team. My teammates are Vidanshu Jadhav, Vedant Chaudhary, and our guide is Professor Dinesh Kumar Bajaj sir. So this will be the flow of our work, starting with introduction, literature survey, objective, methodology, solver and boundary conditions, validation, results, and conclusion. So as we all are aware that aviation industry is booming day by day, and various researches are going on to make the propulsion units electrical or distributed. So to reduce to emissions and increase the energy efficiency. So why does DPS are in increase in recent times? The reason is the conventional units, we can see there are twin engines, each on one wing, whereas in the distributed propulsion system, there is a distribution of smaller propellers on smaller multiple propellers across the wing, which offers several benefits such as increasing short takeoff and landing capabilities, noise reduction, lower operating cost as those are electrical or hybrid induced propulsions, improving safety. For example, if one propeller stops working, then we can rely on rest of the propellers also, and less pollution compared to the conventional configurations. In the figure 1, we can see NASA's X-57 Maxwell plane, where we can find multiple propellers are attached over the wings. Moving on to the literature survey, thorough research has been done on this topic, and the most important ones are presented here. Peter Sharpe and Agrawal has studied on the inward up configuration of propeller attached to a wing of the UAV configuration, where they have found there is lift gain of 18% and a slight increase in the drag. They have also validated the CFD result with the wind tunnel data. Further, Bhalerao and others have considered a Dornier aircraft model where they simulated the model with and without attaching the multiple propellers, and they found that when they have attached multiple propellers, the lift by drag ratio increases to 70%. DIMCHIP have worked on the wingtip mounted propellers for UAVs, while other studies investigated wing propeller combination at various angle of attack, which can be seen in the figure 2 of the literature survey. However, from this literature, we found a gap that although various propellers placements and propeller with a particular wing have been studied, there is still limited investigation on how changing airfoil profiles can affect the performance in the propeller based setup. So this motivated us to carry out our work. So the key objective of our study is to analyze how the aerodynamic parameters such as coefficient of lift and coefficient of drag can be enhanced when the airfoil shape of the wing is altered with propeller attached to it. So for our study, we have implemented NACA 2412, NACA 4412 and NACA 66212 airfoil. In CFD related research, we know that the first step is to validate the solver setup. For that, the geometry have been taken from the Peter Sharpe's paper. The dimensions are as shown on the slide. The NACA's airfoil profile used for the validation geometry wings is NACA 642015 series with its half span of 0.325 meters. The propeller is 4-bladed propeller, and in the table 3 we can see R to R by Rmax ratio, C to C Rmax ratio, and beta B. The Rmax value was mentioned in the paper, which helped us to calculate the R and C values for the 8 different cross section, which helped us in creating the geometry of the 8 in the propellers, as shown in the figure 4. And in figure 3 we can see the we have built integrated all the geometry. The geometries were created in Fusion 360. Moving on to the next part, the next step is to create domain and mesh. So two different type of the meshing domain were used: static and rotary domain. The rotary domain was implemented over the propeller blades, and the static one were given inlet, outlet and symmetry. As we can see in the figure 3 that it is the whole geometry is symmetric. We have given the symmetric wall to reduce our computational power, though the dimensions of both the domains are shown on the slide. Then we have used unstructured types of the meshing, where we have tried to kept finer mesh near the propeller blades, near the wing, and all through the geometry, so that uh, we can visualize the flow very properly over the geometry. The solver setup and boundary conditions were kept same as from the base paper of the Peter Sharpe, which were 3D unsteady with pressure-based solver, and the model used was viscous K epsilon realizable with air as its air with constant property as material. The velocity to the rotary domain was provided as 1164.7 radian per second, with its rotation axis defined as plus x. The overall air inflow was given the velocity of 35 meter per second with turbulent intensity 0.5% and turbulent viscosity ratio as 2. The outlet was defined as pressure outlet with ambient pressure. And as I said earlier, the center line wall of the static domain was given symmetry, and the rest 3 was free slip conditions, and the remaining walls of the geometry were given no slip conditions. Furthermore, the reference values were implemented from the inlet with surface area of 0.078 meter square and constant air density. The schemes used were couple, gradient method was least square cell based, and pressure interpolation was Presto, with momentum kinetic energy K and turbulent dissipation rate as third order MUSCA. The constant numbers are as for the as in the shown on the slide. All these values and data have been kept same as the paper to validate a solver setup. The validation and grid independence table shows different number of elements used for the meshing type, so that we can get a closer value to the lift coefficient. Same, try to get nearer value with that of the base paper, and to and this values were changed altered to also get wall y plus below 5, so as to maintain the accuracy in the results. Now after validating the solver setup, we have changed the airfoil from NACA 642015, which was used in the validation geometry. 2, we have changed it to NACA 2412, 4412 and 66212 with propeller attached over it, and the simulations were carried out with the same boundary conditions and solver setups. From those simulations, the result obtained are tabulated. Our primary motto was to check the aerodynamic parameters. So we have plotted coefficient of lift and coefficient of drag, and those results for all the 3 different airfoil profiles have been tabulated in the
Please
table.
wrap up. Kindly wrap up.
Yeah. Yes. Uh, So we can see from the table that for 66212 profile, there is highest lift obtained compared to rest 2, and also the drag is 0.3432. Also, we have plotted the flow contours, which showed that there is an increase in the velocity. Also, the streamlines also showed that the flow has been accelerated, and which causes the circulation, and that results in the higher lift distribution. To conclude our work, our study shows that airfoil selection also plays a significant role in improving aerodynamic performance in propeller-based configuration. From the simulation results, we found that NACA 66212 airfoil with propeller attached on the wing has the highest coefficient of lift and coefficient of drag. The value of drag coefficient was slight higher than what obtained for NACA 2412 and 4412. That can be because there is alteration in pressure distribution and propeller induced slipstream. Further, we can implement this geometry in the whole aircraft and with multiple propellers attached to it, and we can then simulate the whole aircraft model to study those effects very properly. Further, we can also change the number of propellers and see and check its thrust distribution so that we can find which configuration gives the optimum performance. Also, in the future work, we can make the propellers ducted to check its acoustic parameters. These are some of the references and the image source. Thank you.
Thank you so much, Miss Anjali Mistry. Now the floor is open for the questions. Any questions?
We encourage everyone to be active.
Anjali,
yes,
you
sir.
have not taken into account the thrust. You have just gone for the lift. Lift in case of propeller is basically producing extra amount of drag. So you
Yes, sir.
should.
We have just, yes, sir. As of now, we have just considered lift and drag coefficient. Thrust distribution is in our future work also. So we are going to implement that also.
So what is the reason of extra amount of drag you're getting in that case?
Sir, as we can see that propeller is attached on the wing, some part of the weight is also increased due to propeller attached. And as propeller is moving, the flow vortices are created. So that are causes increase in the drags.
Your title is saying that aerodynamic parameters. Parameters are generally derivatives basically. These are coefficients you are estimating. Aerodynamic coefficients. You should have written coefficients, I think. Parameters are stability and control derivatives. Those are partial derivatives. Okay. Take
Okay,
care in
sir.
future.
Yes, yes, I will take it into consideration.
Okay, Anjali, I have one question here.
Yes, sir.
If you see your presentation, you never give the any type of validation.
Sir, we have conducted validation and I have shown that in the validation results table.
Second
Should I?
thing is, yeah, second thing is a grid independent test.
Yes, sir.
Grid independent test by plus your input or by plus your output.
Sir, output, we have checked those
How
values.
the y plus how is the y plus is output because the mass is generally input.
Sir, after implementing different mesh types and increasing the elements, and after the simulation is over, we have checked in the output case wall Y plus turbulence model in the results. So on the body, if it is coming less than 5 or not, and in that we have found out try to keep it below 5.
Okay, so you measure the by plus y simulations, but what is the mesh size, minimum mesh size at the wall?
Sir, minimum.
It is less than 2 by plus, it is higher than 2 by plus. Okay, anyway.
I'm not able to recall actually, but we have tried to. get it from the base paper only, where they have mentioned inflation layer size on the wings. It
It's
was
okay.
near about 0.01 meters only.
It's okay. Try to understand. If your
Yes.
mass size is bigger at the wall, definitely your by plus value is not correct. Clear?
Yes, sir.
Actual by plus value is very kind of depend on the what is the mass size close to the wall.
Yes,
One
sir.
simple things. Second,
Yes, sir.
and here you give the some parameter. You use the ANSYS fluent. You say that I am using the pressure based solver.
Yes, sir.
Suppose I am using the density based solver. What is the impact of your result?
So then it will be like a more of a compressible flow. In our situation, we have kept the velocity at 30 meter per second, which shows Mach number much less than below 3, which accounts for the incompressible flows. So considering that, we have chosen pressure based, and if we consider and if we try to increase the velocity far beyond, like for the Mach greater than 0.3, then we can go for the pressure based values, where density solver, where density also varies as the Mach number is higher.
So, what is the difference of pressure based solver or density based solver? Only the compressible, incompressible, or something other?
Sir, as per my knowledge, I can say this
Your knowledge is
shows
only
us in it shows about compressible and incompressible flow, where density remains constant, and in one the density also changes with the flow parameters.
So, last questions. You use the press to pressure. What is the motivation to use the press to pressure? Why aren't you choose the standard pressures or second order?
Um, Sir, as I've mentioned also, that all those values were taken
Taken from
from
the
the
reference.
reference paper only, as we needed to validate the solver
So,
setup.
so overall, you just repeat their problem, base paper problem.
We have no, sir, but we have first tried to validate a job solver setup. So for that purpose, we have taken those values.
Okay, thank you, Mrs. Anjali. Now we move on to the next presentation by Mr. Nasik Mohammad Marzook Khan from Amity University of Aerospace Engineering, AUUP. Can you please share his presentation and put it on slideshow?
Yes. Is my voice audible?
Yeah, your voice is audible. Yeah, you can start.
Okay. Right. So good afternoon. My name is Nasik, and I am here to present on behalf of myself and my team on the trailing edge cavity induced drag efficiency in a supercritical airfoil. So, as a brief introduction to this topic, whenever we're dealing with transonic flows, we encounter some challenges, such as the formations of shockwave, boundary layer interactions, unsteady effects like buffeting and flow separation. And in order to still be able to efficiently produce lift in these conditions, one solution that we have is to use a supercritical airfoil. In the case of our study, we use the SC second generation 0710 airfoil, which reduces the drag using a flat upper surface, a thick trailing edge, and a cambered aft section. And this paper is going to be focusing on the trailing edge of this. So the importance of this trailing edge basically is that depending on the thickness of a trailing edge, you can reduce the drag up to one point. You keep increasing that trailing edge thickness, eventually drag will also increase. So in this case, we've taken 0.7% of the chord as the trailing edge thickness. And this study will explore the effects of a trailing edge cavity on drag reduction and performance enhancement using CFD analysis. So the objective of this study is basically to evaluate the aerodynamic impact of a trailing edge cavity on the SC second generation 0710 airfoil at transonic speeds. and we will compare drag, pressure distribution and shock structures with the baseline airfoil of the same, that is without the cavity. So how did we go about this? Firstly, we selected a baseline design, and the chord was taken as 63.5 for this particular airfoil. And simulations were done on ANSYS Fluent on Mach numbers ranging from 0.6 to 0.82 with steps of 0.02. And the ambient temperature was set to 322 kelvins, which we took from a reference study, which is what we validated this with. And yeah, the cavity added at the trailing edge was kept identical to what we were comparing to, just to help us with validation. And the key outputs we focused on over here is we analyzed the CP distribution about the airfoil, the drag coefficient, the Mach contours, and the surface flow patterns. So these were the geometries we made. We filled in the geometry just so it's better visible on the board. There's a pointer. Yes. These are the geometries we picked, and at the end over here you can see there's a little cavity. The thickness of this cavity was 0.0049 of the chord. That's 0.49% of chord length. This was our flow domain, and this was our mesh. So moving on to solving, we selected the pressure-based solver with having enabled the energy equation. After which we selected the SST K omega for accurate shock boundary interactions, and the boundary conditions were basically pressure far field for all the edges, and the air was set as an ideal gas. Viscosity for that air was also set as Sutherland's law, and the free stream temperatures of 322 kelvins. The output data that we focused on were the drag coefficient, CP distribution, and pressure contour. So moving on to the result and discussion of this, the first thing I'd like to show you is the validation of these results, just so you know I am not showing you any inaccurate statistics. And the optimization added to this is the cavity, and yeah, we will be comparing that to some experimental results done by another study. This is what we achieved. The yellow line is what we achieved, the CFD data without cavity, and the blue line is what the experimental study achieved without the cavity as well. So our results show that they closely match with the experimental data provided by NASA in one of their studies, validating our simulation's accuracy, and shockwave and sonic point formation are observed via the Mach and density contours itself. Minor CD differences are present due to the trailing edge thickness variation. We are comparing 0.49% to 0.7% of chord thickness. And yes, this confirms the robustness of our CFD setup for further aerodynamic optimization. So we went ahead and put these settings onto the other cases. These are the Mach contours and density contours at 0.82 for the blunt trailing edge. We can see a formation of a shock wave here now, which is why we chose this to be our the higher limit of our Mach number. We did not exceed this. And yes, now to compare our results with and without cavities. Without cavity is the yellow line you see on top, and the black line is the one with cavity. This is a coefficient of drag versus Mach number, and we can see that at every single point, the CD achieved by the airfoil with the cavity is less than compared to without the cavity. The same points are plotted down onto this table over here. And yes, in the end over here we have a drag efficiency. Basically this is the percentage of how much the drag fell after having introduced the cavity into this. And on average we got a 15.95% less drag with a small cavity at the end. So we can say that there's a drag reduction The cavity modified airfoil shows consistently lower drag across Mach 0.6 and 0.82. There's a 15.95% average increase in aerodynamic efficiency, that's decrease in drag. And shock behavior, Mach and density contours, they validate improved shock control with cavity design. Then there's critical Mach. The optimized airfoil performs better near the drag divergence Mach number than compared to the blunt edge. And we successfully validated these results as well, so we know these are reliable. And this is a coefficient of pressure distribution. This over on this side we have the leading edge, this side we have the trailing edge. Whatever is above here is the lower surface, and whatever is below here is the upper surface of the airfoil. The red color is the blunt and the blue is the one with the cavity. And we can see that there's always a higher difference between the upper and lower surfaces of the blue compared to the red. So this also suggests that these airfoils, they're more efficient in making lift, they get slightly more lift. Now higher lift, lower drag, that also means higher lift to drag ratio than compared to the blunt. So what we can say about this is, there's a stronger suction peak, meaning cavity airfoil shows higher suction near the leading edge. Slightly lower CP across the midchord and enhances the transonic flow. And when it comes to the effects of the trailing edge, steep adverse gradient indicates potential or vortex separation within the cavity. There's a vortex forming within the cavity itself. Then there's lift enhancement. Higher pressure on lower surface improves lift generation. And lastly, aerodynamic advantage. Better suction and pressure recovery suggests superior lift to drag ratio or performance. So to conclude this study, CFD validation has been done and matched closely to NASA's experimental results for the blunt trailing edge airfoil. Optimization impact, basically that the trailing edge cavity reduced drag significantly, especially near the critical Mach number of 0.74. And it also improved the efficiency by 15.95% without a noticeable lift penalty. And the flow insights, the contour plots also confirmed favorable shock positioning and reduced wave drag. Thank you. That's the end.
Thank you, Mr. Nasik. Now we would like to open the floor for questions, and we encourage everyone to be active. Any questions, anybody? Okay, so it seems there are no questions. So now we'll move on to our offline presenter, who is.
So I would like to call upon Ms. Bhavya Saxena, Amity Institute of Aerospace Engineering.
Good evening, sir, and my colleagues. Today I'm Bhavya Saxena, and I'll be presenting my paper on CFD study on the effect of cant angle on winglet efficiency. In this presentation, we'll be covering the introduction, literature review, objective, methodology, results, conclusions, and the references. So first, let me introduce why winglets are so necessary. So aircraft efficiency is strongly influenced by induced drag, which is caused due to the vortices that are formed at the wingtips of any aircraft. And these vortices are really intense and may cause a downward component of velocity, which is the downwash, and it decreases the lift. So for this study, we have conducted it at a Reynolds number of 6 lakh, which is the cruise Reynolds numbers for level flight or small aircraft or UAVs. So for literature review, we have studied various reference papers, and what we found that is that the cant angle strongly affects the L by D ratio, and optimal angles depend on airfoil as well as the flight conditions, which means that for one particular flight condition and for one particular airfoil, there will be an optimal cant angle, and that cant angle may not be the best for any other airfoil. So winglets were introduced by Whitcomb in 1970s in NASA aircrafts, and it was inspired by bird feathers, which are usually seen a little bit upturned when they are flying. So that gave them the idea for to introduce wingtip winglets. So in this study, we used CFD to isolate cant angle effect. We only studied this one parameter so that we can understand it perfectly. And we used a fixed winglet height or area, and we varied the cant angles. So we analyzed three components, CL, CD, and CL by CD. The objective was to optimize cant angle for cruise conditions. So this was our computational domain. We used NACA 4412 because at subsonic regions, it has really good lift characteristics. We used Mach number 0.292, just below the compressibility Mach number, and the Reynolds number was 6 lakh. We used the turbulence model K omega SST. It combines the best qualities of K omega and K epsilon. And we used steady state pressure based solver. We tried using density solver as well, since the Mach number that we took is at the very border of the compressibility Mach number, but using density based solver gave us diverged results. This is the geometry of our wing. We used the root chord of 95 mm and tip chord of 25 mm. We used 5 different types of angles at 0 degree, 15 degree, 30, 45, and 60. We used unstructured tetrahedral mesh because it was far easier to implement, and it also gave us certain somewhat reliable results. And we conducted the mesh independency for this as well. We created an inflation layer around the airfoil to ensure that we can capture the force flow correctly. So for the grid independence test, since it's an unstructured grid, we created multiple grid points, and for the one that for the minimum number of elements where we got a stable result, we took that for the for further studies. So for our boundary conditions, we use pressure far field on the curved part, and symmetry at the middle of the at the wall side of the airfoil. For airfoil, we took no slip wing, and we used ideal gas and Sutherland viscosity model to take into account any temperature change. So we validated it using the reference data, and the same data that was used for the validation, we simulated it with our computational domain. It is somewhat different. There were no edges here, no vertices, to ensure that there is no recirculation in the computational domain. We all tried to analyze it with different types of viscosity models: SST K omega, standard K omega, reliable E epsilon, standard E epsilon, and Spalad LMRs. So for that, we found out that SST K omega gave us the best results, the closest results. So we continued with this computational domain. So these were our results. For the drag, we can see that at the lower cant angles, we got the peak of the CD, and it decreased until 40 degree angle, and then it continued to increase. So we can see that at around 40 to 60 degrees, where we kept increased the cant angle, it also increased the parasite drag. So the reduction in induced drag was far less than the increase in parasite drag. So this wasn't very efficient at higher angles. So at lift, we see that we get the peak at 15 degrees, and it decreases after 40 degrees. So again, because the CL by CD ratio is really low at higher angles, 40 to 60, it means that at higher cant angles, there is more skin friction drag. So as a result, after combining both the parameters, the CL by CD ratio tells us that at lower cant angles, like 10 to 20 degree, we get better results for a higher Reynolds number. And for higher cant angles, the result is not as great. So for flow visualization, this is the vortices that can be observed at the winglet. We can see that at the 15-degree cant angle, which was the best configuration for this airfoil and flight condition, we got narrow symmetric waves and stable vortices. At 0-degree angle, we can see that the waves are quite broad and there is a high drag. At 60-degree, we can observe strong vortices, and thus that reflects disturbed flow. So with the study, we can conclude that cant angle must be optimized for each airfoil and flight condition. The best efficiency that we got was at 10 to 15-degree cant angle, and higher angles reduced performance due to vortex intensification. So our suggestion is to use adaptive or variable cant angles for different flight phases. These are the references that we used for this paper. Thank you.
Thank you, Mrs. Bhavya. Can we now open the floor for any questions from the audience?
Can you show the plot? Plot I want to see. So you have not obtained the favorable results in any way.
No, sir. According to our study, if you see the CL by CD ratio.
CD by CL or
Yes, sir.
CL by CDL?
Yes, sir.
This is CD by CL.
No, sir. This is CL by CD. Oh. So that is a mistake on my part. It's a CL by CD ratio curve. I'm sorry, that's a mistake. That's a typo. Yes, sir.
Previous plots you can show. What is that?
Yes, sir.
You should have also compared it with without that winglet, I think. Without winglet, what it was giving, and with winglet, what it is giving.
Yes, sir. Without winglet, it's giving.
You have to plot in the same graph.
Okay, sir. Okay, sir.
Because it doesn't make any sense of this figure.
Okay, sir.
Without any comparison.
And any experimental validation done?
No, sir. We did not get any experimental data for this paper.
So CD, you can see it is increasing.
Yes, sir. CD is increasing because there is an increase in parasite drag as well. Because when we are increasing the cant angle,
it could be compared with without a winglet, basically.
Okay, sir.
How that looked, whether it is giving a higher or a lower drag coefficient compared to that.
Sort the some visualization kind of without the
Yes, sir.
this graph.
See.
But no, this is a qualitative.
Okay, sir. Quantitative.
Otherwise, there is no sense of any things. Always people have to what level you have to improve it. You claiming like this doesn't make any sense. It must be so in form of graph where you have to be explain it. This is the reason.
Anyway, 4412529
Yes. Yes, sir.
irrelevant to have this winglet in that type of thing.
So actually, I took this case for small aircrafts or UAVs. So for cruise conditions, yes, sir.
But still you understand.
Yes, sir. I understand.
You have to improve your presentation.
Yes, sir.
You have to put the things more systematic.
Okay.
I think we have one question from the audience as well.
So I just want to ask, like, how you will implement the variable cant angles? Like, should we do the variation during the flight, or we can go for an optimized fun angle, or
No,
from
see,
takeoff to the cruise to landing?
yes, yes. So that is what is being suggested right now. There is a technological, we need more technological advancement to be able to implement it fully. Right now, if we introduce variable cant angles in any aircraft, it will increase a lot of weight. So we need something more sturdy that can hold the winglet at that angle, and we can change it during flight. So that is still required.
Okay. If there are no further questions, we would.
I have a one question. You only take the 0, 15 and 60.
Yes, sir.
In between, you have not taken any.
Sir, I wanted to show a bit of comparison
No,
study.
I'm just asking you. So you choose only these three angles.
Yes. 0° to show the one case without any winglet, 60° because that is the worst case, and 15° because that is the best case.
But how can you claim it? Maybe a valid, maybe a best.
Yes, sir. Yes, sir.
Maybe a 16 is 20, 30, 20 is best. Yes. That's why the range 15 to 60 is very, very high. Yes. So you have a in middle 15 to 30. Then may you understand the trend.
Yes.
Clear?
Thank you, sir.
Are there any? Okay, wait. We would request the felicitation team to kindly felicitate Ms. Bhavya Saxena for their research paper presentation. We maybe have a round of applause for the same. Thank you. All right, now we will break for high tea and resume the session promptly at 4:45. We encourage all our esteemed guests to take this opportunity to stretch, network, and engage in meaningful conversations that may foster future collaborations. We trust you're enjoying the proceedings thus far, and we look forward to your continued curiosity and thoughtful engagement with the papers being presented. Thank you. We shall reconvene shortly.
Can we start, sir? So, welcome back to technical session 4. So, let me introduce to the rules again. The total allotted time for paper presentation is 10 minutes. The first bell will ring at 5 minutes and the last one is at 8 minutes. We request you to complete your presentation within 2 minutes after the last bell rings, after which we will continue to the floor for the question and answer session for 2 minutes. So now I would like to call upon Nasik Mohammed Mazrooq Khan from Amity Institute of Aerospace Engineering.
Yes. Am I audible?
Yes, you are audible. Could you please present in slideshow? Yes.
Shall I start?
Yes, you can start.
Okay. Right, so my name is Nasik, and I'm here to present again on behalf of my team on another topic we worked on, which is closely related to the previous one I just presented. This is on the parametric optimization of the SC20710 supercritical airfoil's trailing edge thickness for enhanced aerodynamic performance. So, another introduction into this topic. Supercritical airfoil is used to delay or increase the critical Mach number of the airfoil itself. That makes it efficient for use in transonic flight. And the key features of any supercritical airfoil is the flattened upper surface, larger leading edge, and an aft camber. So, when this airfoil was new, the past tests they used limited precision in trailing edge thickness. And now that we have CFD, we will be doing this once again. So the objective of this study is to reinvestigate this airfoil's trailing edge effects using modern CFD. The trailing edge, the thickness of the trailing edge varied from 0.68 to 0.72% of the chord in steps of 0.01%. That's how we did it. And the focus of this is drag reduction across subsonic and transonic regimes. This was again validated against some experimental data provided by NASA in one of their studies for accuracy. And this aims to identify Mach-specific optimal configurations. So, once again, how did we go about this? We ran a 2D simulation of this airfoil using ANSYS Fluent. We referred to an experimental data adapted from literature in order to validate our results, and our methodology covers the geometry modeling, meshing, and the CFD simulations. So first things first, this is how the geometry modeling looked like. We created 5 different geometries, each with a slightly different trailing edge thicknesses. One with 0.68% of chord, 0.69% of chord, 0.7% of chord, and so on up until 0.72% of chord. And these were labeled A1 to A5 respectively. And if you notice, once again we went ahead with the cavity itself. This is us changing the thickness of the cavity to see what effect that has. So now onto the meshing. We created a C-type mesh for better near-wall control, and the domain size was 7500 mm for the C-grid radius and a 15 by 15 rectangle after the airfoil. And the boundary definitions were inlet, outlet, airfoil, and walls. This is what the mesh looked like a little closer to the airfoil. And yeah, moving on to solving. We used the pressure-based solver activated with the energy equation. SSTK omega turbulence model, and the air was modeled as an ideal gas, to which we assigned Sutherland's law for viscosity. Then the boundary conditions were pressure far field at the inlet and outlet, and the domain temperature was once again set to 322 as given by the experimental study, and the simulations were run once again from 0.6 to 0.84 Mach on steps of 0.02. And moving on to the results and discussion. In this section, the CFD results for SC20170710 airfoil with a 0.7% trailing edge thickness are presented and correlated with experimental data. Additionally, a comparative analysis of different trailing edge thicknesses of the same airfoil is carried out to assess their impact on aerodynamic performance. So firstly, I'll show you the validation before jumping into these results. The experimental study is what's denoted by the blue color line, and the red color is what we got through CFD. This was on the 0.7 thickness airfoil. So the key flow features like shock formation at Mach critical, which is roughly 0.72, and drag rise at 0.76. They confirm accurate transonic behavior prediction. CFD versus experimental results for 0.7% trailing edge airfoil A3, that's A3. They also show good agreement with an average error of about 14.3%, validating our simulation model. And when all these airfoils were compared and plotted on the graph, this is what the graph looked like. Now, I will discuss this graph in fragments. Firstly, we'll discuss before the Mach critical. That's 0.6 to 0.72. So yes, zoomed into that section of it, this is what the results look like. So the airfoil A4. This is by the way, this is CD versus Mach number. So yeah. So the airfoil A4 records the highest drag in the subsonic Mach range. That is the purple line. It's all color coded over here. Each line equals to one airfoil. And airfoil A2, which is a 0.69%, it shows the lowest subsonic drag, outperforming the reference A3 by 2.8%. 2.87% in drag. And post-critical Mach number, that's 0.72 to 0.84. This is what we end up with, and in between the Mach critical and Mach drag divergence, that's 0.72 to 0.76, airfoil A3 shows the lowest drag, outperforming all the others in the transonic regime. And then beyond Mach drag divergence, that's beyond 0.76, A4 becomes the most efficient with a smoother, more linear drag raise, while A3's drag increases a bit more sharply. It's subtle, but it's visible on the graph. And around Mach 0.818, A2 regains its low drag behavior, and A5 remains least efficient across the entire across all the Mach numbers we simulated for, due to its thick trailing edge. At this point, we're getting flow separation at this airfoil. Therefore, there's going to be constant drag, significantly higher than the others. So to conclude this study, the trailing edge thickness, when varied, it will significantly affect the drag in both subsonic and transonic regimes. Mach critical and Mach drag divergence in our case remained more or less unchanged, because these values are dictated by overall airfoil geometry, not just the trailing edge. So in the subsonic regime, the best performer was the A2 airfoil, 0.69% of chord thickness at the trailing edge. And the worst performer due to its highest drag was A4. Now, in between critical and divergence, A3 demonstrated the best performance, and beyond Mach drag divergence, A4 showed a gradual drag rise, indicating stable shock boundary layer interaction, making that the best performer for this section. And A5 consistently exhibited the highest drag throughout every Mach number that we simulated. So the optimal airfoil is regime specific. So for subsonic, the optimal airfoil we found was A2, and for transonic, A4. And yeah, that brings me to the end of this. Thank you. If there's any questions, please feel free.
Thank you, Mr. Nasik. If there are any questions, we encourage the audience to participate. It seems, can the tech team please provide a mic to the gentleman there?
So the graph which you showed, the comparison of different airfoils, can you open the graph? Yeah. So basically what I can see, as you also pointed out earlier, that when your Mach number is reaching higher Mach number, your data is deviating from the experimental results, right?
Sorry.
Hello. So maybe it could be because you have used a pressure based model. Why you have not used density based? Maybe it will be more accurate with the density based.
Yes, actually, we plan on doing more studies with this, and that's one of those refinements we have decided to make in the future.
Basically, this can be a suggestion, because at the higher Mach number, as we are entering the transonic region, we should prefer density based more, because as I can also see your validation graph also, it is also deviated from the experimental data. So you can try with the density based, and you can see like if it is better or not. So,
Yes, my team and I will continue this study, and that's one of those refinements we've already noted down. So
sure.
Thank you.
So this is in similar fashion you pointed out. Your deviation is quite large from the experimental data. That critical Mach number has almost reduced to 0.65, 0.85 to 0.6 or so. So that is inefficiency it is showing. The model you are using is not quite okay, I think. So the suggestion, I think, same density based model you should prefer.
Yes, sir, we will.
Or you have any other reason for the deviation, the validation you have made with the experimental data? Any reason you want to give for the deviation?
The first reason, as you said, sir, it's because we used pressure-based in this. We should have gone density-based. The second reason, I believe, is because it's transonic. It's going to be quite unpredictable. By default, there's going to be some error. Added with that, we have this slightly larger error than we anticipated.
No further. I hope there are no further questions. Okay, so now we'll be moving on to the next presenter.
So I would like to call upon Chobu Shiva from Amity Institute of Aerospace Engineering to come and present his paper. Yes, sir, your slide is visible. Could you please present in slideshow mode?
Yeah. Am I audible?
Yes, you are audible.
Good evening, everyone. My name is Shiva, and today I'm going to present on the topic optimizing performance and shockwave mitigation in mixed compression supersonic air intake on behalf of my team. This is the block diagram for supersonic engine, in which you can see that here we have the supersonic mixed compression air intake. What does that mean? Means like we have external shock and also internal shock forming inside the air intake. So by utilizing these two shocks, external and internal shocks, we were able to like the engine will be generating the required pressure for the combustion chamber. So on this topic, we have done literature review, which include when using cold deflection at 1 to 2 degree deflection at Mach 2.2, the flow is stabilized and shock is also reduced, and it outperformed the bleed system when compared to methods like a bleed system. Cold deflection is improved, has better results, and and it also gives the 3% pressure recovery when compared with other methods. And also we have done research on the RAM vein microvortex generators. These microvortex generators are shown to improve boundary layer mixing and reduced upstream downstream suppression by up to 24%. And these are the different similar literature we have done. So moving on to the objective, our objective is to improve the total pressure recovery and reduce flow distortion at the aerodynamic interface plane. So how we have done this is that by employing the vane type vortex generators to generate stream-wise vortices, which would energize the boundary layer. And also we aim to mitigate the shock-induced boundary layer suppression caused by shock-wave boundary layer interaction. And also we have selected the vortex generators with the desired dimensions to control the shock stability. So coming to the methodology, this is the diagram of the geometry we have taken for this experiment. This geometry has been taken from this Sudipta's paper, and here we can see that the first ramp has 7 degree 7 degree deflection, and the second ramp is at 14 degree deflection, and the total area of the intake is total length of the intake is 15 mm. So and beside when we move on to the figure 2, this is the grid generated for the present computation at 4 degree cold deflection. So we have used structured 3D mesh for the computation. So, and this is the dimensions for vortex generators. Here and the figure 4 shows the structured grid we have generated for these vortex generators. We have taken these vortex generators at the first diffuser. So which we are going to see in the next slide. So this is the timeline for the simulation. Actually, not the research part. This is simulation part. So what we have done is first we have designed the geometry. We have done the machine and refined the machine, and with that we have done the independence test. And after that, then the boundary conditions for density based solver, as we are simulating at Mach 2.2, which is a supersonic regime. and the energy equation is on, and the ideal gas, we have taken ideal gas as ideal gas and Sutherland viscosity and explicit solver. So these are the works we have done previously before deciding the vane vortex generators. So what we have used is like we have used heat source technique or at the air intake, and we haven't got the satisfactory results. We also used bump at the second ramp as a heat source. That also we haven't received any satisfactory results. And third, we have used bump at the second ramp as heat source and air injection. Like we have used three different methods. Like we have used it as a heat source and also air injection to the opposite flow, and the results are not satisfactory. So at final place, we have decided for vane vortex generators at the diffuser on first diffuser. So we got the desirable results for our experiment. So this is the gradient dependency test. This is the graph for pressure ratio. As you can see that we have generated mesh for three different mesh counts. That is at 4 lakh count, 6 and 7 lakhs. And when you look at the graphs, it's almost identical. There was like only slight deviation has been occurred for a medium mesh count. So, but rest of all the gradient dependence has been passed. So, and this is the validation. So we have taken the reference computation from the reference paper we have taken, and the red line in the graph is the present computation we have used, and the blue dots are the reference computation. As we can see that the deviation is not that high. So we have proceeded with the experiment. So these are the contours for Mach and density. So on the left side, we have contours for a base model without any back pressure, and on the right side we have this for on the right side is for case one, where we have introduced back pressure. So when we introduce back pressure, like on the left side, you can see there is no normal shock forming at normal shock or boundaryless suppression. Normal shock forming at the exit of the supersonic air intake. But when we are when we are providing the back pressure, which is 5, ratio of 5, so the normal shock move to second diffuser. So and so this is the graph for the previous contours I've shown. As you can see that when we have introduced back pressure, the graph, the black one, the case one is the graph with the back pressure. So the pressure ratio is increasing after the first diffuser. This indicates the presence of normal shock in the supersonic air intake. So this is Mach contour on the ramp surface with and without vortex generators. So we have considered 4 cases. The first case is on the top left, which is without any vortex generators. So as we can see that the velocity, we can see that boundary layer separation is very strong on in the case one. And when we introduced vortex generators, one pair of vortex generators in the second picture, which is on the top right, you can see that the flow is slightly energized. These vortex generators are introducing high momentum flow to the low momentum flow. So you can see that the flow is slightly energized, and we can see that separation is delayed. When we come to case 3, which is on the bottom left, we have introduced 2 vortex generators. In this case, the boundaryless separation is very much reduced. As you can see that in this Mach contour, it's very much reduced, and the flow has been energized. And when we move on to case 4, we have
wrap it up kindly.
Sure. We have introduced 3 vortex generators, and in this case, what happened is the flow is over energized. but it is better than the case one, where we haven't used vortex elements. So this is the pressure distribution over the ramp and the pressure distribution over the curve. So when we look at the graph between 0.4 to 0.6 location, for the case one, the pressure ratio is there is a pressure region over the in 0.4 to 0.6 for the case one. This indicates that the shock has been that the shock is very high, and for the if we move on to other cases, the shock like the pressure recovery ratio is been high, becoming high. So, and this is the total pressure distribution at various span-wise locations. The first graph is case one. The other.
Really try and move to the conclusions slide since we are tight on time. So
Sure. This is the mark distribution at exit plane, and this is the values. These are the values we have got. So as we can see that in case one, the pressure recovery is at 0.5, and the case two is 0.4. So if we consider all these values, the highest pressure recovery is at case three, which is 0.6. But at the same time, at case three, the flow distortion is also high. That means what happening is that like these vortex generators are introducing the disturbing the flow so much that the flow is very much distorted at the exit plane. So what we have concluded is that uh, the case 4 is the optimal configuration for this experiment, as it has the balanced pressure recovery and balanced flow distortion compared to the other cases. So uh, that's all. So, and these are the references I've used for this experiment.
thank you, Mr. Shiva. Are there any questions for? No. Okay, no questions. So we'll be moving on to.
With it, I would like to tell you that please be on time. Like the total allotted time for paper presentation is only 10 minutes, and the first bell will ring in 5 minutes, and another one is at 8 minutes. So try to wrap up in another 2 minutes. Please be on time.
Okay, so now next presenter is Mr. Karan K. Das from Amity Institute of Aerospace Engineering, Amity University, Uttar Pradesh, Noida. So can he please share his screen and present and put it on slideshow?
Yes, please. Yes. Is it fine?
Yeah.
Okay. So good evening, everyone. My name is Karan K. Das. So I'll be presenting on my paper, the computational study on the performance enhancement of three-dimensional supersonic air intake through the implementation of bump surface, and this was with the help of my professors Neeraj sir, Navin sir, and Rajesh sir. So the contents that I'll be covering are these: introduction, literature survey, literature review, research gap, and objective, methodology, results, and conclusion, etc. So as for the introduction, so supersonic air intakes are critical for air breathing engines like jets and scramjets. Their function is to efficiently compress and guide the supersonic flow before combustion. So some basic challenges is managing the shock boundary layer interaction, which reduces efficiency and may cause flow separations. So after some literature reviews, the research gap that I found was that despite extensive studies, limited research was explored on the surface mounted bumps in three-dimensional mixed air compression. So this research addresses the use of surface bump at particularly supersonic air intake, which is at a 4-degree cowl angle. So the objective of my research paper is to investigate the effect of surface mounted bump on boundary layer interaction in supersonic mixed compression intake, to study the influence of different back pressures, and to evaluate total pressure recovery and exit flow distortion. And these are the parameters that I'll be covering: total pressure recovery and the exit flow distortions. So for the experiment, I have taken this model. This model was taken from Sudeep Das experiment, and this model is for operation at Mach 2.2, and it is at 4-degree curved angle. And the bump surface that I'll be including is below. and it is placed at the second diffuser. So this is the grid setup, and this is the central plane mesh for the 3D model. And I have used a structural grid for this experiment. And the conditions, free stream conditions, are as follows. These are all the conditions for the MAC 2.2. And the boundary conditions are this. So pressure inlet, pressure outlet, and I have the wall condition and as well as pressure outlet at the exit. So the grid independency test has been done, and I have done at different nodes, and I have taken medium node for efficient or basically easy computation. So coming to the results, so first I have experimented on the computed on the base model without any bump surfaces, and these are the result at back pressure 0, 3, 4 and 5 respectively. And these are the MAC contours basically, and we can see that as we kept on increasing the MAC contour, the flow separation is ominent. And based on the contours or based on the results, I have plotted the total pressure recovery of the same, and the black line showing is the case for the 0 degree, and we can see that all the other cases have less total pressure recovery and the minimum for BPR4. And the same numerical values I've also mentioned provided at the below. So here we can see that the most pressure recovery was 0.8 at the BPR 0 case, and flow distortion was this one. And after the providing back pressure and all, the flow distortion was increasing for 3 and 4, and pressure recovery was reducing for 3 and 4, but somewhat it was better in 5, but it was less than for the base model. So my objective was to improve this results. So after I have implemented the bump in such a way that it is placed at the second diffuser. So after implementing, I run the case for BPR3, and the flow MAC contours are this, and the pressure ratio plot have been plotted, and we can see that there was a change in the location of the shocks, and this is the total pressure recovery. So for the base model is the black line, and the red one is the modified model. And I have also plotted given the numerical value, and we can see that the pressure recovery reduced by 1.01%, and the flow distortion increased by 8.9%, which is not basically not ominent for this. Basically, we can say that surface bump was not much effective for this case. So next I went for BPR 4, and the same MAC contour and the pressure ratio plot are this. And for the total pressure recovery, when I calculate the values and plotted, I saw that the total pressure recovery increased by 9.7%, 78%, and the flow distortion reduced by 1.18%, which was the most optimum result that I got. And later I also checked for BPR 5, and the same results which I plotted, I got the result that the total pressure recovery reduced by 12.9%, and the flow distortion reduced by 12 point sorry, the flow total pressure recovery basically reduced by 12, and flow distortion reduced by 12. So it was good for the reduction in the flow distortion, but the total pressure recovery also reduced drastically in this case. So for conclusion, I can say that the bump surface is a promising passive flow control technique. It is mostly efficient at moderate back pressure, basically BPR 4, improving both recovery and distortion. So rest of the case, there was not much efficient. So the future work that I'm going for it are that some, if possible, some experimental work on this, and to include more bump surfaces at different locations. Also, I'm thinking of providing some air injection also along with the bump surfaces to check whether the flow parameters improves or not, and for also to study them at higher MAC numbers. So these are the references. Thank you.
Thank you, Mr. Karan. Are there any questions?
Karan, your simulation is 2D or 3D?
It's a 3D.
But you did not show any third dimensional effect on this.
Okay, so I basically showed the central plane effects only.
But other plane, what is the effect?
Other planes, there was some flow basically at when there was no bump surface, so the flow separation was very much. So after the bump surface, some flow separation reduced and the flow circulation improved. So I did not include in, so my mistake, sorry.
And then you have to be show the some contour on a normal plane of the flow. Then it will see that this is the 3D simulation.
Okay. Sir.
Anyway, so you claim that it is a good bumpy surface, good probe total pressure recovery. No?
Yes, it is prominent at 4 BPR 4 basically, but it can be much more. I am currently working on air injection also, and I am seeing much more improvement in that case also.
What is the configuration of your bump on a surface? In geometry.
So geometry here I have. So total length is 30.
Please explain it.
Yeah. So the total length is 13.5 mm, and it is basically a conical bump. So which I have placed, semi-conical bump, which I have placed at the second.
So conical bump is kind of a more sharp, na?
Yes, sir. I have that way. I have given a blunt portion over here. A 4 mm basically blunt surface I have given, and at the tip also.
Okay.
So in the previous paper, bumps were ruled out and VG were favored. But you have shown improvement with the bump. That is contradictory, basically. How do you clarify this?
Sir, I didn't know about the ruling out. I implemented the bump surface and I got the results, and based on the results, I don't know what you can say about that.
Okay.
Any other question from audience?
Okay, so we'll wrap that up. And now
I would like to call upon Shizan Adil Gamet, Trisha Shailash Salvi from Department of Aerospace Engineering and School of Engineering and Sciences, MIT Art Design and Technology University, Pune.
Yeah. Am I audible?
Yes, you are audible.
Yeah. Good evening, everyone. Myself, Trisha
Put your slide on slideshow.
Yeah. Good evening, everyone. Myself, Trisha Salvi, and I'm a final year student at MIT DT University. I'll be presenting our work today alongside my teammate, Shazan Khamet, and under our guidance of MD Gulam Sarwar, Debrata Sausa, and Dinesh Kumar Bajaj. Our presentation is on CFD simulations of lid-driven cavity flow with hybrid replacements for various Reynolds numbers. Next slide. So these will be the contents that we'll be discussing. So to get us started, so if you look in the figure 1, the lid-driven cavity is a classic model which help us to understand the internal fluid motion. So while simple, the physics it involves is highly relevant to the things like the aircraft weapon bay, as you can see in the figure below, the third figure. So it shows that the aircraft is with its weapons bay is open. So when the air flows over that the open cavity, you get an incredibly complex physics. Like it involves turbulence, strong vortices, and also pressure fluctuation. So it can be seen in the figure 2 and 5. So this can create a lot of noise and vibration. So our goal was to how we can control these aggressive flows. So our solution was to check how the hybrid replacements inside the cavity to see can modify and improve the flow dynamics. Next slide. So this project is guided by the three main objectives. First is it was to validate our CFD solver to ensure its accuracy. So we did this by comparing our results, specifically the clean cavity results from the Huang and Lim's 2020 paper. We also performed a GIT, that is grid independence test. Then the core objective was to perform the CFD simulations on the hybrid rib cavity at 6 different Reynolds number to analyze and discuss its performance under the varying flow conditions. Finally, we aim to compare the results of our original clean cavity to our modified ripped cavity to check the effectiveness of the hybrid rib placement. Next. So this is the flowchart which gives an overview of our methodology. So following our initial literature review and objective definition, we began with the technical work with the geometry design and the meshing for the validation case. So this was followed by the solver validation and the grid independence test. Once we confirmed the accuracy of our computational setup, we proceeded to our main study. So this was followed by the CFD of the ripped cavity at different Reynolds number, and then the performance evaluation, which gave us the results and further discussions. So this slide shows the geometry and mesh for our computational domain. We used a structured grid for its accuracy. Then we show you why we picked the specific mesh. So we can cover that in the grid independence test slide. Now moving on to validation. So to validate it, we model the simple clean cavity and compared our predicted velocity profile along the center line, which was published with published data from the Wang and Lim's the paper. It was given in 2020. The black diamonds you can see are the reference data, and the solid blue line is our work. So you can see that a model is accurate and it predicts the flow physics inside the cavity. So it tells us that our computational tool is reliable. Next slide. So next we performed the grid independence test. We tested the three sizes and found out that 50 and 50 and 100 by 100 meshes showed strong convergence. So for the maximum resolution and stability, we chose 100 by 100, that is a fine mesh. So now I will hand it over to Shazan, who will take you through the test results we obtained for the ripped cavity.
Thank you very much, Trisha. Myself, Shazan, and I'll just quickly go through the results. So first, we can see the Reynolds comparison of the clean cavity and the ripped cavity on the Reynolds number 100. And the main observation which we found is that, is my cursor visible on the screen?
Yes, it is.
Yes. Thank you. So the main observation was that the primary vortex, there is a secondary secondary circulation region is generated on the right bottom surface, but it is small in size. It is with less intensity, and the number of secondary vortices is also less. As you can, if we will see that as we increase the Reynolds number, there are secondary vortices forming here also, and tertiary vortices on the top surface as well. But in the rib cavity, we are already achieving the flow mixing with the secondary vortices at the low Reynolds number. So as we can clearly see, as we are increasing the Reynolds number, the secondary vortices intensity is increasing, and another secondary vortices are generated on the left corner, whereas we are already achieving two primary vortices in the middle portion of the ripped cavity, which increase more mixing enhancement is done. And similarly, for the 1000, this is for the 1000 Reynolds number, this is for the 3000, and here we observe that the tertiary vortex has been formed from the which we got from the reference article, and we can see that there is a very much high mixing once the Reynolds number, the flow is reached near about 3000. And but after that, if you observe, after 3000, we do not see any significant change in the flow mixing, which we will again be seeing when we will be having a parametric study. And this one we also simulated with the Reynolds number 7000, but in the paper, they only simulated with 5 Reynolds number, so we don't have comparison for 7,000, but this is our results for the 7,000. So these are the 6 different dynamic pressure for the 6 different Reynolds number, where we can again see the similar trend which we are following, that we are not getting a significant change after Reynolds number 3000. That means a flow mixing can be done till the Reynolds number 3000, or we can also have a better flow mixing at rho Reynolds number, so that we don't have to apply more and more velocity. So this is the graph for all 6 different Reynolds number. This we have plotted on the geometry, on the center line of the geometry. If I carry to the geometry slide, so here there will be a center line, and on that the velocity profiles have been plotted. These are the vorticity contours, where we can see the intensity of the vorticity, which is very much larger in Reynolds number 7,000, and after that in the after 3000 we can see the vorticity value has been decreased. So if you see it was, sorry, it is increased, but it is not getting much changed. So if you see 2.13 into 10 raised to 6, 2.13 into 10 raised to 6, and again 2.13. So after 3000, there are no significant change in the vorticity intensity as well. So this is the vorticity again on the center line, vertical center line, as well as the horizontal center line of the geometry. And this is the parametric study which we have done, where we can see these are the maximum velocities which corresponding to the Reynolds number, and these are the maximum dynamic pressure we have achieved on the corresponding Reynolds number. And we can see that after Reynolds number 3000, there are no significant changes in the vorticity intensity. So we would like to conclude that after studying the lid driven cavity problem, with the rib placement, with hybrid rib placement, all the three stationary walls, we can see that we can have an enhanced flow mixing with the low Reynolds number, or you can say till up to Reynolds number 1000, or we can also achieve. We can also compare it for Reynolds number between 1000 and 3000. It was not shown in. It was not. We didn't have any comparison. We didn't have any reference work for that. So that's why we did go for any Reynolds number between 1000 to 3000. But that can be implemented in the future. Also, a 3D simulation with different turbulence modeling can be achieved to predict more intensified, more quantified work.
Please wrap up.
Yes. So these are the reference paper which we have referred. Any questions, please feel free to ask.
So what is the motivation of this work? Why you are doing this work?
So our motivation is like the application which we showed in the first slide, where we have this is the weapon bay. We also have landing gears open. We have a type of a cavity which is covered from all the 3 other side, and one side is open. Another example, this is the figure. This figure is nothing but the scramjet combustor, where we have introduced a cavity for the enhanced flow mixing. This can be found in this reference article. So for that, yes.
And for the tangent model, you use the LES method?
No, sir. We have used RAN simulation only. The LES is for the future work.
So in RAN simulation method, how can you have to be close to the viscosity by which model, turbulence model?
Sir, SSTK omega.
Why?
Sir, it has a better efficiency for the near wall function, to capture the near wall. That's why we also added the inflations on the near wall, because we wanted to capture how the fluid.
Try to understand. You making a bump which is not a sharp. One thing, it is a blunt. So definitely more and more vertex is formed, more and more mixing is formed.
Yes.
But in a real, you know that there is a lot of loss of pressure is also. So like you are showing somewhere there is a cavity, there is a flow, so mixing of something. Is it appropriate there or not? It is now questionable.
Okay.
Clear? So let's you have to be a compare with the experiment and really they want to be make a cavity kind of whatever the result is, so that are predictable. That is not something is novel. Definitely making a bump type of any rectangular type of extended kind of these things. More and more vertices form, more and more mixing. This is the predictable. Nothing is clear. But
Yes.
other side, yeah. So anyway,
Which length or how are you calculating Reynolds number and where it is applicable?
So this we directly took from the reference paper. So they the gap which we identified in the reference paper, that they simulated on the 6 different Reynolds number with the obstacle in between. So we tried instead of keeping a bigger obstacle in between, we tried to modify the wall itself. So it will act as an obstacle only, but in a different way. So that's why we wanted to analyze the qualitative analysis. We wanted to quantitatively analyzed.
and your case is a 2D, na?
Yes, sir. Right now it's 2D.
Thank you. You may close your presentation.
Thank
Our
you.
next
Thank you, sir.
our next presenter is Jitesh Gokul V from the Department of Mechanical Engineering, Amrita Vishwavidyapitham. May please share your screen and put it on slideshow.
Am I audible?
Yes, you are audible.
Okay. Good evening, everyone. My name is V. Jitesh
Please
Gokul.
put it in slideshow.
Oh, it is in slideshow.
It's not on slideshow yet. Maybe reshare your screen if that helps.
Okay. Is it in slideshow now?
No, it's not in slideshow.
Wait, I will share.
You can
Okay, you can
continue
start.
like that. It's okay, no problem. You can continue like that.
Okay. Good evening, everyone. My name is V. Jitesh Gokul. I'm a mechanical engineering student at Amrita Vishwavidyapitham, and our professor is Karthik. Yes. Our research title is about temporal instability of liquid emanating from centrifugal atomizer. The contents which is discussed here are introduction, objective, methodology, results, and conclusion. So, centrifugal atomizers is a widely used process for generating sprays in industrial applications such as coating, spray drying, and fuel injection. In a centrifugal atomizer, liquid is supplied to a spinning disc or cup and is flung outside by the centrifugal force, forming a thin liquid film or jet that ultimately breaks into fine droplets. Understanding how this liquid film breaks up is essential for optimizing the atomizer's performance and the efficiency of the spraying process. In our study, we use a linear stability analysis to investigate this breakup mechanism. And we also examined how factors such as fluid viscosity, surface tension, liquid flow rate, and rotational speed influence the stability of the jet. By identifying key stability parameters such as temporal growth rate and breakup frequency, we aim to improve the prediction and control of atomization behavior across a range of fluids. The temporal growth rate characterizes how quickly a small disturbance to the jet grows over time, while the breakup frequency corresponds to the most unstable oscillation mode of the jet.
Excuse me, sir.
Uh,
Sir, your slideshow, your slides are not changing. You are on the first
I'm
slide
just changing it
itself.
now. I'm just changing it now.
Okay.
Understanding these parameters helps in designing atomizers for specific fluids and operating conditions.
Just to clarify, you're still on the first slide, like your original first phase slide. It's still there. It's
No,
not.
I have changed my slide.
No, so it's not reflecting on our side. As for the meeting, we'll present for you if you need us to.
Can I share it as a whole screen?
Your screen
Wait,
is
wait,
shared,
wait.
but
Wait, we'll present for you. Just wait.
Okay, okay, thank you. Can you go to the fourth slide?
Wait.
one second. So we are just getting a paper ID and presenting the required presentation. Just bear with us for a second.
Could you just stop presenting your screen?
Stop. Can you go to the objectives?
What slide? Is
Yes.
this? Okay,
Yes.
continue.
So our primary objective of this research is to develop a theoretical model that explains how a liquid jet breaks up in a centrifugal atomizer employing linear stability analysis, and it can ultimately support the design of more efficient centrifugal atomizers. Can you go to next slide? So our methodologies, our analysis begins with the incompressible Navier-Stokes equation and the continuity equation, which describes the base flow of the liquid jet emerging from the rotating atomizer. Next, we then introduce small perturbations to the base flow. Specifically, we add infinitesimal disturbances to the pressure field, velocity field, and the interface displacement of the liquid. The perturbed variables are expressed as the sum of the state base and small perturbation. Substituting into the governing equations, we get the equation which describing the disturbance evolution. These disturbances are assumed to be normal mode form, meaning that each perturbation varies exponentially in time and space. And under this assumption, you applied a boundary condition such as kinematic boundary condition and dynamic boundary condition, and we linearized this equation to get a dispersed relation, which is stated below the at the bottom. Next page. Next one. You are. So as results, our theoretical results illustrate how fluid properties and rotational speed affect jet breakup. A key finding is that for all fluids studied, the temporal growth rate omega I increases with the rotational Weber number up to a certain point and then decreases beyond that point. Here the rotational Weber number is the ratio of centrifugal inertial forces to surface tension forces. Can you go to the next slide? So, in a summary, our linear stability analysis shows that the jet's temporal growth rate initially rises with rotational Weber number and then falls beyond a critical point. This indicates that moderate centrifugal forces promote instability, whereas very high centrifugal forces don't know. Previous. Can you go to the previous one?
Next slide.
Previous one. Yes. Here, this indicates that moderate centrifugal forces promote instability, whereas very high centrifugal forces stabilize the jet. Among the fluids examined, water exhibited the highest breakup frequency. However, at very high Weber numbers, its growth rate was lower than that of the more viscous fluids. This occurs because at moderate Weber numbers, capillary or surface tension forces dominate water's behavior, whereas at very high Weber numbers, the strong initial stretching of the jet actually dampens the instability of water. Next one. In contrast, viscous fluids like glycerol reached its peak growth at a lower Weber number and exhibited lower breakup due to viscous dampening of disturbances. Glycerol's maximum growth rate was slightly higher than that of the water at the corresponding Weber number, reflecting its high resistance to the surface tension driven breakup. Whereas propylene glycol with intermediate viscosity showed the lowest breakup frequency among the three fluids but achieved the highest growth rate at the high Weber numbers. This suggests that an intermediate viscosity can maximize disturbance growth under strong centrifugal forcing. Overall, our results indicates an inverse relationship between viscosity. Next slide, can you go? Our results indicates an inverse relationship between viscosity and breakup frequency. Higher viscosity yields lower breakup frequencies. Viscosity has the opposite growth on growth rate. Higher viscosity can produce faster exponential growth of disturbances, And these insights clarify how inertia, surface tension, and viscosity interact during atomization. By understanding this interplay, an engineer can tune fluid properties and operating conditions to achieve desired droplet sizes and spray characteristic. Thank you for your attention. So these are the conclusions that we provided. Temporary
conclusion slide.
I've already spoke about this.
So now the floor is open for the questions. Any question from audience or from
the chair?
So, what is the application where centrifugal atomizer is used?
Sir, here we have considered for spray drying application.
Which slide show? Which slide?
First slide. No, like introduction slide. It is
Basically, you say that Basically, you say that the major application in industry is like a coatings, na?
Yes.
Huh?
Yes, sir. Yes.
Coatings. So we generally do the coatings. They have a very low viscosity fluid.
Yes.
Coating fluid generally very low viscosity.
Yes.
So and you have to do here the effect of viscosity is also, na?
Yes.
Viscosity, surface tension, and flow rate. I think flow rate does not affect too much, na? These two properties, viscosity, because automation depend on the Weber number, na?
Yes, yes.
So you did not plot which Weber number is a automation rate, all these things.
Sir, we used rotational Weber number. I have already stated.
Okay.
So, what are other atomizers? Are there any other atomizers also?
Sir, there are like pressure swell atomizer, effervescent atomizer, and many other like. In centrifugal atomizer, there are like many different types: rotating disc, rotating cup, and others.
Okay.
Okay, thank you so much, Jitesh. So now I would like to call upon Lisa Francis Souza from MUT Institute of Aerospace Engineering.
We ask the chair and everyone present in the meeting to bear with us while we get the slide up. So yeah.
Good afternoon. I am Lisa and I'll be presenting on the topic Introduction of Asymmetry to a Canonical Diamond Airfoil through a 10% thickness reduction in upper surface for optimization of shockwave structure and drag characteristics. So diamond airfoils are considered the ideal shape for supersonic flow. It uses wedge surfaces to manage oblique shocks and expansion waves, which are more better to manage in wedge surfaces. So in theory, we know that symmetric configurations, symmetric airfoils generate zero lift at the 0 degree angle of attack. But in real flows, there are situations, there are effects of shockwave boundary layer interaction and viscosity, which induce asymmetry to the airfoil and thus produce lift. So previous studies confirm that small geometric modifications can have a great impact on drag and lift in high Mach flows, with high velocity flows. So this study, our study, introduces 10% upper surface thickness reduction to a diamond airfoil, a canonical diamond airfoil of 1 meter chord. So the objective for our study was to see how upper surface reduction enhances affects lift, drag, and stability of a diamond airfoil. And then we conducted further studies on comparison of lift, drag, moment coefficients, and pressure coefficients. So we studied from the Mach range of 1 to 7, supersonic to hypersonic, and the modification was done of 10% reduction in the upper surface, and we used space claim for modeling and ANSYS fluent for simulation. So a baseline airfoil has 1 meter chord and 4 degree half angles, and asymmetric airfoil has 10% reduction in the upper surface. We did a structured quadrilateral mesh H-type topology, and our domain was 30 by 20, 30 by 25, and inflation layers with y plus value less than 1 for boundary layer resolution. So this is the geometry. You can see the 4 degree half angles in the in our diamond airfoil, and the left side is the original diamond airfoil, and the right side is the modified one, where we can see 10% reduction in the upper surface thickness. So this is the meshing. We did grid clustering in order to capture the flow physics closer to the surface of the body. We used density-based solver because the flow was supersonic and hypersonic, and SST K omega turbulence model was used because it captures flow physics better, closer and away from the wall surface. Boundary conditions were pressure far field was used for the inlet, as we can input our Mach numbers manually. Ideal gas was selected as air, and Sutherland's law was used for viscosity because it captures the temperature viscosity relation better. The free stream temperature was 300 Kelvin and turbulence intensity 5%. Output. Let's move on to the results. So we can see here the comparison of lift coefficients for the original airfoil, which is the blue line, and the asymmetric airfoil, a modified airfoil, which is the red line. So we can see there's a gradual increase in lift till Mach 5.5. It's not specified here, but it's we get a highest lift coefficient at Mach 5.5, and then when the flow transitions to hypersonic, the lift coefficient starts decreasing. And then we did the same for drag coefficients. So we can see that the average drag coefficient is lesser for the modified airfoil than the original one, and there's a gradual decrease in after the hypersonic transition, and there's a sudden peak, sudden rise of when the flow turns completely hypersonic. We can see we have done the same for moment coefficients. So the average moment coefficient was for original airfoil was 0.843 into 10 to the power minus 3, and for modified airfoil was minus 1.93 into 10 to the power minus 3, which is better, but it's also showing stronger nose down moment. And for the hypersonic regime, the moment coefficient values for both airfoils converge and remain small. So it's almost the same. So there is not much difference in the hypersonic flow region. We did the same with pressure coefficient distribution. So here we can see at 0-degree angle of attacks, pressure coefficient is nearly identical for both surfaces due to symmetry, resulting in no pressure differential and zero lift. This is for the original airfoil. And for the modified airfoil, upper surface, there's thinning in the upper surface, which leads to a positive lift. So the conclusion is asymmetry shifts the pressure centroid downward, enhancing lift without larger pitching moments. So here you can see the pressure contours of the original symmetric diamond airfoil and the modified asymmetric diamond airfoil. So we can see there's some reduction in the pressure coefficient on the upper surface of the modified asymmetric airfoil. So in conclusion, we achieved 28.08% of drag reduction in the modified airfoil, and there is efficiency, aerodynamic efficiency in the Mach number range of 1 to 5.5, and we have observed hypersonic limitations as performance drops after Mach 6, which starts from the supersonic flow to hypersonic flow transition. Overall, we observed that despite minor pitch instabilities, the modified airfoil remains effective. It's much more better than the original diamond airfoil. Thank you.
Thank you. May we start the questions from the chair and the audience?
The drag coefficient is more than lift coefficient. I have seen. You can see the plot. What is the lift coefficient that you have achieved? Yeah.
So this is the maximum value is at 0.007.
0.00023.
Yes, sir.
This is the lift.
It drops at in the hypersonic flow regime.
No, next slide you can see. 7.007. But drag coefficient you are in 0.0 something. This is in 0.00.
7 times she showed us 7 times increase at the peak.
Yes, sir. So there's a
so baseline is very close to zero. Original, what do you mean of original? Sorry,
yeah.
What do you mean of original here?
So original airfoil.
So original airfoil, what is the value of CL?
So it's not mentioned in this. I haven't. I don't remember the values.
The original is
yes, sir. Almost zero. It's almost zero. It's near
that
zero.
That is symmetrical at zero angle of attack. You say.
Yes, sir.
Left is zero.
Yes, sir. For the symmetric airfoil, because it's symmetric. Symmetric airfoils have zero lift.
The value I am saying that drag value is higher, then L by D ratio is going to be.
Yes, sir. We will conduct further studies on the L by D ratio. And,
how much L by D from this plot you can get?
See,
you are getting drag coefficient more than the lift coefficient. Is
yes,
that
sir.
okay?
No, sir. But then, sir, we are getting overall individual results are better. We will conduct further studies on this airfoil, and from that we can conclude about the more improvements in this.
Any other questions? No? All right. Thank you, Ms. Lisa. Now we would request the felicitation committee to felicitate. Can we have a round of applause? Okay, our next and final presenter for the day is Mr. Satyajit Panigre from Indian Institute of Technology, Bhubaneswar. Can you please step up to the dais for your presentation? The tech team will assist you with your getting your presentation up. Thank you.
So, hi, good afternoon. So, this is a small presentation on aerodynamic characteristics of aerofoils for flying wing or blended wing blended wing flying systems. So, when I started with the problem, so there are some 1600 number of aerofoils existing in the AF tool plotter in Google. So also I came across various papers where they have just studied a one single series aerofoils, and this simulation is not going to be in the ANSYS. So I have did so many studies in ANSYS, CFX, or Fluent, and in Star CCM, but this is going to be different, and very few are knowing about VSP. So I'll start with the introduction, objective methodology, and result and conclusions. So blended wings are mostly used to enhance the fuel efficiency and range, and also for endurance. So they are also providing a various number of mode of launch, like from texting to launchers. So challenges are also the blended wings are also longitudinally unstable, but we can overtake that thing by using the reflexed airfoils, which are having a unique afterthoughts. So which also slightly reduce the lift coefficient, but it's provide a better longitudinal stabilities. So there are few studies where they are discussing about the aerofoil selections, starting from ZMR 19 to 26 series, then MS series, then Epler series. So mostly people are using the NACA symmetric series, also NACA 2421 series, and they are mostly for the application that the various aerofoils, they are super in their own category. So mostly MH60 are a MH60 MS series are a MS series aerofoils are more efficient. However, the 60 series 60 number is very familiar, and the TS AGI 12 are 12 is used in our mix series far beyond. So here in the blended wing whichever I have taken, there I have neglected the inlet design in the VSP, which can be done, but it will take a long time. So I have gone for a blended wing body of 2.8 meter with a root core of 7.5, and there are four sections having the various taper ratios. And here I have used the vortex lattice model. So in which VSP toolkit provides beyond 150 vortex lattice model, the results are almost converged to the other ANSYS or star system models. But the disadvantage of VLM model, that's neglect the viscous flows, but it provide almost 80% similar data in a very short time, which is within 1-2 minutes. If the VLM plane are between 150 to 300, and it increases depends on the VLM planes. Similarly, also we can take the vertical planes. We can also take the horizontal planes. Here I have kept limited horizontal planes, and I did this simulation for 150, 250, 350, and 500. But mostly the UCAVs what they are planning nowadays for small turbine gas turbine are limited to 350. Also with a angle of attack variation from -6 to 18 degree, so that I can study various parameters to justify whether the aerofoil is good or not. So these are the different 5 aerofoils are selected with this baseline NACA 2412 series. So these are the drag I have taken drag coefficient, lift coefficient, L by D ratio, and the endurance factor, which is CL power 1.5 by CD, and also the coefficient moment of coefficient, coefficient moment, the moment coefficient. So the drag coefficient, Falcon and TSIG series are providing better results. However, the MS series and Epler are showing lowest, and MH and Epler series are performing very well. Coming to the lift coefficient, Epler series is having a very high lift coefficient. However, the Falcon, MHI, and TSG series are almost similar. So, coming to lift to drag coefficient, MH60 and TS12 series are having high coefficient. But here I focused on 5 degree because we are giving the aerofoil setting angle. We are giving with some angle of attack to provide a better lift. So Falcon and other are giving the same L by D ratio. Falcon and TSIG series are also giving, the other series are giving the same almost same lift to drag coefficients. Coming to endurance, Epler is having a very good endurance, but MS series is high efficient. Coming to the fifth angle of attack, this is the coefficient of movement. The Falcon and Epler are having higher value compared to the other three, and they are almost similar, the MH and TSI series. So this provide very good data for the upcoming few 5 to 10 years, when we are focusing on our mass production of UCAVs to select a better to select a good aerofoil in the range of 300 to 400 km per hour for a small gas turbine. So the key outcomes are MS60 and TSAGI 12 are having very good are having high efficiency for blended wing body, and however the L by D ratio is maximum for the MS60, which is almost similar to the TSAGI 12. So coming to the longitudinal stabilities, MS60 and TSAGI 12 are having good performance. However, the Falcon and Epler 339 are showed very low stabilities. So coming to endurance, the Epler 339 and NACA series are performing better, but as I told, we are giving some initial angle of attack while designing the plane. So here also MS series are having some advantages. So this is the references, and these all are conducted for high Reynolds numbers.
So the floor is open for the questions.
So here you use the open VSP.
Yes, sir.
So what is full form of VSP?
Sir, it is Open Vehicle Sketch Pad. It is some 30 years back NASA have developed this software. Nowadays also it is very efficient because coming to blended wing, when we'll go for a complex geometry, there are some we'll call that dihedral, also sweep back and winglets. So designing that using our normal softwares like CATIA and Siemens NX is very complex because we are importing the aerofoil and changing it according to the plane and orientation in the sweep wave. But VSP is providing a very these things can be designed within 1 to 2 minutes.
But this is more specific for the only this type of cases.
No, for all kind of aerial systems. We can design fuselages, also the propellers, or this is just some 100 MB software, and this all things I have did in 1-2 days.
It's okay. It is a finite volume or finite element of some.
So both, we can do the structural analysis also. We can also do the structural analysis also. FDM is also possible, but we are taking the VLM model, vortex
vortex lattice method.
Yes.
Okay. So there is no finite element, finite volume. This
no,
is
FEM is also existing. We can do the structural analysis.
Okay.
But here we have not used.
But it kind of a method and kind of a model we have developed a VLM.
Yes.
So you have not shown the original aircrafts, I think. And what value L by D ratio you have got maximum?
So it is around
28.
28.
28.
Yes.
For which aircraft? Some aircraft. Huh?
Sorry?
So what is the actual value of that aircraft with which you have compared?
Sir, this is a conceptual model, not taken.
Not compared to that.
So this.
Any validation you have done for this? Any validation?
Sir, validation, the VSP source itself said that more than a 200 vortex model are giving almost 75 to 80% similar result to the normal FEM methods, whichever we are doing in structured or unstructured mesh. So almost 75%, but in a very less site, less computational power and time.
So, do you have aerospace engineering over there at IIT Bhubaneswar?
No, sir. Actually, I am in a modular UCAV. We are designing with our own engine, in-house engine. The engine is already done, so I have taken care of the I am going to take care of the body design. So my professors are from ADE, so they are giving me a push. But unfortunately, we don't have aerospace department in the OD side.
So actually, here the meshing is not like a.
No, sir. There is no mesh. No. Yeah, there are some
discretization. There is a pipe method. Yes, is a one different type of.
Yes, but I was in CSIR. They followed the same thing.
They have a very advantage.
It's
computational time is very less.
Yes, sir. I have given to my juniors to come up with some CFD. They took 1 day, 2 days, and just come with one aerofoil with some results.
It is very fast, very.
Yeah, but it is not accurate. It is not accurate.
More specific and still accuracy is.
Yes, accuracy. But after finding some 0.7 is the CL is coming 0.02. In CFD, if we will directly go from open form or ANSYS, we will get almost around 0.2 6 not 0.22 or 2.5 2.3 this much variation will be there, but it will give in very less time.
Order remains same.
But sir, there we are using a proper if we use ICM, we'll get even very good results for structure.
Have you seen those lectures by Professor Pant?
Yes, sir. Yes,
yeah. So wetted area, etc. You can calculate all those things.
No, sir. In IIT Bombay also they have shown one time that ESP. From there I got inspired. That I am also doing CFX and star CCM, but it's just I found curious so that we can design some complex geometries in very short time, and also we can get some overview. Yes, sir. For a preliminary design. Yes, sir. I have did I have did the effects of velocity also. That become a very big paper. Also, I have did for each series. I have taken 5 aerofoils. We are planning for that journal.
So, what did you find there? Can you show the effect of velocity?
No, sir. I have not included here.
Okay, right. So,
but yes,
here.
But that is also coming approximation,
okay,
not accurate.
In your paper.
Yes.
Okay. Can you tell me what you got? What is the effect? If you
Sir,
CL, what will be the effect? CL will decrease at the same end or increase?
No, there will be like here it is not validating much because the viscosity effects it is neglecting it like from the starting, but the shock wave it will appear, it will like the solver is not giving accurate results, but from time concern and for computational concern it is a good methodology here.
Is there any need to validate your result with experimental result?
Yes, we can provide, but the design is very complex and for 350 we have to book a wind tunnel. That is
So
a
based on this software.
Yes, we can also validate with
based on the
CFX.
result which you obtained using the Open VSP.
Ji.
Okay, develop the airfoil. Okay, which you identified and used in the aircraft.
No, like
or experimentation.
sir,
with
mostly
the
I prepared TSAGI 12 for my UCAV design, which is a like sweepback dihedral UAV with a single jet turbine. We are like planning to fly it by like end of next year, like 2027. So there I have fixed TSAGI 12, but the MH60 is widely used nowadays, and they are saying how because in the region of 450 to 500 that is having a better option for TSAGI 12 and also for high mark, because that we are using in our MiG 20 like 21. So thank you.
Thank you so much. Now, I would like to call Dr. Agnew sir for facilitation. Now, as we conclude the session, we extend our heartfelt gratitude to our session chair, Dr. Rakesh Kumar, and our session co-chair, Dr. Basant Singh Sikawar, for their invaluable guidance and thoughtful engagement. Let us all give them a warm round of applause. May I request Dr. Agni Roy and Dr. Sanjay Singh to facilitation of our session chair and co-chair as a token of appreciation.
We request the session chair and co-chair to kindly join respected Sanjay Singh sir, Agni Roy sir, Narendra sir on the dais for the felicitation. Round of applause. May we please invite the co-chair for the felicitation, Mr. Basant Singh Shikarwar sir, Dr. Singh Shikarwar. Another round of applause, everybody. Thank you to our honorable chair and respected co-chair for conducting such an enlightening and thought. Thank you to our honorable. Finally, thank you to our honorable chair and respected co-chair for conducting such an enlightening and thought-provoking session. Thanks to the staff, faculty, and all the members of the organization committee for seamless execution and management of the event. Finally, a thanks to our excellent audience for being engaged and enthusiastic throughout the sessions. We shall continue the conference with more talks and sessions tomorrow starting at 9:30 sharp at F-3 Seminar Hall. We request all to be present on the location on time. Thank you and have a pleasant evening and join us for dinner for further networking.